Okay, I should be broadcasting on YouTube now. We can check everything. Check, 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 check. This is James Burke at the 2024 Mars Society Convention. Check. This is James. This is James on the Google Meet call. Check, check. Check, check. Do you want to do an AD test or something? Yeah. Okay. Okay. Yeah. Please. Okay. Please help yourself. You can just open another browser tab and
All right.
do whatever you need to do. Go right there. Open a new tab. If you can leave those other ones, that would be great.
Okay.
Thank you. Yeah.
Hey, James,
Yes, sir.
I have 2 videos in my presentation. Just want to make sure.
Yeah, I just downloaded them here for you to try out. So there they are right there.
All right, let's.
I don't know. Yeah, it's a little slow. And then I would do that one.
Okay, so there's audio in this.
Okay.
I don't mind if there's no audio. Okay. So would this play?
Hey guys, if we play a video on the laptop up here, shouldn't that be going into the? Mhm. Like there's 2 levels to it. The other one is we have to share it on the Meet also. So that part should work. We just do share this slideshow, which I'll do before you come up. That'll get that out to everyone. But yeah, it's not working in the room right now.
Okay.
Which is this, these guys, this setup. So your stuff looks good. Oh. Okay. Let me try that. Yeah, I think that's what we were doing yesterday to make this work. Let's see. That one doesn't seem like.
I think you just muted it.
I muted this laptop because I'm trying to get this stuff to work with it. Yeah. Line in. Speakers. Yeah.
If it doesn't have audio, I can work with that because I can just talk over it.
The other thing is we could, I think, open in a Google tab. Open the video in a Google tab. Oh wait, that wasn't it. Oh, this is a zip file. That's what's going on. Let's take these out of the zip file. Glad we're doing this now.
Yeah.
Now let's play this from the desktop, not the zip file. What I was saying was we could also, if it's just the video, we can open that in a tab and then share the tab. Chrome tab. And then it says also share tab audio. Two videos up in two tabs for you, and then you can just flip over to those and play them. You just hit space
Okay.
to play them.
Actually, the first one, if it didn't have audio, is even better. But for this one, I want the audio.
Okay.
Okay.
Cool. Yep.
Thank you.
Yeah, of course. And Brian, I'll be right here if you need anything when you're talking. So.
And it just so happened that this week I interviewed for the fighters books. And so that was a real girl.
Yeah. So, you know,
That was so much. Yeah. It was all roots there.
yeah.
There's a whole lead up to it too, because there was that. They had a panel where it was just. I was there. Yeah. It was chaos. Right.
I'm currently working on
So many.
I'm actually working
City show. Yeah.
I've been I'm
Power to say. The fact that he did it. Well, we're all there. Bigger. Exactly. In concentration. Yeah. There's only one place he could have gone. The perfect place to go. I'll send you. Because, I wrote that up.
I know, I didn't know about that, but I'll have to.
Just felt like something's happening. Yeah. It's like, so right. They love these guys. Oh, let me show you this. That was it. We were for some pictures they said. I was watching.
We'll watch it all night. So.
Yeah, yeah. That should be the first one that I would. Yeah.
And also, every so we're basically taking sets.
Yeah.
And I watched this series once a year. And so basically start up
Something's all watch. And then you watch something that. Yeah, so it's in the background.
That we just need
it's not something that
Yeah.
I emailed,
As long as you Oh, yeah. That's, yeah, yeah. All right. So it's they're up there. Mhm. Yeah. Yeah. A lot of those. Yes, the one that's kind of a little darker. I don't know why I'm not. Basically.
I'm James.
I'm David.
Nice to meet you. Yeah,
Do you live here in Seattle?
I do.
Okay.
I've lived here for 25 years, worked at Microsoft, and now I'm trying to help get more space companies to come move here through Space Northwest. And then We have about 100
That's worked out.
I hope so.
How's Robert doing? Because I was watching.
Yeah, he's doing okay.
Yeah. That would be very disappointing. Yeah, timing is really bad. Yeah.
We'd be low in our spot, though.
Yeah.
It's a good full.
Okay. Yeah. I mean, there are always some hiccups, but it seems like things are just do my thing and trust on.
Yeah, I think we'll have no issues with what you've done now. State all did the testing.
Oh, good.
Yeah, they'll pop on. We did it 2 of those yesterday.
And they do their own slides, so they're in charge.
Be all set.
Yeah.
We'll just sit back and watch it.
Good.
Share their
That's
slides.
what I like. Sit back and watch.
Yeah, so, and I think like, if you want, we can pull a chair up on the stage for you, or you can stand at the podium.
I can stand at the podium, but I probably have some folks that I'll just be holding on the hands, but I don't think that will.
And I'll be right here to help with any.
Okay, all right. Good. And then for the banquet tomorrow night, is that something I could attend?
Absolutely.
Okay.
You would feel free to, yeah,
Uh-huh.
you don't have to do anything.
Okay.
Just show up.
Mhm. And then Alan Stern is going to talk.
Yeah. Yeah, we're about to start. So.
Yeah. Let's see. Yeah.
Just consolidate. This time. It's a Lego. These are all kind of simulated logo models, and it was in the sky of the original. This is the startups. Started it's not realistic. It's just a corresponding pattern. Hey, how are you? Online meeting. It is, but I would much rather just if I didn't have to do all of it.
What size do you need? What size? This is large.
Yeah, it's exhausting. It's a lot of work. It's sweaty going long distances.
Good morning, everyone. Here we are, day 2. I see some smiles, some bright eyes, bushy tails, excited for continuing our plenary speakers today. Just want to make a couple announcements, reminder about the reception tonight at the Burke Museum. It's going to be really fun. Please show up. It is free. Make sure you have your badge on to get into the reception. It is 21 and up, so sorry anybody that is not of legal drinking age to not be in attendance. We are also doing the Mars VR this afternoon from 1 to 4 in room 334 by Jeff Rayner and the team, so check that out. And want to remind everybody that we do have the raffle. So right outside the main ballroom to the right is the raffle item. It is for students. It's a Lego set. James, keep me honest, it's the Perseverance rover, right? Yep, exactly. So if you're a student, please enter that raffle. All right, let's get to the fun stuff. So next up for today, we have Dr. David Catling, who is a professor of Earth and Space Sciences in the Astrobiology Department of the University of Washington. His research focuses on the coevolution of planetary atmospheres, surfaces, and life, aiming to understand planetary habitability. Dr. Catling has significantly contributed to NASA's Mars exploration, including the Phoenix mission to the northern polar region of Mars in 2008. With a PhD from the University of Oxford and prior experience at NASA's AIM Research Center, he brings extensive expertise to the study of Mars environmental evolution and the potential for life on the red planet. Everybody welcome Dr. David Catling.
Well, good morning. So my talk is about Mars in the past, which hopefully complements the next talk, which is going to be Mars in the far future by Edwin Kite. And I'm just going to talk about how Mars ended up to where it is today as far as we understand it. And this is the outline of my talk. Going to give a little bit of motivation for all this focus on Mars and its past. And we're particularly concerned scientifically about volatiles. So those are substances that tend to form a gas or vapor or liquid at prevailing planetary temperatures because they determine habitability. Mars, of course, today has a very thin atmosphere and cold climate. The mean global temperature is about minus 55 degrees Celsius, which is quite similar to the Antarctic interior. And it's extremely dry. And then part of the motivation for Mars, of course, is to ask the question, is there life there today, or was there ever life on Mars? So what do we know about that? So let's start with the motivation, which just comes from these big questions that we all have pondered at some time. Are we alone in the cosmos? Where do we come from? Where are we going? Some people like to add a final one. How much should I tip to this? But we all have looked up at the night sky and reflected upon some of these questions. I avoid the fourth one because it's philosophical. But talking of philosophy, this question about whether there's life beyond us was asked a long time ago in a book by Aristotle from over 2,300 years ago. He asked if other Earth-like worlds and life exists. His answer was no. Perhaps that's why he looks so sad. I don't know. But the thing is, today we don't need to go and ask some old guy or old lady their opinion because we have science and technology. So we can gather scientific data to try and answer the question objectively. And when we think about life, it's carbon-based for reasons that I could go into, but basically there's a limited toolkit, which is the periodic table, and very difficult to get things as complicated as us or even microbes unless they're carbon-based, and also that's what you expect from the origin of life. And also life as we know it requires liquid water as a solvent, and liquid water is extremely abundant throughout the cosmos, hydrogen being the most abundant element, oxygen being number 3. So that's why there's a focus on follow the water, and we can follow the water back to its origin. Where did the water come from on the Earth or on Mars? And we can look to the asteroids, in other words, the building blocks of the various planets. So here, for example, on the right, you see distance from the sun, and you see the types of asteroids, E-type, S-type, M-type, and so on. And then on the left, there's also distance from the sun, and then the water content of these various types of meteorites. And these various types of meteorites kind of map to the asteroids that we can see with these various arrows that I've put on here. And you can see that if you construct a planet from even relatively interior meteorites originating from interior asteroids, they have enough water basically to make the Earth's water content, because the Earth as a whole, although we have our liquid ocean, is actually quite dry when you take as a bulk average. And so as you go out in the solar system, maybe to the outer asteroid belt, you might get asteroids with 10% by weight water ice. And so in general, we expect Mars to have been enriched in volatiles, perhaps even more than the Earth, because it's farther out from the sun. We can also look at isotopes like deuterium, hydrogen, nitrogen isotopes, and that confirms that we did indeed get the water and our other volatiles, nitrogen, for example, and carbon from asteroids. So all the water is basically asteroid water. That's what we drink, that's what we're made of, that's what's in the ocean, and also interior to the Earth. Maybe there's 2 to 5 oceans worth of water inside the mantle. Those are sort of current estimates. And indeed, there's water on Mars. So this is a map from Mars Odyssey spacecraft, and it used neutron spectrometry to deduce that in those blue regions, there's subsurface ice. And then, as was mentioned in the introduction, a mission that I was involved in with a very small science team. We had 35 scientists, a bit different from the current rovers. The Phoenix lander, we actually dug in the soil, and you might remember that we revealed some white stuff. That was what it was initially called, but then it turned to vapor on timescales that we expected for ice. And indeed, we verified that what the orbiter had deduced from this rather indirect physics was correct. And then more recently, there have been impacts into the high latitudes of Mars that have revealed the ice. And then after some time, a few months, the ice goes away because it sublimates. So indeed, there's a lot of subsurface ice. How deep it goes is a little bit unknown, but there's some information from the morphology of impact craters that maybe it's probably 10, 20 meters deep and no deeper than that. So there's certainly ice there, but when we add up all the inventory, we can look at the polar ice caps, and we can ask the question, if we melted everything, how deep would a layer be around the whole planet? So for example, if you melted the polar ice caps, you might get up to about 20 meters of global equivalent layer water. If you took the ice out of the regolith, the adsorbed water, another 20 meters. There's probably some covered glaciers on Mars. That's just a few meters. And in fact, most of the water seems to reside in what we call alteration minerals, where water in the past reacted with this minerals, rocks on the surface of Mars, and has kind of added water into them. So you're probably familiar with gypsum, plaster of Paris. So that's calcium sulfate with 2 H2Os in it. That's an example of a mineral that's got water locked up within it. And there are probably a lot of clay minerals. And this kind of how much there is depends on how much you extrapolate downwards. Was Mars' atmosphere thicker in the past with carbon dioxide, and where did that go? The atmosphere today is 6 millibars, or in SI units, 600 pascals. Surface pressure. The polar caps, if we were to turn them into gas would basically double the Martian atmosphere. Carbonate rocks, there aren't many of those compared to the Earth, where they're quite ubiquitous. But it's been estimated that that would be, about a factor of 2 times the present Martian atmosphere. But to be honest, we don't really know because they could be buried. We can also look at meteorites, like the famous Allen Hills 84001 meteorite, which has some carbonates in it, and say, well, let's say that's typical, and we extrapolate downwards through hundreds of meters. Then maybe there's something like, 10 times the present Martian atmosphere locked within that carbonate, which, if you heated it up to a high enough temperature, would produce CO2. And this, but probably one of the major things is there's actually carbonate in the soil or dust. It was something that, for example, the Phoenix lander identified, but it had also been identified spectroscopically from orbital instruments. Another volatile is sulfur. Today, a lot of the sulfur on the Earth, at least in the very surface of the Earth, is in the ocean, and that's plotted on here in kilograms. And then if you look at Mars, the soil and dust and the sedimentary rocks that we can do an inventory and get maybe about 10 times less than what's in the Earth's ocean, which you might expect because Mars is 10 times less roughly the mass. So there's water on Mars. It's just not there as a liquid. It's locked up in various places. And similarly, there's more atmosphere on Mars, but it's also locked up in various places. And there's also things that we find in the ocean on the Earth that are locked up in various places on Mars. So that makes it a dry planet, like our other neighbor, except, of course, our other neighbor is not user-friendly for visits, Venus, but it's so hot that water can only exist as a vapor, and there's not much of it. And scientifically, this is the reason why Mars hasn't had this sort of nice temperature like the Earth over geologic time, because on Earth we have this special situation where we basically have a geological thermostat called the carbonate silicate cycle. And the way this works is that over a million-year time scale, if the planet is very hot, then you get a lot of rainfall. The carbon dioxide reacts with the continental minerals, makes cations. Those are the positively charged ones, and negatively charged anions that get washed by rivers into the ocean. And then the CO2 gets removed into calcium carbonate, which is shown on this diagram here. So that it's a negative feedback. It will draw down the CO2 very slowly, but over time to a more temperate climate. And conversely, if it's cold, covered with ice, the planet, then this kind of shuts down this weathering cycle, but CO2 continues to be pumped out by volcanoes. So a key difference here, of course, is that Mars doesn't have this liquid water on its surface, and of course it doesn't have an active tectonism. And this, of course, actually, that little picture forms the basis of our theory of the habitable zone around the sun and also around other stars. And the idea is if you go too far out in the habitable zone, carbon dioxide will condense, or you'll need so much carbon dioxide to warm your planet that it starts scattering all the light away. And basically the negative feedback breaks. And on the inner edge, you get so hot that the atmosphere fills with moisture, and you get this phenomenon called the runaway greenhouse effect, where the planet can't radiate as much energy as is getting in from sunlight, and so it sort of literally runs away and becomes hotter and hotter until the surface melts, and the water vapor goes up into the upper atmosphere and escapes as it's broken down. So that's sort of an overview of where Mars is today, but what about water in the past? There's a lot that one could talk about here, but the basic essence is that we see these huge outflow channels. So this is a very crude geomorphic map of Mars, and where that sort of mauve purple stuff is, and marked channels, those are regions of outflow channels. And these are very big, 20 to 100 kilometers wide, deep on the highlands, broad and shallow on the plains. So these typically originate in the highlands. That's that reddish color, the cratered highlands, and they go out to the northern lowlands, the plains. But in addition, on those northern lowlands, which you can't see on this map, but there are many of these valley networks, much smaller features, typically a kilometer or so wide, with tributaries on the older terrain. But in addition, there's also on this older terrain, if you look at the craters, they're heavily eroded, their rims have come down. Sometimes they're just sort of very faint features because they've been heavily eroded. And then if you look within the craters, you can see delta deposits. So that's where water has come in and it's deposited its sediments underneath some lake, for example. And we can also look at lots of geochemical evidence about the past liquid water that I mentioned earlier, where the water has been locked up. So Mars had this fluvial history, fluvial meaning stream or river-related features that we can see today cut into the landscape. But then what happened to this climate and atmosphere and the surface if it was supporting liquid water in the past? And it basically comes down to two things. Mars is small and it's far from the sun. And so because it's small, it can suffer atmospheric loss. If it's hit by a big impact early on, that can impart sufficient kinetic energy that gases escape. That's what we call impact erosion. And it's sort of a feedback thing. The more you lose, the more susceptible you are to loss. Because it's small, there's a little heat flow today, probably something like 20 milliwatts per square meter compared to Earth's average of 90 milliwatts. There's no plate tectonics because of this low heat flow. And there's no magnetic field, dipole magnetic field, which doesn't protect the planet from the solar wind. In fact, if you look at objects in the solar system, there's a sort of dividing line between estimated impact velocity and escape velocity, where if it's above 5, the estimated impact velocity relative to escape velocity, then you end up with these, the worlds here that are marked with the gray circles that don't have atmospheres. And then the more colorful objects below are the ones that do have their atmospheres and not subject to impact erosion. Mars sort of straddles this line. It's depending on the speed of the object. With long period comets, they would be erosive for Mars. Lower velocity asteroids might add things to Mars. This also explains why, for example, Ganymede around Jupiter in the big gravitational well of Jupiter doesn't have an atmosphere, but Titan, similar size in the lesser gravitational well of Saturn, does have a thick atmosphere. And the other thing that causes escape is heating from the sun. And you can do a similar diagram where on the right-hand side here, objects with atmospheres, and on the left-hand side, objects without atmospheres. And we wrote this paper a few years ago and said, oh, there's a dividing line here as well. We called it the cosmic shoreline, which is caught on in the exoplanet community. And we said, look, you could use this to predict empirically which exoplanets might have atmospheres or might not have atmospheres. So for example, here we would say that Proxima Centauri b, our nearest known planet, probably has an atmosphere on this basis, or maybe not, because actually early on it was beyond what we call the runaway greenhouse limit. Now, if you delve into the isotopes of gases and substances on Mars, typically the light isotope has been lost relative to the heavy isotope. And I'm not going to dwell on this because you should never present complicated tables in a presentation. But basically, if you look through these various isotope ratios, say the deuterium hydrogen is a factor of 6 bigger than on the Earth, and that suggests water loss at the top of the atmosphere. That's also why Mars is red. The hydrogen has been lost relative to oxygen, which has got left behind and rusted the planet. Ultimately, that's the reason. And we can look at other isotopes that indicate various types of erosion, such as impact erosion that I talked about earlier, where the primordial isotope has been lost, for example, 36 argon, and then a radiogenic isotope that is produced over time from the decay of potassium, 40 argon, gets relatively enriched, say, compared to what we've got on Earth. So there's evidence for all of these escape processes. And when you put it all together, there's sort of a picture like this, that, okay, we're here today, but we've lost a lot of atmosphere, 6 millibars. If we go back maybe 3.54 billion years, we've got 10 times more. Go back to the very earliest planet, another 10 times more, roughly speaking. So let me get on to my final topic. Is there life on Mars today, or was there ever life on Mars? One way to address this topic is to think, what do we know about signs of life on Earth, earliest signs of life on Earth? The oldest possible sign of life is actually a single zircon crystal, which has some graphite inside it, which is enriched in carbon-12, which is what life does. It enriches the light isotope of carbon relative to carbon-13. But you don't really know the context, and it's just a piece of graphite. Did it come from biology or not? Don't really know. Then, if you go forward in time a little bit to 3.8 billion years ago, you can find what's called a black shale. So that's a fine sedimentary rock. It's black because it's got so much carbon in it, but it's been heated up and pressurized, and now the carbon is all graphite in the form of flakes. And that was discovered by this guy, Minnick Rosing, a Greenlander in Greenland. And then more recently, people have done genetic studies, one that just came out, and said that our last universal common ancestor lived about 4.2 billion years ago. So life must have originated very early, if that's correct. As we go forward in time, you can find stromatolites, which are these mounds produced by photosynthesizers. Here's some in Western Australia. It makes a very nice seat if you're tired from walking up hills. That's me sitting on the world's oldest stromatolites. Don't worry, it doesn't do any damage. They're just as hard as rock. They are rock. And what we can say is that Earth was inhabited within hundreds of millions of years of its formation, and maybe Mars or Venus, which perhaps might have been more Earth-like then, evolved life too. We can only find out from exploration, and this is what current, at least US exploration, has looked like in the past and in the future. And what do we know from current studies? Well, let's just focus on the more recent things. So you may remember, let's go back to the rovers Spirit and Opportunity from 2004 and forward a little bit to the Curiosity rover. They landed here on the Martian map. And some key takeaways is that they confirmed that there was water transported sediments on the surface of Mars, indicated by the small-scale sedimentary layers, shallow water, indicated by these things called blueberries, which are concretions in geology, which are little spheres, spherical type objects, spherules, that form when groundwater passes through the subsurface, and these little things can precipitate out from what's in the groundwater. Then there's Curiosity rover, been exploring Gale Crater, and probably a key takeaway is the inference from, again, it's sedimentary rocks that have been observed that have suggested benign waters that perhaps lasted at least hundreds or thousands, maybe tens of thousands of years, and bringing things right up to date. Perseverance rover, which landed in February 2021, and in Jezero crater, this 45-kilometer diameter crater. And up there on the west side, you'll see an inlet valley, and you'll see a delta feature. And that, of course, has been the focus of this mission, because it's thought, well, a delta by definition forms under water. So this is this, and then there's an outlet channel. So it's thought that this was once a big crater lake with this well-preserved delta deposit. And here's where the rover is now. It's currently at Neretva Vallis. That's the inlet side of things. It landed down in the crater. These little red marks show where it's got sample tubes for prospective sample return. And it has 43 of those, 38 tubes for putting in rock and regolith. And then that's what the tube looks like, about 6 inches long on the left. And there are also some witness tubes, and one for air, one for soil. And the instruments on board Perseverance rover can indeed look for signs of life, because prior to going to Mars, they're actually used to look at old signs of life on the Earth. So, for example, there's a X-ray fluorescence instrument called PIXL, Planetary Instrument for X-ray Lithochemistry. And there's a Raman spectroscopy luminescence instrument called Sherlock, which is a real mouthful if I was to expand the acronym. So you can Google it. But basically, these things can detect the presence of different minerals and elements, also organics. With Perseverance rover, it's possible to abrade the rock to get rid of that dusty surface, to look inside, and that was done first of all in the crater itself. And of course, we can, these little diagrams on the left here show the instrument footprints So you can co-locate various instruments, look at what's in there, identify igneous minerals, volcanic minerals, salts, and even more recently, this one came out 2 weeks ago. People got excited about this because it was has been advertised as a potential biosignature. Yeah, I'm almost done actually. Potential biosignature. So this is, I showed you that diagram where the rover is now. This is basically in that region of the northern edge of Neretna Vallis, that inlet to the crater, where it cuts through the crater rim. It's a river that fed the lake. And what's really interesting about this sample is that Pixel, that's the X-ray fluorescence instrument, shows that this, for example, this is a natural surface. This natural surface in the middle here is fine-grained with silicon, aluminum, and iron. But there are these so-called leopard spots, these white areas where, iron is red because it's oxidized. But if it becomes unoxidized, it becomes chemically reduced, it can be pale, like these white spots. And these rims also have iron phosphate around them, the little black rims of the so-called leopard spots. These big veins are calcium sulfate with possible sulfide. So why is this of interest? Because when you find chemicals in different redox states, the oxidized form, the reduced form on Earth, often biology does that. It's how biology works. All biology uses redox chemistry. It's what you're doing now. You're oxidizing whatever you had for breakfast with oxygen, organic stuff, and making CO2 and water. Microbes are much more diverse in their metabolism, but they all use redox chemistry. And in fact, it's probably universal throughout the galaxy. That's the way life works, given the periodic table of elements. And the other thing is that the Raman instrument found organics, not here, but in a nearby abrasion patch, the same rock material. And so we have organics, we have redox differentiation, we have this going on. So this then is a prime target, but unfortunately, Perseverance rover can't go beyond this because it just doesn't have the instruments, say, to look at the isotopes of things in this rock. So that's why these samples need to come back. So I've got a couple of slides of concluding comments. So I'm actually on the science team of Perseverance rover. What we've found is that the crater floor rocks contain igneous minerals, volcanic minerals, but also minor salts that could have come from a prolonged interaction with groundwater, maybe infiltration from a lake, potential habitable conditions and biosignature preservation. But also on the delta, there have been sedimentary mudstones, there have been rocks with carbonates and igneous minerals, possibly where waters flowed through and oxidized the iron and made hydrogen on Earth. Life lives off such things. We've never seen those black shales. Remember that picture I showed you of Minnick Rosing, the Greenlander, with that black shale? Never found those on Mars. So to me, that suggests that maybe life didn't get that far on Mars, because to produce black shales, you need photosynthesis. You use the energy of sunlight to make a lot of organic carbon, and that goes into the rocks and makes them black. So maybe what we're looking for is simpler forms of life. So the search for life then can help us perhaps understand the evolution of life, or even an unsolved problem in science, the origin of life on Mars. So this is still in progress. Let's return to the big picture. 2 weeks ago, there was a scientific conference at Caltech, the 10th Mars conference. One thing that struck me is that many of the same questions that were asked when I was a kid, so decades ago, are still there. We don't know the absolute ages of the surfaces. We don't know the evolution of volcanism over time. We don't have an accurate history of the Mars atmosphere and its climate and its water. There's a debate about whether Mars had ocean. We don't know whether there's life. And certainly, sample return will help with that, and with chronology, nuanced geochemistry. But it shows you the limits of payloads and the difficulty of connecting local to the global. And so it shows you perhaps why human exploration would be a great step forward in exploring Mars and answering some of these questions instead of leaving them unanswered for decades. So to summarize then, I talked about the scientific motivation for exploring Mars, comparative planetology and astrobiology, whether there was life there. I talked about Mars evolution, basically started in a good condition, has got to where it is, the permanent ice age from volatile loss. And I talked about how the fact that there are still many unanswered questions. We know a lot about Mars. There's a huge amount of data. It's second to the Earth, but it's become a fire hose. So there's 600 papers a year, scientific papers. I can't keep up with them all. Most people can't. So we're now specialists. There's Martian geologists, there's Martian atmospheric scientists or whatever, a bit like the Earth. But still, many of these big, basic unanswered questions are unanswered from decades ago. And while sample return would help, human exploration could provide so much more. Thank you.
We have time for one question. There we go.
If we fast forward 500 years and we've managed to terraform Mars and given it some kind of atmosphere and surface water, do you see a way to keep them in the absence of a magnetic field and tectonic activity and volcanism on Mars, or will they inevitably go away again as they did in the past?
They will over time, but fortunately the time scales are long. And so basically you're going to have, I mean, maybe Edwin's going to talk about this, but you're going to have some like industrial process to continually pump out what you need to warm the climate. So you're going to be constantly fighting against it, but you've got time scales on your side because things like us are just, snaps of a finger in geologic time. And what we're talking about for atmospheric loss processes are generally much slower, thousands, tens of thousands, even millions of years. So, yeah, you would have to work against it. That's all.
Thank you so much. Is Edwin Kite here? All right, come on up. Get your slides loaded.
PowerPoint.
Yeah, I got them right here. Okay, you're all set.
All right. Next up, we have Professor Edwin Kite, who's a prominent researcher at the University of Chicago, who has pioneered a novel approach to terraforming Mars. Working with teams from Northwestern University and the University of Central Florida, Professor Kite's team has developed a method to suspend iron or aluminum nanorods in Mars' atmosphere, creating essentially a greenhouse effect that warms the planet. This warming could release potential carbon dioxide from the ice caps, thickening the atmosphere and further raising temperatures, potentially reviving Martian streams and lakes. Everybody welcome Professor Edwin Kite.
Thank you for that introduction. Hello, everyone. I'm very happy to be here. Is there a clicker or something to advance
You can just
slides?
use the arrow keys here. Should be able to work. Yeah, on the screen should be able to advance.
Thank you. So I mostly work on Mars rovers and climate modeling of the past, but today I'd like to talk about possibilities for Mars's future. So the Mars rovers are exploring the traces of arguably the greatest known environmental catastrophe, which is that Mars once had rivers and lakes and a habitable climate, at least intermittently, but lost it. So on the left, we see the large valley networks that David Cowling mentioned in his talk. And on the right, we see one of the rover field sites, a river delta and lake deposits. So So Mars also had rivers in the past, so much warmer than it is now. But Mars today is too cold for life. So this is the basic obstacle to establishing a photosynthetic biosphere on Mars. So I'll focus on that first step in today's talk, warming Mars up. This is a necessary first step, but it is insufficient for habitability. A warm Mars with some liquid water would still be a hostile environment, even for extreme life, because of the simultaneous challenges of high ultraviolet light, salty soil, perchlorates in the soil, low pressure, which by itself is not a problem. There are dozens of species of extremophile organisms that can grow at 7 millibars, but it's still a stressor. And any pioneer organism would have to deal with all those stresses simultaneously. I'm not going to talk about those problems today, but if you're interested in that step, then you can either read the proceedings of the April 2024 Pasadena Mars Terraforming Workshop, which are online, so just Googling Mars Terraforming Workshop proceedings will bring it up. And if you're interested particularly in the Pioneer organism step, then take a look at Pioneer Labs. It's a new focused research organization based in San Francisco, which is working on that. Okay, so that's the context, but I'm going to focus almost exclusively on the first step today, which is just warming up the planet so simple life has a chance. And of course, this has been an area of investigation for over 50 years. So Carl Sagan in 1971, and then in more detail in 1973, suggested adding some dark substance to the polar caps to release carbon dioxide, perhaps set up a rapid release of carbon dioxide to make Mars's atmosphere thick again. And as early as the mid-1970s, NASA was sponsoring studies to essentially look at all of the steps from the previous slide. So not just warming Mars up, but also establishing a photosynthetic biosphere, raising the oxygen level, and so on. And so if you look at the history of studies on warming Mars up over the last 50 years, you can sort of put it on axes of how easy do people think it is versus time. So the first probe showed a planet that superficially resembled the moon with a tenuous atmosphere. So that's sort of the first trough, Mariner 4 in the 1960s. And then calculations by Chris McKay, building on work by Carl Sagan, showed that Mars could be close to a tipping point that would release abundant carbon dioxide back into the atmosphere, which sounds good. And then Mimi Gerstel and later Margarita Marinova showed that super greenhouse gases, for example, chlorofluorocarbons, could warm Mars. So the optimal cocktail of super greenhouse gases to do this, you need about 40 billion tons in the atmosphere. So that's a big industrial effort. And part of their motivation was the idea that if you did that, then natural release of carbon dioxide would take you the rest of the way. However, Joukowsky and Edwards underscored in a 2018 paper, and this is consistent with, David had a slide on this, that the tipping point idea, which motivated a lot of the early work, doesn't work. And the problem is that there just isn't enough carbon dioxide stored as ice on Mars to make it work. The polar caps are mostly water ice, not carbon dioxide. There is some carbon dioxide in the polar caps, but only enough to double the atmosphere, not to thicken it to the hundreds of millibars that you would need for carbon dioxide alone to produce a warm Mars. But recently things are looking up, thanks to a local warming study by Harvard and JPL, and our own global warming work, which I'll now describe. So for this audience, you probably already know that Mars's polar caps have at least enough water for a 30-meter global layer spread out evenly, and that about 1/3 of Mars's surface has shallow buried water ice. That shallow buried water ice extends equatorwards to about 40 or 50 degrees. There is circumstantial evidence for water ice at lower latitudes, but basically no proof. And so the necessity is not just to warm Mars up to 273 K. Actually, temperatures measured by Curiosity rover and on the Curiosity science team do get on to up to 273 K, but there's no water ice there to melt. And so you need to warm things up to 273 K where the water ice is, which is, as shown by this impact, a little bit in the subsurface, polewards of 40 or 50 degrees in both hemispheres. And we have pretty good maps of the distribution of this water ice from indirect means like neutron spectroscopy and gamma ray spectroscopy, confirmed spectacularly in some cases by geologic exposures of the ice in the aftermath of impact. So those little chunks of ice don't last long, they sublimate away in the dry air. So previous work on warming Mars globally emphasizes greenhouse gases. What this plot shows is output from a three-dimensional calculation, not by me, by Isabelle Decker, using Chris and Margarita's optimal cocktail of greenhouse gases. So the red curve is about 30 Kelvin warmer than the baseline. So that's the point at which you start to melt the ice during the warm season, which is perihelion season. Mars's orbit has an eccentricity of 0.09, and so at perihelion season, you get about 40% more sunlight than at aphelion season. Okay, so to do this, you need about 1 kilogram per meter squared column of added gas. So that's not bad. These are potent greenhouse gases, but 1 kilogram per meter squared multiplied by the surface area of Mars is about 100 billion tons of fluorine. The gases are mostly fluorine. And there's not much fluorine in the Mars soil, and we don't know of any concentrated deposits. So in the regime of, well, you can warm Mars, but first you have to mine much of Mars down to depths of hundreds of meters or more. And if this is the best we can do, then warming Mars is essentially still science fiction, a problem for future generations and not for the people in this room right now. We asked, can Mars be warmed with aerosols instead of gases? This is a fairly obvious idea, so it's probably been thought of before, but I haven't been able to find an investigation of this that predates our team's work. I'll now describe results we published yesterday in Science Advances. The paper is open access, you can read it all. This is the first paper from our collaboration. The lead author is Samena Ansari. She's an electrical engineering PhD student at Northwestern, working with Professor Huma Maseni. Northwestern did the nanophotonics. I did the 3D climate modeling with significant help from Dr. Liam Steele when he was a postdoc in my group. And Professor Ramses Ramirez at the University of Central Florida did 1D climate modeling as a cross-check on the 3D results. So I'm going to talk through the principle of using aerosol to warm Mars using natural dust as a starting point. But natural dust actually cools Mars. So let's talk through how this happens. So the Mars sky is always dusty. Due to its small size, natural dust is lofted to high altitude, tens of kilometers, and it's always visible in the Mars sky. It's actually present up to 60 kilometers altitude. So the top panel, that sigma subscript x comma r, is the total cross-section for a single dust grain. The sum of the scattering and absorption as a function of wavelength. So that is the solid line in the top panel. The dotted line in the top panel, that's just the scattering contribution to that. So the distance between the dotted line and the solid line is the absorption contribution. So Mars dust blocks sunlight at short wavelengths, so less energy absorbed from the sun. But in the infrared regions, which is off to the right in the pink band, that's the wavelength range within which most of Mars's thermal infrared is emitted. Mars dust lets the infrared escape. So it doesn't look like much, but that's a log scale. So the lower on the right side is a big difference. So the net effect is to cool the planet. So the key wavelength ranges for cooling Mars again are the pink band on the right, corresponding to the peak black body emission from Mars's surface. And so we need to reduce that cooling using a greenhouse agent that stops the thermal emission from just leaking away to space. Mars has a lot of natural CO2, 180 kilograms per meter squared column of atmospheric CO2 gas. And that does a good job at blocking the thermal infrared from leaving in the gray band. But you can see that the pink band is wider than the gray band. These are called spectral windows. And in order to warm Mars, we need to block those spectral windows, which are at roughly 22 microns and 10 micron central wavelength. So the bottom panel just describes whether the light that is scattered is forward scattered or isotropically scattered. So if it's forward scattered, that's 1. And so that happens at short wavelengths. And at short wavelengths, you want forward scattering if you want to warm Mars up, because that means that the sunlight gets bounced down to the surface rather than being bounced back to space. At long wavelength, you actually want the scattering to be isotropic, so 0. And the reason for that is that you want as much as possible of the infrared radiation to be bounced back to the surface, keeping it available to warm Mars. Okay, so ideally, you would want an artificial aerosol that looks like this, one that lets sunlight in. So this is just an ideal aerosol, blocks the infrared, and forward scatters sunlight to the surface. So to test various candidate aerosols, we used three-dimensional finite difference time domain simulations of the interaction of the light with the particles. The particles are tumbled by Brownian motion. These are not active particles. They're just inert. You release them. They do their thing. Eventually, they break down in the natural environment. They'll be tumbled by Brownian motion, and so we had to calculate orientation average properties. And very quickly, just starting with a half wavelength metal dipole, we found nanoparticles that have the desired properties. So this is an example for 9 micron long iron nanorods. Aluminum nanorods behave similarly. They settle much more slowly than dust. So you put them in the air, they're swept up by natural winds. They take many years to settle out. You may ask, why is it 9 microns, not 11 microns? And that's related to losses within these particles. They're much, much smaller than the antennae we're familiar with from radio. And so analytic approaches don't work well for thinking about what the right lengths are. Okay, so the basic idea is release these particles probably during the daytime, because that's when the winds are, when the convection is strongest, so they're lofted to high altitude. You need to release them a little bit above the surface, but 10 meters above the surface is fine, and 100 meters above the surface is probably optimal, so a relatively short pipe. Then they're swept by natural winds across the planet. They have a lifetime in the atmosphere of a few years. They will eventually degrade, oxidize, break down. And so you need to keep resupplying them. There are possible loopholes to that statement. Photophoresis might allow self-lofting of the particles, and that's one possible avenue for future investigation. So here are the average surface temperatures during summer from a 3D climate model with 160 milligrams per meter squared of nanorods. So basically everything except the yellow is, everything is orange, red, or pink is above the above 273K, including most of the ground ice zones. And this is the average temperature during the summer, which I've defined fairly arbitrarily to just be the warmest 70 sol period during the year. Day-night average, but it's still, this is not the annual average temperature, which remains colder. Okay, and so this corresponds to about 30 liters per second, assuming a 10-year particle lifetime, which is probably about right. So this is the seasonal cycle in the control simulation on the left and in the warm simulation on the right. So this is just to illustrate that it's only warm during the summer in this case. This is roughly the threshold of nanorod loading at which things get interesting for allowing liquid water on Mars. But of course, there's no limit on adding more nanorods in principle. And so this shows the global mean surface temperature as a function of nanorod loading. So there are a few takeaways from this plot. What I showed you on the previous two slides is the black arrow. And so this is 5,000 times more effective on a per unit mass in the atmosphere basis than the best greenhouse gases. Because the x-axis is milligrams per meter squared, right? Whereas the previous best was 1 kilogram per meter squared. We've only just started looking at aerosols. So this is the sort of, these are not optimized aerosols. And that comparison is comparing to the optimal mix of greenhouse gases. So other takeaways, there doesn't seem to be any in principle barrier to getting to 273 Kelvin, but you can see that the x-axis is a log scale, whereas the y-axis is a linear scale. That's a very common attribute of like greenhouse agents, either gases or aerosols. So it does get harder and harder to warm as your desired temperature increases. But then the flip side of that is that you don't need a lot. If you just want 1/3 the warming as a test or precursor, then you only need roughly 10% of the infrastructure. So that's the log linear scaling working in your favor. Okay, yeah, so at about 10% loading, you already get about 1/3 of the warming. I think I'll skip this slide, but this is in our paper, which is open access. So this is the detailed vertical distribution and atmospheric thermal response. This is the first paper, and we're continuing to work on many other angles. So the obvious one is optimizing the particle design. So I'm confident that we can get at least a factor of several improvement beyond what we published yesterday, but I don't know how much more beyond that we can do. One totally different line we're pursuing is carbon nanoparticles. So carbon nanoparticles are attractive because graphene, for example, which was fairly recently discovered, was actually fairly recently popularized. It was actually discovered by Soviet scientists in the 50s, 60s, but no one paid attention. Has a 0.77 milligram per meter squared density, and so it's an attractive particle for Mars. We're investigating that. Thinking more about climate feedbacks as Mars warms. Right now, our models do not include carbon dioxide outgassing from the poles, but we're sure that would happen, and so that's an obvious additional effect to include. And water vapor buildup as well, because water vapor is a strong greenhouse gas. And we also want to do zoomed-in simulations, essentially weather modeling rather than climate modeling, of exactly what happens at the release point, because you have a very concentrated release of warming particles. And so what does that plume do? Manufacturing, for metals, one possible pathway is molten regolith electrolysis followed by physical vapor deposition with roll-to-roll processing. Then you've got to detach them from the roll and then release them. Key issues with this approach will be consumables. So if you're doing molten regolith electrolysis, you want your cathode and your anode to last as long as possible because your replacements have to be shipped in from Earth, and coatings on the particles. And many organizations are looking at this, including Blue Origin. And for both the metals and the carbon case, you're looking at about millions of tons needed in the atmosphere at any one time. So it's still a large amount, much smaller, of course, than metal production on Earth, but still a large amount compared to everything we've done for in-situ resource utilization beyond Earth. And so millions of tons for a 10-year lifetime would be hundreds of thousands of tons per year, sustained indefinitely. For carbon, MOXIE, which is an instrument on Perseverance, the rover that David Catling is associated with, electrolyzes carbon dioxide to make oxygen. With a small change in voltage, it can make carbon as well. And that can be used as feedstock for top-down synthesis of carbon nanoparticles, then ultrasonication for size sorting, further selection probably needed to get just the right sizes that you want because the resonant wavelength will depend on the size, and then release. An attribute with these particles, by the way, is that they're probably going to be only about 1 micron across. A little bit counterintuitively, graphene and related products resonate with thermal infrared at micron or sub-micron sizes. Key issues and needs for this approach will be efficient selection of just the right sizes, and again, coatings. And for this audience, so you need a particle making system, a terraforming engine, to be sent to Mars. So SpaceX's Mars rocket, Starship, makes its 5th flight in a few weeks. And in April, SpaceX released their plan for Mars. it says starships will send 250,000 tons to Mars every 27 months. So SpaceX is almost finished building a factory, shown here, whose purpose is to build one reusable Starship every 2 days. I don't know if SpaceX will get to the numbers shown here, but this is much more than you need to get a terraforming engine to Mars, and so we can do it from a logistics perspective. Okay, so what are the next steps? Simulation, we are designing much improved particles, we are studying weather modeling of plume release, and we need modeling for climate feedbacks. Batch manufacture for testing, we need to validate the simulated optical properties. We need flow tube measurements to measure clumping, and wind tunnel experiments. And this is building towards a precursor or test mission. Monitor the plume, measure the warming. And all of these will test assumptions. So clumping behavior, reuptake, plume behavior. So if things look good, then the next step will be to warm Mars by about 10 Kelvin. So why that number? It's much bigger than interannual variability, but it's still much less than you need to generate liquid water. And so the goal there will be to assess the size of natural climate feedbacks. And then finally, the final step would be full deployment, starting to melt the ice. And the assumptions that are tested there are just unknown unknowns. And so a nice attribute of this method is that if you stop releasing the particles, then the climate just goes back to the pre-perturbation state within a few years, because the particles just settle out. Okay, advocates of terraforming must first become advocates of scientific exploration of other worlds. If we're going to seriously contemplate warming Mars, we have to confront big remaining uncertainties. And in my mind, one of them is whether Mars has liquid water aquifers deep down. We just don't know. A good method to search is electromagnetic sounding. In my mind, that's a priority, both from a scientific perspective and also looking ahead from a warming Mars perspective. We know there's 30 meters or so global equivalent layer of water sitting on the surface, but we don't know how much global equivalent layer of water there is deep underground. And if they exist, we must check if they have extant life, because study of that life could have great benefits that would warrant robust protections for its habitat. So zooming out, this is my last but one slide. We don't know that Mars has the volatiles that would be necessary to produce an atmosphere breathable by humans. But we do know that Mars has enough volatiles to produce an atmosphere that could support photosynthetic biosphere and plant life. And so, not my metaphor, but quoting from a previous paper, as you warm Mars up, it's a little bit like descending a mountain. So Mars today is colder than the coldest places on Earth, uninhabitable for life. But as you warm things up, you enable more and more complicated photosynthetic life. And so, I'm sort of out of time, so I'll just summarize. I've talked today about warming Mars to enable a photosynthetic biosphere. Recent developments include flight test success for Starship, which improves our ability to land payloads on Mars by about 2 orders of magnitude per Mars landing. Aerosols offer 4 orders of magnitude improvement on previous proposals for globally warming Mars. There's a new FRO in synthetic biology for Mars, so pioneerlabs.org. And if you're interested in the big picture context, then I encourage you to check out the proceedings from the 2024 Pasadena Mars Terraforming Workshop, which are online. Our own next steps are focused on batch manufactured lab tests of the nanoparticles. Thank you.
Okay. Time for one or two questions here. Thank you. So I read about this news story. It made the news. It's pretty big news a couple days ago. They named it Glitter. They called it Glitter. Is that what you guys came up with, or was that more the news that came up with the glitter? The one question I had
was the difference between the aluminum and the iron. Is there going to be a big difference in the raising of the temperature?
So our paper is open access, so I'd encourage you to read the paper. I have no control on what happens some steps down the chain when reporters get to it. The difference between the iron and aluminum from a radiative properties perspective is small. Aluminum's advantages are it doesn't oxidize as quickly. It's lower density, so less mass for the same radiative warming, and less clumping concerns. So overall, we think aluminum is better. Is that the question? Okay.
If you have metallic nanoparticles in any concentration, would that block all radio communications?
So Mars already has an ionosphere, even though it has no magnetic field. It doesn't have an ionosphere. No, the wavelengths are very different. So laser communications are probably the way things are going anyway.
Thank you very much. We're going to end there. Thank you very much.
Thank you, Professor Edwin Kite, for your presentation. Next up, we have the highly anticipated NASA panel. I want to introduce our moderator for this session, which is Alan Boyle, who's a veteran science and space journalist known for his work as a science editor for MSNBC.com and NBCnews.com from 1996 to 2015, where he won the 2006 Space Frontier Award and the 2014 National Space Club Communication Award. Currently, he serves as a contributing editor at GeekWire and a contributor to Universe Today. Boyle is also the author of The Case for Pluto, How a Little Planet Made a Big Difference, and the creator of Cosmic Log and the Fiction Science Podcast. Everyone, welcome Alan Boyle.
Okay, thanks so much, Ashley. If you include my time at MSNBC and NBCnews.com, I've been covering Mars exploration for more than 25 years, starting with the Mars Pathfinder mission back in 1997. And I have great memories of attending my first Mars Society conference back in 2003. And there was an interesting guy I met back then. I think his name was Elon Musk. I guess he's doing some stuff now, so I guess he turned out okay. Now I'm honored to be on the other side of the podium to moderate this session on NASA's Mars exploration strategy. It's a crucial time to talk about the future of NASA's Mars strategy because there's so much going on right now. We're going to be discussing plans to bring fresh samples of Martian rock and soil back to Earth for study, a Mars sample return mission that is very much up in the air. And we're also going to be talking about how Mars exploration meshes with the Artemis moon program and how this all prepares for human exploration of Mars. So we have a high-powered panel to talk about all this. Tiffany Morgan is the Deputy Director of the Mars Exploration Program at NASA headquarters. Her job is to provide program leadership in exploring and characterizing Mars to understand its past and its current environment and to prepare the way for human exploration. Minnie Wadhwa is the principal scientist for the Mars Sample Return Campaign based at NASA's Jet Propulsion Lab. She's also the director of the School of Earth and Space Exploration at Arizona State University. And Patrick Chai leads the Mars architecture team at NASA's Langley Research Center and manages in-space transportation assessments as part of the agency's Exploration System Development Mission Directorate. He also co-leads the campaign assessment team for the Moon to Mars Architecture Development Office. I'm looking forward to hearing more about what's ahead for Mars exploration at NASA, and we'll try to leave plenty of time for your questions. And so without further ado, let's start out with a presentation from Tiffany Morgan. Take it away, Tiffany.
All right, good morning. I am very excited to be on this panel to talk about Mars and the plans NASA is developing for the future of exploration of Mars. So without further delay, on to the next. Sorry, getting used to the IT always, never ends. Okay. Before I share a few plans for the future, I'd like to highlight a few Mars events from the past year. This is a picture from Odyssey, the longest orbiting satellite at Mars. In fact, this past year, it completed 100,000 orbits around Mars. Our Odyssey captured this high altitude view of the planet's horizon and Olympus Mons. You can see it right there at the bottom of the image, the dark area. Using thermal emission imaging system, also known as THEMIS. And then above Olympus Mons, you can see a mixture of dust and water ice clouds on the horizon. Okay, and then Curiosity. Curiosity continues to explore Geddes Vallis Channel in Gale Crater. These crystals were found after Curiosity happened to drive over just like a white rock in a field of white rocks, and it crushed the rock with its tire and exposed these yellow crystals of elemental sulfur. This was the first time the mineral has ever been found in pure form on Mars. This picture right here in this rock, it's about 5 inches across from left to right. It was nicknamed Convict Lake after a location in California, Sierra Nevada. The sea of this sulfur stones in this area is just amazing. They don't really know how the scientists don't really know how it was created, but they are looking to answer and investigate more about Curiosity and how this elemental sulfur formed. And then Ingenuity. Originally a tech demo of just 5 flights in 30 days. After 72 flights and 3 years on the surface of Mars, we said goodnight to Ingenuity this past year after she sustained some rotor blade damage in a rough landing over some featureless terrain. She does continue to take daily pictures, and when Perseverance is in sight or communication, able to download those pictures from Ingenuity. And as many of you know, we are having a solar cycle maximum, and we've had amazing aurora here on Earth. We're also having awesome aurora on Mars, and it's a great time to be studying space weather at Mars. This image was captured by MAVEN's Solar Energetic Particle Instrument back in May, just on the dark side of Mars, getting just an amazing aurora from a solar flare. Okay, and Perseverance, of course, recently explored the Bright Angel region. And if you look down the center of this image, it looks much lighter than the areas around it. And that's why they've called it Bright Angel region. And this is a little bit of a cliffhanger. Minnie's going to share more about this with you, but we found a very special and potentially important rock called Cheava Falls, which is just at the center of this photograph to the right is kind of the region that rock was found in. Very exciting news about that rock that was found by Perseverance. Okay, so on to the missions that we are developing now. These images illustrate missions in work for exploring Mars. All of these missions have aspects of partnerships. Partnerships are very important to NASA, much of what you hear about on this panel, and plans and developments between NASA and international partners, also between NASA and industry partners. Partnerships really are the future of space exploration. It helps us achieve discoveries faster, promote innovation by expanding the communities that have access to space and Mars, and just including an environment where everyone can contribute. So what you see on the top right of this image is JAXA's Martian Moon Explorer, or MMX, and NASA contributed Magane, which is a neutron and gamma ray spectrometer payload on that mission. And MMX is planning to collect a sample from Mars moon Phobos and bring it back to Earth. Just below that, the rover that you see there is ESA's ExoMars Rosalind Franklin mission. And that'll drill into the Martian subsurface, investigate the soil, look for organic materials. It's going to drill about 2 meters down. NASA contributions to that mission include the mass spectrometer for MOMA, the MOMA instrument, lander descent engines, radioisotope heater units, as well as the launch vehicle. Up on the top left image, you'll see Escapade. This is a low-cost mission launching later this year. It's 2 identical spacecraft, and it's going to conduct heliophysics at Mars. And the data that we get from Escapade will also enhance a lot of the information and data that we're getting from MAVEN. So we'll really understand a lot more about both the Sun and Mars, by combining all the data that we get from Escapade and MAVEN. Okay, and in the middle of the screen, you'll see a sample tube, and for reference size, this is a sample tube here that I have. And this is to represent both the Mars Sample Return Program to return samples to Earth, as well as the Sample Receiving Project, which will recover and analyze the samples here on Earth in collaboration with scientists around the world. Both MSR and the Sample Receiving Project are collaborations with the European Space Agency, very important to us. And can't wait to hear more about that in a few minutes. And last, at the bottom of the slide, you'll see an illustration of astronauts, and this, of course, represents NASA's Moon to Mars initiative, which leverages partnerships with agencies and industry all over the world, and you'll hear a lot more about that from Patrick. All right, and this brings us to the future of Mars robotic exploration. Last year, I was at Arizona State University for the convention and introduced the Mars Exploration Program Future Plan, Exploring Mars Together. For a quick recap, the science priorities of that plan are to explore the potential for Martian life, discover dynamic Mars, and support human exploration of Mars. The plan initiatives include a range of mission types, from payload hosting to low-cost missions to medium-class missions, maybe such as the Mars Life Explorer, to create a balanced portfolio that ideally capitalizes on launch windows roughly every 2 years. We do also need to replenish our infrastructure, our aging infrastructure that is at Mars now. The last time NASA launched an orbiter was MAVEN back in 2013. So we need to make sure that we have good comm as well as good imaging. Shout out to HiRise on MRO. We also may want to add some new capabilities to the infrastructure, maybe surface weather monitoring. And then, of course, the last initiative, missed technology. We need technology to enable access to regions and surfaces we haven't explored before, and to enable low-cost missions so that those new missions don't have to take the burden of carrying infrastructure with them. And then the last initiative is togetherness. We need to be good stewards of Mars and explore as a community through partnerships. We've really, in the last year, made a significant amount of progress in work to define the implementation of this future plan. The first thing that happened earlier this year was commercial services studies were awarded to investigate how commercial services can be utilized for missions on Mars. So this is robotic missions. We did like 4 design reference missions in terms of payload hosting, payload delivery, communications, and imaging. So services that we could leverage with industry on Mars. We've also been planning for human science missions on the surface of Mars. NASA commissioned a National Academy study to identify high priority science objectives to be addressed by human explorers. Hope to have those findings in early 2026. Additionally, NASA's Planetary Protection Office, in conjunction with a whole bunch of other international and science communities, is working to establish policy for crewed missions to Mars. We've embarked on initiating a series of Mars surface science workshops. Those are similar to activities that we've done with the lunar community for lunar exploration. And these workshops will engage the community to understand what science we want to achieve in advance of humans arriving on Mars, as well as consideration for science humans will conduct once they are on the surface of Mars. And then lastly, this past March, the president's budget request included a generous bump to the Mars exploration program's technology development effort. If Congress agrees with this request and appropriates the increase, we'll have almost $40 million in 25 to spend on Mars technology development. This is pretty exciting for MEP and technology advancements. We've been preparing for the possibility by investigating directed projects at NASA centers and competing projects with industry and academia. So more to come once we receive an appropriation, fingers crossed for everything there. Okay, and I guess before we move on to talk about the Mars sample return, I just want to leave you with this image of robots and humans exploring Mars together for all humanity. Thank you.
Okay, great. Thank you so much, Tiffany. Nina, I guess it's your turn.
Great, thank you. Tiffany, if you could please help me with my slide deck. There, great. All right. Hey,
Make sure we're trying to catch your audio, so we want to make sure that we hear you really well.
okay, is this good?
Yeah, that's better. Yeah, thank you.
All right. Well, thanks very much, Alan, and I'm really, really thrilled to be here today to talk a little bit about Mars sample return. We've explored Mars for just about 6 decades at this point, and with increasingly sophisticated spacecraft, with flybys, orbiters, landers, rovers, with systematic exploration strategies. First it was follow the water, then following habitable environments, and now it's the consensus of the science community that the next big advance in Mars exploration, or in fact the next big advance in understanding broadly even the solar system, would come from returning samples from carefully selected sites on Mars. And so our exploration of Mars so far has taught us that the planet in its ancient past may have been Earth-like, perhaps, that it may have been warmer, it may have been wetter, there may have been a thicker atmosphere. And we believe that life originated on Earth possibly prior to around 3.5 billion years ago. And, there's hardly any kind of rock record left of that time on the Earth. Less than 1% of the Earth's surface is older than about 3.5 billion years. But in contrast, Mars, 50%, more than 50% of Mars's surface is about 3.5 billion years or older. And so Mars actually provides a potential record that Earth does not preserve anymore. And so what we're hoping to do by going to Mars is to understand what early planetary evolution was like, the geologic context, understanding that, and then trying to understand, how, when, and where life may have originated. And so that's sort of the context. Next slide, please. And so, the big science questions that we're trying to address then with sample return, basically we want to understand the global evolution of Mars first, the geologic context. How do rocky planets form and evolve? What's the history of the magnetic field? Because that may have played a role in the habitability of that planet. What's the timing of major events? You want to understand something about climate evolution on Mars, history of water on Mars. And then, of course, the big question about the potential development of life on early Mars. When was Mars ever inhabited? What do prebiotic, prebiological environments, habitable environments look like? And again, the how, when, and where did life first form? And we can't really fully grapple, with the question of understanding the how, when, and where of life without really understanding, as I said, the geologic context. And so it's all a system that we're trying to understand as a, habitable planet as a system. In recent years, of course, we've been able to send these incredible laboratories to the surface of Mars as part of rovers like Mars Curiosity and Perseverance now. And, the question is a legitimate question. Why do we want to bring these samples back? Why not actually just study those samples in situ, right? And so the next slide sort of addresses that point. Tiffany, if you could proceed. Yeah, so really there are limitations to what you can do, even with the really complex and incredible laboratories that we have on the rovers, the kinds of spatial resolution and the analytical precision that we need to be able to really address some of the highest priority science questions, such as being able to address the question of, was there evidence of ancient life, to do extremely precise analyses of the organics that we return potentially as part of these samples, to do really high precision isotope dating of these materials. You really need the kinds of instruments that, the size, mass, and power requirements of these are really kind of prohibited in terms of space flight. You have things like synchrotrons that are city blocks wide that you can't really put on spacecraft. There's complex sample preparation that's needed for some of these things, making thin sections, dissolving the samples to extract the organics, those kinds of things, incredibly hard to do on the surface of Mars by rovers and instruments there. And of course, once you bring them back to Earth, you've got the entire arsenal of laboratories here on Earth to apply to these. Carl Sagan famously said, extraordinary claims require extraordinary evidence. And really what that means is that important discoveries, and there's really nothing more important than really, determining whether there was evidence of past life on that planet. You're going to want to replicate those analyses, and you want to be able to do that in multiple labs with multiple investigators and analyzing these samples. And again, that's something that you can only really do back here on Earth. And then, of course, the careful curation of these samples is going to allow generations of scientists to analyze these samples in laboratories here on Earth with tools that we've not even developed at this point, and basically to answer questions that we've not even thought of at this point. And so this is going to be really important when we bring these samples back. Next slide. And so really, there's, three big aspects to bringing these samples back. We've got, the global and the national significance of this ambitious plan to bring back these rocks and soils. It's going to pave the way for humans to Mars. The impact and the inspiration, you can't underestimate that. The big question, are we alone in the universe? This is the nearest term opportunity to answer that question. And this will inspire future generations. And this is, of course, addressing high priority science, National Academies level science. And so, we'll learn not only about Mars, but also about habitable planets in our solar system, other habitable planets in our solar system and beyond. Next slide. So Mars sample return will really be groundbreaking in a number of ways. It's going to be the first launch from another planet. It's going to be the first in-orbit rendezvous at Mars. It's going to be the first round-trip mission to another planet. It'll be the first return of samples from another planet. And many of these capabilities really are going to be key also for ensuring safe round-trip travel for humans to Mars as well. And so I think this is going to be a path breaker in a lot of ways. Next slide. And it's already underway. So, Tiffany mentioned the fact that, Perseverance is out there in Jezero Crater collecting these rocks and soils and atmosphere samples already. And so this is already happening. For the last 3 years, we've been collecting these samples. So I'll tell you a little bit about what we're doing with that. Next slide. Just a reference here to show you in that red ellipse, this is where Mars 2020 or the Perseverance rover is. And this is basically just a global topography map of Mars shown here for reference, showing some of the other places where we've landed assets. And the next one here shows more close an image of Jezero Crater, and the black ellipse there shows the region that's been explored so far by Perseverance. Next slide. And this is basically, you can see sort of the inlet valley showing the flow of what we think was like a river-like feature into this crater. There may have been a lake at the bottom of this crater sometime. You see a delta-like feature on the upper left as well. This is some of the best preserved ancient lake and delta deposits on Mars. And really, the things that are within Jezero crater probably date back to something like 3.5 billion years. The areas around Jezero probably date back to even older, around 4 billion years. And so it's going to be a window into early planetary evolution that we've not really had a chance to explore before. And, records a diversity of habitable environments, including, rivers, deltas, as well as near surface groundwater, possibly hydrothermal environments, etc. Next slide. This is then just to show you kind of the white traverse here shows the path that Perseverance has taken so far. And in yellow are highlighted some of the science campaigns, the areas that have been explored by these science campaigns. The red crosses are places where we've already collected samples. And so we've got actually 28 sample tubes, and Tiffany showed that beautiful, sample tube there. So you can see it's about this, the rock core that's collected is about the size of a piece of chalk. And so we've collected 28 sample tubes so far. 10 of them have already been deposited on the crater floor as part of a depot, and that's a contingency sample. And then there's a number of samples that are now currently on board Perseverance. Next slide. And this actually, I love this image because it shows sort of the diversity of samples we've already collected. And so what you're doing here, you're looking at the top image of this sample tube. So it's about 1 centimeter across and shows an image of the top of the sample tube before the tube is sealed. And so you can see this is the order in which the samples were collected from left to right, top to bottom. And what you see here actually as those gold images with the X's, those are actually, there's 3 of those, and those are actually blanks, and they help us to sort of characterize the contamination. The rest of them are all various types of rocks, as well as regolith or soil samples that have been collected. So this is an incredible diversity, a diverse set of samples, including igneous and sedimentary rocks, regolith materials, and it's going to tell us an incredible amount about the kinds of questions that I talked about before. And I'll show you the last slide here. This is the sample that Tiffany mentioned, Cheava Falls, the very last one that we collected that we're really, really excited about. You can see on the image on the left-hand side that this rock is actually somewhat reddish colored, and there are these colorful spots on it called leopard spots that are somewhat lighter toned, and they have this sort of encircled by this dark rim. And it's really incredibly interesting because, we think that this could be showing us that this rock underwent some kind of oxidation reduction chemistry, redox chemistry, which is, on Earth, those kinds of chemistries really are driving some microbial activity. They're mediated by microbial activity. This rock is also rich in organics, and this is, shown by the Sherlock instrument on the rover. There's a really, really strong signal of organics in this rock. And the white stuff that you see on the sides of this red rock, that's sulfate. This is mineral that's deposited by water. And so there was water flowing through this rock. So this is a really incredibly interesting rock. You've got these 3 things that are telling us something really, really interesting about the possible potential biosignatures that may be present in this rock. And the interesting thing, of course, is that, we've studied this rock now on the surface of Mars with the instruments on the rover, but really to be able to definitively say whether we are seeing biosignatures, you need to bring this sample back. And so we're really super excited about the possibility of bringing something like this back soon. That's all I had.
Okay, great. Thank you so much, Mini. And now it's Patrick's turn to talk about how this all fits into kind of a wider spectrum of exploration. Go ahead.
Great. Thank you very much. I'm going to bring my charts up. Hopefully you guys can hear me. The chart is starting to think about sharing. There it goes. Okay. Thanks for inviting me to come talk. And I guess I'll give a slightly different perspective, a little bit higher level. Of course, my focus and our office's focus is primarily on the human exploration side of things, but that's not to say that we don't coordinate quite directly with our partners here and within NASA across the site center. A lot of our inputs are provided by our science mission directorate, and really that comes from this the blueprint objective that the agency rolled out about 2 years ago now. The pillars of exploration is what we're calling them. The three reasons that the why we explore: science, inspiration, national posture. And science is a big chunk of why we explore. And I like to say to everybody who whenever I talk this is there's an intentionality in the three pillars, because you think if one of these pillars doesn't exist, the stool falls over. So the three pillars has to kind of work together concurrently for this to really stand weight, right? And really the inspirations and the national posture and science objectives really comes decomposed into these different areas. And if you haven't got a chance to review these documents, I highly encourage you to look at both the Moon to Mars objective documents and also the developments of that Moon to Mars objective, which goes into a lot of detail about each of the objective, especially the science objective and how they relate to the decadal survey that's currently out. And all of these objectives and recurring tenets that are part of this objective sets really is how we are formulating and driving the architecture definition. And we have our architecture definition document that we publish now twice. And then the Rev B, the third iteration of that, will be coming out in the January-February timeframe. And that's how we are driving the architecture. We start with the why and the reason, the rationale for our exploration, and we drive out what the needs are from the architecture and really define what the segments and the components of those of the pieces of the architecture that need to be developed to satisfy those objectives. And that's how we engage both our internal workforce and our partners across the board, right? How we communicate very clearly our objective and how they can contribute. This is a key process in which the agency has developed to really drive out and ensure that not just internally within NASA, but with our partners, we are all coordinated with our effort. And as I mentioned a little bit, the architecture components, the objectives are very high level, and our job was as the strategy and architecture office is then decompose those objectives and determine how do we divvy them up into things that are digestible, essentially. So we have defined several segments of our exploration, starting with our human lunar return segments, which is already ongoing with Artemis 1 through the first few Artemis missions. Artemis 1 already flew, right? Artemis 2 is getting ready to fly here soon. And then, of course, we always have that forward-looking lens, right? What are the things that we are doing now that will help prepare us for the following segments? And one key area of discussion is that these segments are not sequential necessarily in nature. We don't finish one segment and move on to the next. There's likely going to be a lot of overlap, right? Because some things we're doing in this current segment is helping us prepare for the next segment. So, and all that gets linked together with our sub-architectures, which are the different components, different area of expertise and research that we're pulling together from across the agencies to help us understand the challenges, understand potential solutions. And then the elements themselves, the Moon and Mars Program Office has prime purview of those. And it's not just NASA elements anymore, right? We have partners, both international and domestically here, that are providing services, are providing elements as part of the overall integrated architecture, right? So the job for the strategy and architecture office is to make sure that we understand and evaluate all the different options, push and pull the use cases and functions that we define, so that we have the right pieces and right puzzle pieces at the right place at the right time. And that is the key part for this integrated effort. For Mars specifically, obviously, as you saw from the segments, the human to Mars segment is a few pieces away, right? The current focus is the lunar. For Mars, the current focus of the Mars architecture team is really helping the agency define decision road mapping. We've been studying Mars architecture for well over 50 years now. Lots of different studies, lots of different ways that we can obviously send humans to Mars. But at some point, we have to come together and make strategic decisions on some of these key things. That way, we can start honing down on sort of the strategy on how we implement human exploration. And a lot of that is going to be driven by different pieces of the information that we're gathering. So as part of our internal effort, we are laying out this decision road mapping process, right? What things are dependent on other things? What is the right order to make certain decisions? Last year we talked quite extensively about the who, what, when, where, why, and how question, right? To define an architecture, you have to answer those questions. Well, depending on the order in which you answer those questions, your architecture could look very different. So understanding the dependencies of different decisions, understanding how, what the proper order is to make some of those decisions is key. And that is currently part of our detailed work to try to understand. And of course, that work is concurrent with defining some of the key decisions now. Last year at the Moon Mars workshop, and as part of our architecture definition document and white papers, we spelled out what we thought was the initial first 7 decisions. Kind of call back to the first 7 astronaut corps. We have 7 decisions that are very important. I think we are driving decisions for Mars architecture. And the white paper goes into a lot more details about each one and the dependencies associated with each one of those. And we're working them very, very hard right now to make sure that the agency comes together to provide resources and provide data to help us inform the architecture and to make the right strategic decisions for each of these decisions. And of course, as both Tiffany and said, that science really drives it, right? Why we go, one of the 3 pillars of exploration is science. So science is driving a lot of these decision making. This is why, Mars science priority is one of the key driving decisions that we identified last year. And the community is hard at work at this. The National Academy spun up a study to really help drive out what are the key things that are needed. That human exploration need to focus on here in the initial segments, and they're having, I think, some public hearing actually this week talking about those very important things. We eagerly await the results of that so that we can help us prioritize our internally at what the science priorities are, because there are numerous, and we understand that it's impractical for us to tackle all of them at the same time with the same mission. So there is a natural order to them. So that's one of the key things we have to drive out is what are the things that we want to understand, and there's so much we want to understand. So that's sort of my opening remarks. Again, there's a lot of information on our architecture website. I think there's 28 now white papers associated with the architecture that has been published. Again, the architecture definition document, Rev A is out in public now. The Rev B version will likely come out in January timeframe. And we are always open for engagement. We do hold a public workshop both for our domestic partners and international partners in the February timeframe. And there's some more information in the architecture webpage that talks about that. We invite both industry and academia and researchers to come and give us feedback on the architecture. And that's a great way to stay engaged. And one last, parting thought, as I think Tiffany mentioned, partnership is everything. NASA values our partners across the board. And we understand that this is not something that NASA can really go at it alone. We need partners to help us solve the very, very challenging problems that is sending humans to Mars and back. And that's all I have. Thank you.
Okay, great. Thank you so much, Patrick. I'm sure we could be here for another hour talking about your questions. I had a couple of questions that I just wanted to throw out. One was relating to the status of the sample return mission. I believe that NASA is taking another look at that mission because of budgetary constraints and trying to figure out the best way to put it together. And you've turned to commercial and also agency partners to kind of look at what the possible options are. I understand that that process is continuing and that the proposals might be coming in the fall, and you'd be taking a look at that and trying to put something together that might take you into the winter or next year. But there are already people here at the Mars Society are already talking about potential ways to do this. Last night we heard about a concept for a sample return mission that could make use of SpaceX's Starship, a Rocket Lab Electron upper stage, Tesla Cybertrucks, ATVs, and Optimus robots. There was also an option for actually sending people in a Starship to do the lab work on Mars. And so I'm guessing you're not going to be able to comment in detail about those kinds of proposals, but I wonder whether you could talk more generally about how far out of the box NASA would be willing to go when it comes to out of the box thinking.
Wow, Cybertruck, that sounds awesome. I haven't heard that one before. I would like to get a copy of that paper because that sounds intriguing. So I'll just kind of talk a little bit about the timeline again. In July, there were, I believe, 7 studies awarded to different companies to study what we could do to make the architecture more efficient in terms of risk, in terms of cost, and in terms of schedule, getting the samples back sooner. I think they were 90-day studies. We will expect to see those back, like you said, in the fall, and we'll kind of assess the timeline from there, depending on what we see in the reports. But I think we're looking, we want something that is also reduced risk, but reduced price. And as Minnie showed in her presentation, we've never done a lot of this before. We've never launched off of another planet before. We've never brought samples back from another planet before. So, I mean, I think there has to be some ingenuity or innovation in some of the solutions. So I think the trade space is broad. And then also I want to mention that it is not just the 7 industry studies, but we've also got, I think, 3 other studies from centers and FFRDCs that are in parallel to that. I'm not sure exactly on the timeline, but that's also kind of why we probably won't have a solid answer on a revised or a forward architecture for a little while still. Minnie, did you want to add anything to that?
No, I mean, I love the Cybertruck idea. I'd love to see more about that too. But just thinking about the fact that going there and doing the kinds of analyses, I think again the kinds of things that you can. I think that would be really cool and really great. But probably for the first time around, it would be great to just bring the samples back, just given the kinds of advantages that I mentioned in my talk.
Okay, great. Tiffany, I think I saw what you did there with that reference to ingenuity. So I'll look forward to seeing the helicopters in the plan. The only other question I had to do with the presentation we just saw here at the conference about terraforming. And there was this science paper that came out this week about putting iron or aluminum nanoparticles into the Martian atmosphere to warm up the atmosphere and thaw out the ice. I know that is a way long term. You've got to talk about the near term missions first. But is there anyone who's thinking about that, whether terraforming is going to be an option? Do you have any response to the publication of that research?
I'm happy to offer a response unless someone on the panel, maybe Minnie or Patrick, would you like to start? I do think it's pretty far out. I'm a big planetary protection advocate, and I know that Minnie does a lot with planetary protection as well. I think we need to make sure that we explore responsibly and that we protect Mars and we protect the secrets of our universe. But we also do need to send humans because humans can do the best, science. They make the most progress. But I think there's a handful of things that we need to learn first. Maybe subsurface transport models, surface transport models, increasing the fidelity that we have of our models today, to learn about things before we start melting the ice for use. But hopefully it's in the future.
Yeah, I mean, I would just add that, yes, I mean, I think, this certainly in the realm of the far distant future, and we're talking something like, maybe a century or two into the future. And ahead of that, there's a lot of work to be done. And I think there's a lot that we need to learn about Mars before we start doing those kinds of things. And so, yeah, it's one step at a time.
Okay, I've got a whole list of questions here, but I'm sure people in the audience do too. So I want to give them a chance. And so people will be passing a microphone around.
Hi, thank you all for joining us. So my question is specifically about the location of the sample returns and something one of you mentioned earlier. So the Curiosity rover at Gale Crater discovered sulfur rocks recently, and I believe about a decade ago it also discovered a liquid brine, a high level of salinity, that there being possible liquid water being able to kind of subsist on the surface. And Gale Crater is also at a near equatorial latitude, meaning it can be very suitable for human settlement, higher temperatures and whatnot. So all of that combined makes me think that Gale Crater would be very ideally suited for a sample return. But the current plan is to return samples from Jezero Crater. So I'm wondering what you all think Jezero Crater offers as opposed to Gale Crater, if it's better or not. And if you do think, and if you do agree with me that Gale Crater would be a better location to return samples from due to the reasons I described, if you could elaborate as to why. Thank you.
Maybe I can take that one. So, there was an actual workshop and a lot of sort of science community discussion about where to go to collect the samples and bring them back. And this was extensively discussed in the science community. And the agreement was that Jezero Crater, the consensus of the community was that Jezero Crater offered the diversity of habitable environments and the kinds of water rich environments that were the most promising in terms of really being able to assess the question of whether there was evidence of ancient life sometime, that we can find, whether we can find evidence of ancient life. And so, and we're already seeing that in the collection that we've got so far, and particularly of this last sample that I showed you. I mean, that's an incredibly intriguing sample, and probably the one that I'm, personally, I've been incredibly sort of skeptical of any kinds of evidence that we've seen of possible biogenicity on Mars. But this is a really, really interesting sample. And so, our plan is at the current time to bring back the samples. We're collecting the samples at Jezero. We're doing all, the due diligence in terms of the geologic mapping and the context, understanding the context of these materials. And we've got that incredible diversity of samples that we really need to address the big questions. And so I think, we are going to be hopefully bringing back those samples from Jezero Crater. And I not to say that there's nothing, there's not interesting materials at Gale. Certainly there are. And hopefully, there'll be future things that'll happen that could, that could enable sample return from other places on Mars.
Okay.
Usually share from all technology and ideas, but in this case, they've had successful regolith return missions from the moon and are planning one in 2030 from Mars. What lessons can we learn that will speed up our sample missions and make them more cost affordable?
I want to make sure I heard the question correctly. Based on activities that we're doing on the moon, what lessons learned can we learn for future sample missions? Is that what I heard?
Is more, what lessons can we learn from China's effort, their return of samples from the moon and their plans to return samples from Mars around 2030 or so?
Vinny, do you have anything there?
Well, I mean, I think the Chinese effort, we don't have a lot of details exactly of their, certainly not of them about their Mars plans. I think there's some very broad sort of informational things that we have about it, but nothing in detail. So it's hard to know, what the lessons learned might be from that. Certainly, I think, it's incredible that they were able to bring back the samples from the far side of the moon from within South Pole Lake and Basin. I think those samples are certainly exciting, and I'm hoping that with the soon to be kind of the Artemis missions and other activities at the moon, we'll be able to return some of those kinds of materials as well. But yes, I mean, I think it's a little hard to say exactly what those lessons learned could be, just given the somewhat paucity of information that we have. Tiffany, did you want to add anything to that?
I do want to add. Well, we we don't know details or specifics about what the Chinese are doing on the moon in terms of bringing back samples. We have OSIRIS-REx, and we will learn a lot, and we have learned a lot already about bringing samples back from Bennu. What's the Osiris from? Anyway, the OSIRIS-REx mission, bringing those samples back. So in terms of opening the container, time inside of the clean room. It's not exactly the same. There's still a lot more that we have to do for Mars sample return, since Mars is an Earth return restricted location from a planetary protection perspective. And the moon and the OREX mission are not from Earth return restricted places, but there is still a lot in terms of CONOPS, recovery, sample analysis, and preparation that we are learning there.
Okay, next question.
Hello, Chris Temby with the Agnostic Life Mining Association. Hi, guys. So I have a couple thoughts. My first question is, how likely is it that there's going to be some sort of Mars version of CLIPS? And then also, I think, Tiffany, you mentioned, I think I heard you right, that there's possible appropriations for $40 million to do some technology development and innovation. And it seems to me like, well, the first question about that is what sort of technologies are being prioritized? And also it seems to me like the architecture should, I guess, inform what sort of technology should be developed, but it also seems like the architecture is in flux. So, I mean, I'm specifically thinking about ISRU infrastructure and technologies. But so is there some sort of chicken and the egg thing where it's like we need to invest in technologies for the architecture, but the architecture isn't in place yet? So yeah, those are my thoughts. Thanks.
Okay, let me clarify a couple of things. There's actually 2 commercial studies going on right now. There's commercial studies for MSR, and then there are commercial studies that are looking at services for future robotic missions. And then the technology budget is specific to future robotic that is not MSR. So I think your question was asking about how the technologies could feed the MSR studies, and those are separate. The commercial studies that we're doing for MSR will inform that architecture, and they are bringing the information about the technologies they need for those architectures. So that's kind of all bundled together. Whereas on the robotic exploration end, we've got commercial services, which is, how are we going to just kind of maintain Mars altogether for robotic exploration, optics, payload hosting, payload delivery. And I have heard a lot of people kind of talk about, like a Mars CLIPS program. And right now these studies are investigating whether that's feasible, whether there's enough interest at the surface of Mars. It certainly seems like there's a lot more interest than there ever has been in the past. But is there as much as there is at the moon is what we're doing the studies for. And then regarding the technology and the $40 million upper, hopefully, fingers crossed, that was the recommendation from the president's budget request. But of course, we have to have an appropriation from Congress before that becomes real. And we are preparing for that. But again, that is technology for robotic missions, such as drilling or entry, descent, landing. So certainly not at the level that MSR is doing, not in terms of size and scale at this point in time.
you talked a lot about Jezero Crater in this presentation. I was curious about what other sites of interest there are for the sample return outside of Jezero Crater, potentially future sample return missions.
Well, so, a few years ago, there was a discussion of, possibly something like 5 or 6 different sites that were proposed as potential, for interesting for science-wise to bring back samples. They included some of the sites that we've explored before, with the Spirit and Opportunity rovers, for example, and also, of course, Gale Crater. So, I mean, I think there are a lot of places actually on Mars that could potentially be very interesting to go to sometime in the future. There's, of course, the equatorial regions are easier to get to, but then, there's a lot of interest, of course, in the polar regions, the ice caps there, and being able to sample some of the volatile materials there. So that there's a lot of really interesting science possibilities there. But for the time being, and realistically for the future, for return of materials, hopefully in the 2030s, Jezero Crater is the place where we are headed if that's, sample return moves forward.
How much more time do we have left? So I think this should be the last question.
Thanks for such an inspiring panel. So I've got one quick question. Based on the outcomes of the Ingenuity mission, what do you think is the future of potentially having helicopters for future exploration on Mars?
Did you catch that? The future of helicopter exploration on Mars.
I think it's super exciting, actually. It opens up a whole new realm of, exploration possibilities, being able to access areas and topographies on Mars that we really couldn't even imagine before. So, I mean, I think it's super exciting, and it opens up lots of possibilities. I don't know, Tiffany and Patrick, if you wanted to add anything.
Patrick, I think how humans are going to use them is probably the most interesting.
Yeah, I think it's a great demonstration of how innovations can really expand our sort of even thought process of how we could explore, right? I think it adds, I think it has the potential to add quite a lot of possibility to how we operate and how we explore, right? It really extends the range, and I'm just gonna throw my last chart back up because if you notice what the astronaut is potentially trying to do, is this is sort of of course, this is not official. This is just sort of a artist concept of it. But yeah, I think part of this and how the exploration program, the Mars exploration program is doing is really helping us define what is possible and what things we even think about, what things that we haven't dreamed of, right? One of our colleague who've been working for Mars for a while like to say, we know more about Mars today than we ever did when we first stepped foot on the moon, right? And it's because of the robots, right? We know so much about it, but there's also obviously so much more we don't know, right? And when they landed on the moon, there was so much uncertainty even about the regolith. Is the lander going to just sink into the sand? They don't really know. They had some educated guesses. But because through the Mars Exploration Program, we know quite a lot, so we can do a lot of these plans, and we're going to learn so much more in the next coming years with going back to the moon, learning how we operate, learning how the complexity of integrating multiple systems together to field a single campaign. All those lessons is going to be applied for, and the samples that we potentially return can feed forward to how we plan these missions. So all that really comes together as an integrated thing, right? And I think that's really important for us because without it, it's very challenging to do all these plannings.
Okay, great. I wanted to give each of the panelists a final round to give your closing remarks, and I guess we'll go in the same order that we started with. If Tiffany, if you wanted to go first.
I have probably said a lot of this before, and Alan, I think you said some of it as well. Very exciting time for Mars. There's more interest in Mars now than ever before. like Patrick said, we know more about Mars than we knew about the moon, but there's so much more to learn. And it's so exciting every day. You know, it was within like 6 weeks when Curiosity found the sulfur and Perseverance found Chayava Falls. You know, it's so exciting to see what comes next. What can we learn? What can we discover? And it's not just about Mars, but how it impacts our Earth and the history of the universe, the secrets of life. And I think there's a lot of things that we want to do before we put humans on the surface, but having humans on the surface is just, you know, the most exciting thing to do. Go on some awesome hikes. I mean, but field work, that's what we call that, field work. So I'm really looking forward to the future of everything and doing it together with robots, with people from all over the world, all different types of organizations, and you know, diversity for everything.
Okay, Minnie?
So I'm a geologist by training, and, you know, I am just incredibly excited because to me, you know, I'm vicariously exploring Mars as a geologist right now with the kinds of assets that we already have. But really, I mean, I think the powerful thing, the thing that's really going to transform our understanding of not just Mars, but just more broadly how we actually get to form habitable worlds in our solar system and beyond our solar system, I think that's going to come from really studying these samples at the atomic level here on Earth, and the kinds of samples that we're seeing now, Chayava Falls and others. I mean, I think the definitive answers about whether there's that evidence of ancient life, that's going to come from studying those rocks here on Mars. So, and I'm seeing that, you know, just a decade ahead or a little more than a decade ahead. And it's always seemed that way for me ever since I was a graduate student. Mars sample return was 10 years into the future. But this is, you know, it's starting to actually feel real because we're collecting those rocks right now. I think that's so super exciting. So, yeah.
Okay, and Patrick, you have the last word.
Oh boy. Yeah, I'll just echo what everybody said, right? I think the thing that really excites me is this concerted effort across the NASA to really engage with our partners, right, both domestically and internationally, and learning how we can work together to solve these really, really difficult and challenging problems, right? I think of Star Trek in that fictional universe when the whole world comes together and joins and do exploration together. My dream is that we're headed in that direction, and how we learning on these cooperations and corporate efforts with common goals. And I think big part of that is really laying out the objective of what we're trying to do. And we've done that. Our partners are thinking about how they want to prioritize their objectives and maybe potentially sharing those with us. And I think that's a key part, right? Making sure that our objectives all align so that we can all come together and explore together, right? And make sure that we complement each other's weakness, or complement each other's strengths and weaknesses. And so that to me is the most exciting things. And then I would say that, you know, as Tiffany said, you know, there's more excitement and more engagement that we've had than for a very long time, and we love seeing it. And this is how we can, you know, the inspirational part of that 3 pillars, right? We have to be able to inspire the next generation so that they can come behind us and really, you know, put us to shame in terms of their innovation and ingenuity. So.
Okay, thank you so much to our panelists and to the audience. Let's give everybody a round of applause. Very good.
Right. Thank you.
Thank you.
Thanks.
Thank you.
Do you want to? Okay. No, we're taking a break there.
Oh, of course.
Yeah. So guys, we're going to take I think we have in the schedule a 15-minute break right now. So we'll go ahead and do that, and then we'll come back and have the next speaker. Thank you very much. Okay. That was great. That was great. Yeah. thought that went really, really well. Yeah. I mean, you have to really trust it. Yeah. Oh, we're gonna get all the Kens and Tony and Roberts. Make sure we
Yeah. Right, response. Right. Right, right.
Yeah.
Right. Oh, I was just asking.
I'm guessing that's color.
Got a USB.
Right.
I got you.
How are you, by the way? It's good to see you. Awesome. That one's not coming up for some reason. Oh, I'm sorry. Okay.
I also have it on USB.
Next. Close the other one. So I'll do it the way we're going to do it, which is the other thing though is we share it on the Google Meet too. So let me just do that. Yeah, that should work. Hold on, we don't have focus there right now.
Perfect. You can see my notes. Thank you.
Awesome. Yeah.
Well, actually, yeah. Yeah, we do all the time.
So sort of action.
Yeah.
Oh, there we go. There we go. Everything I coordinate with.
Oh.
Curiosity. Okay. I'll what's up? I'll sort the day where
Okay.
I don't need to take yours.
I got just.
Oh, here, I'll roll by it. You hang on to that one. I'll take your
That's true.
Okay. I will text Molly. She's making it. Yeah, she's, yes. Yeah. Okay.
Hi, good.
Hi, I'm Ashley. I'm going to be doing your introduction. I just wanted to make sure that
I'm writing about
okay, there we go. Easy to remember.
Yeah,
There's not.
exactly. Yeah.
No mention of words. I think I got that message. Fair. So we want to abide by the rules.
Like Martian blueberries.
So much stuff.
Yeah.
Okay, I'm from local the area. It's
Are yours? No, I this is the first time. No, I presented to our society. Yeah, two or three it's the same. And I'm actually funny thing is, so us going over to the launch host, there was a camera. So the difference between rent and is now deciding back.
Right. That's right.
Yeah.
That's
Yeah. So you did use it.
Yeah.
And you moved out there for a while.
I can do all of
If you want to move back to Gallery, so anywhere else.
There's a lot of it.
Yeah. SNS is That's why I was in Mars Society.
I'd like to welcome everybody back to their seats. We're going to go ahead and get started. Jim is wheeling and dealing over there at the swag table. Welcome, everybody. Please take your seats. All right, well, let's go ahead and get started. Next up, we have Max Fagan, who is an aerospace engineer with a background in trajectory optimization and space-based resources. He completed his undergrad in astrophysics and electromechanical engineering and continued his graduate work in aeronautics and astronautics at Purdue, with a focus on Mars entry descent and landing trajectory optimization. Since then, Max has worked at NASA Ames, SpaceX, and Made in Space. Max, this is really cool, has been a Mars Society member since he was 10 years old. He also served as crew astronomer for MDRS 99 and commander for Crew 186. He currently lives in Seattle working as a piloting engineer on the development of NASA's Artemis lander. Everybody welcome Max.
All right. Well, thank you very much, everyone. It's wonderful to be back here. This is one of my favorite venues for speaking at because it's a subject and an audience that I very much relate to. As you said, I have been a member of the Mars Society since I was 10. And this is stepping out a little bit from my comfort zone. I am an aeronautical engineer. I am a little more uncomfortable in the realms of people engineering, but this talk is based on a concept that I encountered, and I'm indebted to Bruce Garrison and Rick Tumlinson for kind of putting the idea together. But I have found this to be a useful framework for kind of envisioning the various ways that the different groups within the aerospace community picture the future of our solar system. And this presentation is my attempt to kind of put this together into a common synthesis of the various ways that we portray the future of our solar system into something that all of us can kind of relate to. I doubt you will see a lot of new material that you haven't seen here before, concepts or ideas that you haven't heard of before, but hopefully the framework will be insightful and provide you with a way to visualize the way we see the next couple centuries going down in our solar system. So let's get started. So the questions for today that I want us to think about are, what are the next few centuries of our solar system going to look like? We have different perspectives depending on who you talk to. Where are we going to live? Where in the solar system is going to be the best place for us to inhabit? And where are our resources going to come from? And of equal importance, what are we going to do? It's not enough just to say we're going to put people in space. If those people are going to live and work in space, they have to be doing something, something productive, something justifying us being in space. And what exactly is that activity going to really be? Let's set a couple of ground rules to keep this speculation as grounded as we possibly can. First of all, let's kind of start with the basic assumption that humans are still going to need the same stuff. We're going to need air, food, water, volume, a mild temperature radiation environment, community, places and opportunities to interact with our fellow humans. And let's also assume that the kind of industries that we build are still going to need the same kind of stuff: general resources, metallics, organics, water, all of the same things that we recognize in an industry today here on Earth. What we'll be doing with that might be a little different, but the inputs are still presumably going to be similar. Second, we have to assume no new physics. I know we can envision very grand futures if we are allowed to assume out there physics like warp travel or matter transmutation. But to keep this exercise as grounded as possible, we're going to have to assume that no new physics. So travel will get faster and more efficient. We'll presumably have practical modes of interplanetary travel, but no moving faster than light and no reversing entropy. Third, I'm assuming that basic economics is not going to change. Now, what we choose to value may change, but what we are incentivized, how we are incentivized to pursue what we value is probably not going to change. There is still going to be a premium on efficiency, although how we measure our efficiency might change. It might be in terms of energy efficiency if we're in an energy efficiency limited environment, or it might be in terms of delta V or time. There's always a finite amount of time. So we're always incentivized to do things in the most efficient way possible. Fourth, new miraculous robots or AI. I know living through the past couple of years has gotten a lot of people quite hyped up for the idea that humans are about to become obsolete. I don't think that's true. I think that automation and robotics are going to continue doing as they have for the past century. They are going to make human lives more efficient. They're going to automate tasks, not jobs, but there is still going to be a need to have humans present wherever the work is being done. And fifth, no aliens. Sorry if your future solar system envisions the presence of aliens coming to visit us, but unfortunately for the purposes of this exercise, we're going to have to assume that it's just us. Now, again, I'm an aeronautical engineer. I'm not a computer scientist. I'm not a roboticist. I'm not a sociologist. I am in no position to say that all of these are good assumptions. All I'm asking us to assume for this talk is that these are necessary assumptions in order to keep this kind of far out speculation grounded. If you want to put together future solar systems that challenge one of these assumptions, don't let me stop you. I am not insisting these are the right assumptions, only that they are necessary assumptions for this level of speculation to have some semblance of reality. So the central assumptions that we'll use to answer these questions are, these are the two I think are the most important ones to make, is what do humans inhabit on Earth? Because I believe the same principles are going to kind of guide us where we inhabit in the solar system. And it comes down to access and need. Humans live in locations that they can gain access to first. We weren't able to live we weren't able to live in the Americas until we gained access to the Americas via the land bridge from Asia. We weren't able to live in Antarctica until we developed the technical capabilities to access Antarctica. And we don't move to these locations until we identify a definite need. That need may be something as simple as a desire to explore it. It may be something as complicated as agricultural opportunities. I'm not going to try to get into really deep details about why humans expand, explore, and move into new locations, only to say that it usually doesn't happen until we've gained means to access that location and identified a definite need to move to that location. So the central thesis of this talk then comes down to answering those questions within the realm of these four philosophies. And again, I'm very indebted to Bruce Grierson and Rick Tumlinson for coming up with this framing. So I am not the originator of this framing. I just think it is a very useful way to try to answer these questions. The point is to make the distinctions clear, but I really want to emphasize there is overlap to these. These are not Hogwarts houses. I am not going to insist that one has to pick a camp and then only adopt the mindset of that camp. You can contain multitudes. I don't want to leave the impression coming away from this talk that one is one of these four, only that these four provide a useful framing for understanding the different perspectives on the answer to the previous questions about where humans will live and work in space and what we will do. So the four philosophies that we're going to go into a little more detail on are von Braunians after Wernher von Braun, the O'Neillians after Gerard O'Neill, the Zubranites after, Robert Zubrin. I don't need to explain that. I don't need to explain that to this audience. And the Saganites after Carl Sagan. So let's go into a little bit about what each one of these philosophies kind of pictures as the future of the solar system and how they answer the main questions that we're planning to ask. The von Braunians might be identified as kind of one of the oldest philosophies, and it's really identified with the philosophy of space as an expansion of national power. If you've ever met someone who has strong opinions on the difference between space situational awareness and space domain awareness, or someone who uses the verbiage of space as the ultimate high ground, or someone who talks about the implications of great power conflicts in space. You're probably talking to someone who is picturing the future of the solar system from the von Braunian perspective. We tend to see the future of the solar system and our expansion into the solar system as being driven out of a need to pursue national interests in space. We can credit a lot of great accomplishments in space with this. The Apollo program, while obviously it brought back incredible wonders of science, not for the geopolitical need for the United States to demonstrate soft power and technological prowess in the Cold War. The Apollo program is an example of this philosophy in action, in my opinion. So the idea of why we are in space in a von Braunian philosophy is because it's necessary to control space to further our national interests for great powers here on Earth. Whether or not you see this as the right or the wrong way to envision space, I am not intending to tell you it is right or wrong. This is not a prescriptive talk. I only want to outline this as one of the four primary philosophies that is kind of posturing our picture of what the future solar system is going to look like. From a fictional perspective, For All Mankind is a really good fictional portrayal of a future that I think is built on this idea as primarily a national government-driven space program. For the O'Neillians and the philosophy of Gerard O'Neill, this is kind of more embodied by members of the National Space Society, although obviously there are overlaps with the other three philosophies. And the idea is, if you've ever heard the term planetary chauvinist, The idea is that, yes, humans evolved on Earth. Earth is a fantastic place to bootstrap a civilization, and Mars is an excellent place to bootstrap a civilization as well. But even if Mars were made to be as vibrant, as populated, and as productive as Earth is, congratulations, you've only doubled the carrying capacity of the solar system. If you want to talk about trillions of human beings, then we need to look at places where we're really volume unconstrained. And Gerard O'Neill's idea for that was, well, let's look at space habitats. There are only a few planets worth of habitable volume in the inner solar system, maybe more if you include the moon, if you include terraforming the moons of Jupiter and Jupiter and Saturn. But there is a nearly indefinite, trillions of times more volume available just in cislunar space alone, if we allow ourselves access to the resources to build these massive rotating habitats. So that was O'Neill's primary contribution, is the idea that if we want to maximize the carrying capacity of the solar system and really enable humanity to become as much as it possibly can be within the resources constraints of the solar system, his argument was we need to look beyond the planets and start thinking about interplanetary and cislunar habitats like the kind that were portrayed in The High Frontier. It definitely is a 70s, 80s philosophy that kind of grew out of the concerns about overpopulation and pollution that were really prevalent in those eras. But I do still think there are merits to the idea of, if we really want to be human maximalists, do we want to look beyond planets and look to places that really maximize the amount of volume that humanity could really access? The philosophy, I obviously don't need to explain to this audience, but yeah, it's the idea that the best place for humanity to expand, at least in the medium term, is to Mars as an independent branch of human civilization, terraformed to support the same kind of population, civilization, and technical level as we're capable of supporting here on Earth. I can think of really no more image or visualization that more embodies what we think of as Zubernites than the idea of terraforming Mars, turning it into a second home for humanity, and really maximizing its potential. This is really what embodies the Zuberan philosophy. Is we are human maximalists. We believe that the solar system is there for us to expand into. And in order to maximize the human potential of the solar system, we need to create these new worlds. We need to bring Mars to life, that kind of thing. I obviously don't need to, again, explain that to this audience, but that's kind of the embodiment of the Zuberan philosophy in contrast to the other two philosophies, is the focus on Mars as the next best place for humanity to start our expansion. Fourth and lastly is the Saganites. This is a bit of an outlier because its primary focus isn't so much on what humans do in space from an industrial and civilization point of view. The focus is on what space can do for science. What space can, we want to go to space because space has the answers to the big questions. The questions of, are we alone in the universe? Where did life originally come from? Are there other places in the solar system that can support life? These kind of questions are the kind of questions that we really need humans in space to answer. And the primary focus of the Saganite philosophy is, let's send humans to space in order to answer these questions. Now, Carl Sagan was not just an advocate for space for science's sake. Carl Sagan absolutely advocated for expansion of humanity into the solar system for anthropocentric reasons as well. But I would argue that there is still a big motivation among many people that space is for science. And the Saganism philosophy is kind of the embodiment of that. So those are kind of the four philosophies that I want to focus this talk on. Let's try to put a couple of numbers to this. I am, again, an engineer first and foremost, and my background is really in astrodynamics and trajectory optimization. So I tend to think of human expansion into the solar system from the perspective of delta V maps and solar system trajectories. So what we've got here we go. This is a solar system access map. So this is a series of delta V calculations showing the minimum possible delta V transport from one location. So if you look here on the left side, these are your points of origin, the various places that humans might start at or that necessary resources might start at. And then along the top here are the various locations we might want to transport all of those people, technology, resources, materials, whatever it is we want to transport. And then what I've done here is I've just identified what is the minimum delta V window. This allows aerobraking to take place wherever aerobraking is an option. So that's why it's not going to be perfectly symmetrical. And then we've just color coded it by the, we've color-coded it by the magnitude of the total delta V in order to go from one place to another. So we can think of this as a proxy for how difficult is it to move from one place to another in a solar system. We can think of this as a map of the answer to the first question of when do we gain access to various places in the solar system. Now, a couple of caveats to this. Again, this is just the minimum delta V. It is not a plot of the average delta V. And this is assuming that it is an impulsive transfer. So an impulsive departure and an impulsive arrival. This doesn't account for the option of having like a torched ship or an antimatter or fusion propulsion, something that could get to a location in the solar system much more directly rather than taking the slow route. But we can already see, even under these assumptions, that we have certain kind of islands of accessibility. If you see a lump of green somewhere, kind of an island of green poking up above the sea of yellow-red. What that is representing is kind of you can think of it as basically an island chain, a series of places where it is really easy to access each other, places where it is easy to travel between those locations, whereas being relatively isolated from the surrounding areas. And if we overlay the various philosophies on here, we can already see a pattern emerging about where they tend to focus. Von Braunians, now, Werner von Braun did write the Mars project. I don't want to accuse him of being Earth focused, but the philosophy of his as space as an expression of national interest tends to primarily be focused on Earth. We tend to talk about what assets can we station in the various orbits around Earth in order to ensure control of space, in order to control effective monitoring of the Earth. In order to control effective access to Earth. We tend to be focused mostly on the Earth-Moon system and where we can move about in there. So that this little green island here of Earth-Moon access tends to be where the von Braunians tend to focus. The O'Neillians have a similar focus in the cislunar system, but recently, sorry, I say recently, I mean in the last 20 years, the expansion has also included the near-Earth asteroids. Now, Gerard O'Neill, when he originally came up with his math, we weren't aware of the abundance of resources presented by the near-Earth asteroids or in the main asteroid belt. The resource abundance of asteroids was still a hypothetical point in the 70s and 80s. Since then, the National Space Society and the people who have continued O'Neill's legacy have kind of come to understand that if we want to make that trillions of humans in space habitats and cislunar space vision work, it's not enough just to access the resources of the moon. Bringing in the resources of the asteroids is also important. So the O'Neillians tend to focus on these two green regions where we provide access to cislunar space and the near-Earth asteroids. Zubernites take a bigger view, encompassing the three-part trade that could take place between both the Earth, the asteroids, and Mars. Again, the idea being that Earth, as a high-tech civilization, is always going to be able to export the high-tech that requires a planet-sized infrastructure in order to produce, whereas the asteroids, as some of the most easily accessible resources in the solar system, because they don't require landing or taking off from a planet, are probably the best place to gain access to just raw material, silicon, water ice, iron, even just regolith for radiation shielding. That kind of thing is abundantly available in the asteroids. So the asteroids provide those raw materials, Earth provides the high technology manufacturing stuff, whereas Mars is still the best source of organics in the inner solar system. So Zubernites focus on all three of these islands: the cislunar island, the Martian island, and the island provided by the resources of the asteroids, to kind of build this three-part solar system trade. Saganites don't really fit on this map very well because, again, they're not really focused on access so much as what interesting science can be done all throughout the solar system. So if the question of, well, it's actually really, really hard to get to Jupiter doesn't really faze a Saganite, because the question is, it doesn't matter. There is science to be done to Jupiter. We should get there as soon as we can. So Saganite doesn't really fit very well on this map, unfortunately, but I wanted to put them on there anyway. From a solar system resource map, so this was kind of answering the question of how do we access various locations, but that's not enough to just say access locations. We also want to answer the question of what is available where. This is a very, very rough map of the various materials that are available in different locations on the Earth, Moon, Mars, and asteroids. Now, again, Earth is not a homogeneous body, neither is Mars, and neither are the asteroids. None of these bodies can be well approximated as a single monolithic composition. So I have tried to be fair in indicating really what resources are accessible in various locations. And the primary distinction is between the O'Neillians and the Zubernites. The O'Neillians, again, tend to focus on the resources available on the moon, with a high focus on the wide availability of water ice at the lunar South Pole, as well as the availability of manufacturing materials like iron, silicon, and regolith on the asteroids. Whereas the primary point of interest to someone who's primarily focused in Mars is the abundance of carbon and water ice that Mars offers. Now, again, it's deep down in a gravity well, but if the primary place where those resources are needed is one on Mars for terraforming and in the asteroids, it's still easier to get it there from Mars than it is to get it from a place like Earth. So to sum it all up then, to answer those three questions, where will we live? Well, we have a couple of different options depending on who you talk to. We have Earth, we have space HABs occupying interplanetary space and cislunar space. We have the moon, we have Mars, and we have the asteroids. What do they provide? Well, as I said, Earth as a high technology society, at least for the next several centuries, it's unlikely that Mars is going to be able to produce things that require multiple nation state long supply chains, or at least it's probably going to be more profitable to produce that kind of stuff on Earth. So Earth will kind of be a manufacturer of high technology of robotics and finished goods is the philosophy of the Zubernites and the O'Neillians. Meanwhile, space HABs, interplanetary space HABs, provide access to essentially unlimited space. Earth has a high carrying capacity and we're nowhere near it, but I don't think it's realistic to expect Earth to be able to support trillions of human beings, not at least if we want those human beings to continually enjoy an increasing standard of living. So if we want to support trillions of human beings and really maximize the capability of the solar system, we're going to need to start thinking about space habitats and actually living in space supported by the resources of the planets and the asteroids. The moon is still an abundant source of silicates and oxygen. Again, there is water on the moon, but not enough to support a trillion human civilization. It's really more enough to bootstrap a civilization in cislunar space. But the moon still is an excellent source of silicates and oxygen, which is a necessary resource for building all of this interplanetary infrastructure. Mars is and remains the best source for organics and carbon in the outer solar system. It's not as abundant as Earth is, but its proximity to the necessary location where that is needed is kind of the primary argument there. While the main belt asteroids and the near-Earth asteroids offer a similar distribution of resources, although it's much more diffuse, the main appeal being it's already in space and you don't need to go into or out of a gravity well in order to access it. And the key distinction then between the Zubernites and the O'Neillians comes down to where our real focus is in which in situ resource utilization paths we're planning to take. And some of the central challenges that we have to solve in order to bring these solar system visions into practicality are different depending on which philosophy we're looking at. What we call trillion-dollar questions for the O'Neillians are, where do we get our water? The moon, again, has some resources of water, but it's not the same thing as the abundance of polar ice caps on Earth or Mars. But on the other hand, because it's an entirely space-based system, we can tune our gravity environments in. If for some reason it turns out that humans can't live in a 0.38 gravity environment indefinitely, or at least it's just inconvenient to do so, space habitats have an appeal of that. Again, I am not asserting that humans can't live in a 0.38 gravity environment indefinitely, especially not if we're allowed to assume centuries of technological progress in biomedical techs. But that's the question that we have to answer before we can really understand that. Another open question is really whether interplanetary economies can operate with two-year lag spans. If you can only transport between Earth and Mars every synodic period, that's a very different economy than the kind of modern economy we're expecting, where we measure lag times on the order of weeks. So to sum this all up, the reason I really like this philosophy of visualizing these four different approaches to the solar system is because we've had about 50 years to think about this kind of stuff. A lot of really great thinkers have written books and papers and concept studies about this, but the thing that really excites me about it is that for the last decade and for the next 50 to 100 years or so, is we are going to actually get to see this get implemented. Everyone has a different perspective of how we want it to happen, but that doesn't mean that it is necessary to narrow yourself into only one of these perspectives in order to visualize what is happening, because it's really exciting now to be living in a world where a private company can be inspired by one of these visions and then just work to make it happen. An instance that I find kind of really is illustrative, which really explains the staying power of something like the Artemis program, is to put Artemis on this map. Artemis is a massive effort, but it's important to emphasize that it only covers a very, very tiny portion of this exploration space. And it has appeal to all four philosophies, which is partially a way to explain its staying power. Imperfect as it is still a program with forward momentum that is accomplishing real hardware construction and a worthwhile scientific and geopolitical goal. So I think seeing it on this kind of map is a useful way to visualize why that is, because it manages to pull in aspects of all four philosophies. So thank you very much for listening. Like I said, this was kind of an attempt to get outside my comfort zone of technical topics. But if you have any questions, I would be happy to take them.
Okay, this has got one.
Oh, hello. That's a super interesting talk. I really appreciate it. I'm curious, is the diagram of the different philosophies on the locations, have you looked at that in a 3D kind of model?
What would you like the third dimension to be? Like time?
To degree of fit, for example, but although time might be interesting too.
I'd love expanding design studies to include as many dimensions as possible, but that chart already took me 5 months to put together. So expanding it to 3 dimensions would take a couple of decades. I need to heavily automate it before I'm able to do that. But yes, I would love to expand it to include more dimensionality.
Okay. The other interesting thing is I believe we're probably some of all of the above.
Yeah.
And also I've had the good fortune to see and meet 3 of the 4. Well, I've met 3 and seen all 4 of the philosophy progenitors. So thank you.
Wonderful.
Interesting analysis there. Thanks for taking an unorthodox approach. This one is kind of a gimme, but I'm curious, which philosophy would you subscribe to?
I think the reason why this breakdown appeals to me so much is because I see aspects of all 4 of them. I can really see the appeal of all 4 of them. If you force me to pick one, I'd say I can't pick one. I'm somewhere between the O'Neillians and the Zubernites, but the more and more and deeper into my career I get, the more and more I understand why the importance of the von Braunian philosophy is so front and center in our national discourse today. But the reason I got into this originally was for the love of the science. I read Carl Sagan, I read Robert Zubrin when I was a kid. So I really can't really pick one. They're all appealing to me, which is I think why I like this framing so much.
Hi, Max. Lynn George from University of Colorado, Colorado Springs. I really liked your solar system transportation map and was wondering what astrodynamics tool you used to come up with your minimum delta V's.
Excel.
Excel, was it based on
Excel.
Lambert's solution
Yes,
or not?
yes.
Okay.
I do stuff in Excel that should never be done in Excel. That should be done in MATLAB or STK or something like that. It's just the way that I tend to work. So yeah, I wrote a Lambert solver in Excel.
Excellent. Thank you so much, Max. This was fantastic. Thank you.
Thank you.
This is something we should automate. Okay.
Way to go closer. Yep. Next up, we have Brian Versick, who is an award-winning conceptual designer with nearly 30 years in the design visualization industry. He has collaborated with private companies like Deep Space Industries and Axiom, contributed to documentaries such as The Science of Interstellar by Warner Brothers, and has been featured in over 100 publications worldwide, including multiple spreads in National Geographic. Brian is renowned for his innovative use of video game engine tools to enhance awareness and education about space exploration, focusing on both planetary services and free space environments. Everybody welcome Brian.
Hello, thank you. I'm not sure what to do when the introduction covers most of what I'm going to talk about. So, I mean, that was really the Cole's notes. Just extrapolate on that, and thank you. So, for those who don't know me, my name is Brian. I'm a conceptual designer. I've been an artist since I was really little. Some of my earliest memories are my uncle's painting and drawing. And one of my earliest memories, I was about 4 years old. My older sister had a book report or a report due for school, and my dad. It was on giraffes, and my dad had a piece of paper and a pencil, and he drew a giraffe on the paper. And I was 4 years old, and I remember seeing that and was mesmerized instantly. It was like sorcery, this magic, where there was a blank piece of paper, and within minutes there was this image on it, which very easily portrayed what a giraffe looks like, and it was easily recognizable. And so, without putting any words to it, you could put this paper in front of someone, and they know what a giraffe looks like. And as part of a conversation, I felt, even at 4 years old, that seemed really, that was powerful. And a bunch of my uncles were painters, and so I was just around people who were creating images to portray places or ideas. My dad was a draftsman, and it really it propelled me to just think like, this is a power I want. This is I want to learn this sorcery. So I started drawing, and I've always been drawing. Images for ideas as communication. Words are not my thing. I'm not a talker. I let the images. If an image is worth, they say image is worth 1,000 words, but it's really worth so much more. Because if you wanted to say talk to someone about asteroid mining, it might take more than 1,000 words. But you're also not going to get that chance to give them 1,000 words before they start walking away. That's something I've learned. Over and over again. You start trying to talk about something like that, you don't necessarily have time to get in 1,000 words. But if you show a picture, within seconds, they kind of grasp what it is you're talking about. You just kind of like bypass this whole conversation thing, got right in their head. Now they have this image in their mind. So for the rest of their life, when they talk about asteroid mining or they hear it in the news or something, they now have this image. So you've just implanted something, and you've implanted this idea. So what are the ideas that we're implanting? And so let's implant really good ideas that help further the conversation. Well, what conversation do you want to further? So my conversation that I want to further is about space exploration and human settlements of the solar system. So these are the images that I create. I started in visualization design in architecture and engineering almost 30 years ago. But for the last 20 years, I've been primarily focused on space exploration and humans moving beyond our planet. Because these are images that I felt I was uniquely suited to be able to, I had the skills to show it, but also really the passion and to me, the knowledge of why it's important to have these discussions in the first place. So I create images, and these images I think are useful in lots of different ways. I think I have let the Mars Society and National Space Society and teachers and educators use my images free of charge for well over a decade, because I think they're doing the work that they are using my images for the purpose that they're intended, to further the conversation. I also do professional work for scientific publications like National Geographic or Discovery Channel or documentaries, and I work with private space companies that are trying to, they have concepts that aren't necessarily intuitive. So how do you deploy a dozen CubeSats around the moon? What would that look like? And it's useful to talk about. In-orbit refueling isn't necessarily an intuitive concept to go into. But Orbit Fab is doing it, and I love being able to contribute to these types of clients. So all of the clients that I work with in the space industry are all doing something that I find fascinating. I'm in a unique position to be able to work with people who I think are just doing incredibly important work. And it's never the same thing day after day. There's no, I used to work on like condominiums and even hospitals where you kind of just, you take a model and you move it to the next. You have the same door frames, the same windows, but in space exploration, you don't really have the same type of pre-made models. You don't have, you really have to reinvent the wheel every single time. So it's stimulating, it's rewarding, it's power beaming from space. Why would we do it? What would it look like? At industrial scale, it's got to be massive, but for testing, you could actually demonstrate it with something like a CubeSat. Beaming power from the rims of craters on the moon to the bottom of the craters. That's a useful technology. What would it look like? When Planetary Resources first announced their intentions well over a decade ago, they used some of my images, like this one, to try to talk about what it is they wanted to do. A group that I've been working with for a couple of years called the Asteroid Mining Group. We formed our own company called Deep Space Industries. And I did all of their visualizations, and boy, that was a really creative moment in time where every single day the things that we were coming up with and trying and putting our thoughts behind, it was just motivating, inspirational. This was one of my first real images that I put into, first real effort that I put into the depth of the conversation. When you talk about asteroid, I'd read the book Mining the Sky by John S. Lewis, and if you haven't read it, you might want to put it in. It is, to me, it's over 20 years old now, but to me, it made plain to me not just that asteroid mining is possible, but that it's inevitable. There's so many resources out there that are accessible, and they're already where it is we need them. And so when I'm, in reference to the previous talk, I'm a little bit of an O'Neillian myself, but also Zubrin. I mean, it's all of the above, but when you talk about really big space stations, the cost is so much about the resources required and how do you get them where they need to be. So if we're lifting all those resources from Earth, the cost is prohibitive. It's never going to happen, but you wouldn't have to, because all the resources that we need to build these massive space stations is already there. And so wherever it is we want them to be, that's where we can put the resources. And so some cases we go up to an asteroid, we kind of nudge it into the right place, and it becomes it's orbiting around the moon, or we put it where we need to be, we refine it at our leisure, and we build whatever it is we want to imagine. My purposes have always been, I've always focused on the architecture of where the humans live. That's always been my main goal. And so I do a lot of work in the infrastructure that would support that, but ideally where people are actually going to live, because that's the part that really connects to the average person who isn't in this meeting or comes to these types of conferences. There are a lot of people who really actually, believe it or not, there are people who don't think about space exploration and living off the planet. There's actually people who don't. That's crazy. But I have a lot of friends and family who, when you get into this conversation, they just stare at you blank-faced and have no idea even why. And in their mind, perhaps they're thinking of claustrophobic little tubes or something that's very sterile, or because they watch science fiction, perhaps it's dystopic. And so what I always try to do is really focus on the quality of life that could be achieved off of this planet. Because wherever humans go, throughout, as humans have scattered around this planet, wherever we go, we bring humanity with us, culture with us, and environment with us. We don't live, no matter what kind of, you live in a small apartment or a big home, you make that place your home. And so wherever we go, we're not just bringing a place to live, we're going to make a home there. And so when people see images of they see the things that they like in their own home, and there's a garden, maybe they got their pets, trees, a place to hike, a place to go fishing or boating. It taps a different part of the brain where it allows you to move to a second part of the conversation, where now we're not just talking about why you would want to, but we can start talking about how it would happen. Which is an extremely important discussion. The more people sitting around the water cooler talking about how we get off this planet sustainably and permanently, that's how we're going to go to the next phase. We need to encourage these conversations. So in the and I mean, I always want to bring my own world with me. These were my two dogs, and that's me wearing my Darth Vader shirt, because I mean, wherever I go, I would want to bring my own world with me. That's the point. The things that I love here are the things that I would still want to have with me there, with the exception of necessarily being able to walk around outside without gear. For a while, I lived in Nunavik, Northwest Territories, about 200 miles inside the Arctic Circle, and for a lot of the year, you can't leave the house without really bundling up. And the way that the houses are all built, you have your door to the inside, then you have a vestibule and door to the outside. Because it's minus 40 outside, if you open up the door and you didn't have the vestibule, all the air in the house goes out and everyone's freezing. So you actually have this like little artificial airlock, which and you spend probably 10 minutes bundling up because you can't have any surfaces. And so in a lot of ways, the frigid Arctic is actually a really good analog for living in a place like Mars. And I think that helped to direct my own feelings towards this, is that I feel like I'm used to spending a lot of times inside because the outside is inhospitable. And so Mars doesn't seem so unappealing to me because I lived in the Arctic. That's my rationale. By creating these images and trying to reach out to people, the images, since I was little, they were two-dimensional, they were static, and you can only do so much with an image like that. I've always been trying to increase the tools that I use, the skills that I have, so that it's more immersive. And so past the image of a still, I mean, if an image is worth 1,000 words, an animation's worth 1,000 pictures, because now you get a better sense of space, you get a better sense of scale, and you can just understand what it is we're talking about a little better. And so images or animations were kind of the next level of where I wanted to bring a person into these conversations. That brings me to my current project, which I call a Space Hab Simulator. It's a piece of software where my intention is to really immerse the viewer into the space. So we're now past a static image. I think if someone can walk around these places and interact, they get an understanding of what it is we're talking, the potential topics that they can then discuss in detail become really interesting, but also very broad, and we can focus it. I'm very science and engineering based. I want it to be based on the actualities of space exploration, human-centered space exploration, and so the elements, for all intents and purposes, it's a simulation, but it looks like a game. It'll play like a game. A person will download this thinking it's a space exploration game, and not even understand, or not necessarily be purposely conscious of the fact that they're going to have to understand a bunch of the science and engineering involved in space settlement in order to actually play the game. So what I'm going to do now, all these images that I've been showing are so far are just from the past 10, 15 years. The images now are from the simulator. So I use a gaming engine called Unreal, which gives really good fidelity. The shading looks good. It looks really nice. I want a person to be able to just suspend their disbelief enough to really think like they are They are programming, they are moving something around the surface of Mars. The program itself will have a Mars version, it'll have a moon version, and it'll have free space, where you'll be able to design your own space stations. So I'm going to talk about the Mars version for obvious reasons. So when you start the game, you're going to have your site selection. There's obviously lots of places to choose from depending on your own mission parameters. And you can define your own mission parameters, whether it be exploration, industry, resources, life support, or just plain research. You'll be able to choose whether you want to be near volcanoes or openings to lava tubes or areas where we know there's likely to be a lot of water near the surface. Once you choose your site, you'll have a base, a beginning habitat to start with based on the parameters of your own mission. And so if you are focused on exploration, you might have a couple more rovers. If it's research, you might have a larger laboratory. If it's life support, you might have a larger agricultural unit. You'll have different ways to research or explore the area around your initial habitat. You'll have helicopters that you can look at areas from above and identify areas to go to send your wheeled rovers. This particular wheeled rover has an arm with lots of different attachments. It has brushes, drills, diggers, movers, collectors. It can bring back samples. And you'll also have crew members that you can just send to these places. So you have a couple different ways, and it'll be up to you to kind of manage your resources and how it is you're going to explore, and with your exploration being one of the parameters of the game. When you identify certain areas, you'll have equipment that's quite modular. I designed it's a very versatile chassis of a vehicle that can be modified in a lot of different ways. It can have the ability to put a habitat on it, basically, where this rover can go out for weeks at a time. There's drilling equipment. There's equipment that bulldozes the top surface off and uses microwaves to capture the volatiles in the water. So if this is something you'd use if we think there's going to be water near the surface. And a drill like this to be able to find potential deep aquifers that are 500 meters down or more. After the surface exploration, there's subsurface exploration, lots of reasons to look around lava tubes. My intention is that a lot of these different parts of the simulation will be modules that can be downloaded separately. So a grade 4 science teacher could download the lava tube module and just have a class where they're walking around the lava tube, finding the things that we hope we would be able to find, and working with planetary geologists. And I have a long list of advisors that I'm working with, where ideally I want the simulations to be as optimistic as the planetary geologists would hope them to be, as well as the engineers still based on the sound engineering and science that we'd expect to be able to do. So it is a reasonable science opportunity. Life support systems, there's going to be the agricultural module. This would be a module that you could download on its own and just play with the cubic footage. So how would you optimize this particular farm? You could optimize it for calories per cubic meter, or calories per watt, or calories per liter of water used, or varieties of tastes that you can add to your to supplement your bulk protein that you brought with you. And so that protein could be almost anything, or just the bulk calories, and then you just add the flavors of the fruits and herbs and that sort of thing. Resource management, you got a couple different resources to manage: power, water, atmosphere, and humans. Growing up, I liked games like SimCity, where you're almost like the administrator. I love administration type things. So I like the idea of being able to sit back and manage the habitat as an administrator would. So you have your inputs on one side, power generation, you have your storage, and then power usage on the other. So ideally, to make to make it a fun game, the generation is never enough to cover everything that you want to use. So you have to set your priorities. So do you want to power your rovers to go out on longer trips, or do you want to make sure that you have enough power for your hydroponics and add another crop? Logistics and supply. This is logistics are fascinating because obviously on a place like Mars, we don't have overnight delivery. You've got to plan a long ways in advance to figure out what it is, where it is you want your settlement to go. So what do you want to build, or what kind of supplies do you need? And you have to order those a long ways in advance. And if you don't have something, then you don't have parts for something, you potentially are going to lose a capability, and hopefully it's not a critical capability. With the end goal and the win state being ultimately increased self-sufficiency of the habitat. So if you get to a point where you grow enough fresh produce and proteins and calories that you don't need to bring food from Earth, that would be one particular win state. If you can get all the water that you need, and you can by using electrolysis get the energy that you need for to send return flights back, you don't need to bring in equipment, other equipment. If you can produce your own parts, you can use the atmosphere to create polymers, and the polymers to print parts. And so again, the increased self-sufficiency becomes a win state for the simulation. The crews, each individual crew member has their different likes, wants, and skills. And I think that's important to modify. So if you have someone who really likes, they're a botanist, they're going to probably enjoy their time more if they're working in the agricultural area than if I use botanist because I watch The Martian quite a few times, and to me, everyone's either Mark Watney or Mark Watney's friend. And so depending on what it is their skills are and their particular interests, you will have to decide how to allocate your crew's time. This is so I did a quick little 2-minute animation from within the game engine. It gives an idea of what it's going to look like. It's kind of just a preview of the game itself. Take the moment to just mention, I have a bunch of posters over here with the proceeds going to the Mars Society. If you buy any and I'm around, I'd be happy to sign them if you wanted. If you want to follow what I'm doing, I'm on Facebook, Threads, Instagram. Thank you very much for time.
That fly through was amazing. That was really like, I can't express how impressed I am with that. Congratulations for that. Thank you. Any questions? Yeah, go ahead, Kemba.
What would you consider for this new technology of spatial computing, things like Apple Vision Pro to provide the audience with a high fidelity kind of taste or experience of what you do?
So I'm trying to build this. For the most part, my team on this has been very small. 98% of it has been me. So it's a really small team. I have been bringing in interface designers, modelers, programmers, but for the most part, it's a very small team. And I'm trying to build it sequentially. There's a lot of I'm doing an MVP first, and trying to build on top of that. My goal for this is that it keeps on building, and that you can play this in VR, you can in augmented reality. One thing that I've been working on is once you set up something like the farm using augmented reality, I have a room in my house that's basically just an open room. That room can be my laboratory, and so especially with the MetaQuest 3 has really good augmented reality right now, where you can superimpose things into a certain space. So once you allocate the space to be able to put your laboratory into that space, or even designate a certain room of your house, once you allocate the size, that is your lava tube. So you can navigate within that room, and that can be the lava tube, or that could be the airlock, and that you can superimpose your habitat within the rooms in your house with the your kitchen table can be your lab desk, or the kitchen counters can be part of the lab. And so you're walking around your house with your VR glasses on, interacting, and that is your laboratory. So so the goal is to just keep on doing this. I've been creating images, drawings my entire life. I've been creating 3D models. I've been using computer to do my models and animations for over 20 years. And I've been doing it just because even when I'm not paid to do something, this has always been my evenings and weekends going back for as long as I can remember. So I'm not going to stop. Now it's all in this gaming simulator. I would anticipate that my next 10 years are this, and it just keeps every single year. When you ask me how it's going, I'll have more to show you. And I hope that there's a VR component, and I hope that when I at least get the initial MVP up on something like Steam, that revenue helps to drive an increase, and it scales, because there's so much to add. I think I could probably have I have 100 lifetimes worth of work to do, at least. So I'm sure I can't get to it all, but yeah, big plans anyways.
Yeah, so a brief question first to figure out the rest of my question. Are you familiar with Kai Statz's work with CIMOC?
Yeah, Kai Statz and I work very closely, have been for over a decade. In CMOC, when you pull up images of what it could look like, those are my images. And so Kai is doing the SAM analog at Biosphere. So I was the initial designer for the SAM habitat. And I've also been working on they have a Mars yard now. So I did the initial designs for the Mars yard before the production company came in and carved it all out of foam. But yeah, Kai and I work very, very closely together.
Very cool. That basically answers my question. So yeah, continue to do great work. It's awesome. Love what you're doing. Yeah.
My intention is to work with all the analogs, because what they're simulating is ideally what I want to simulate. So it's SAM, it's the MDRS, and HIMARS. And so the things that they're working on are the things that I want to be able to implement and simulate as well.
You're probably familiar with the game Surviving Mars, which, other than VR, seems to have a lot of the same features that you mentioned. I was wondering, other than VR, what are your main differences in focus or design from that game that you intend to direction that's going to go?
Honestly, I haven't actually played Surviving Mars. I'm aware of it and I've looked into it. This has been, the things that I've done have always been passion projects. And so I created large Kalpana 1 cylinders, even though other people had already created them, and I created something that was different. I worked on asteroid mining when other people had already done their version. So what I'm doing here is a game that I want to play. It's a simulation that I want. And there's going to be a lot of overlaps to what other people and companies have done. This is exactly what I want in a game, because it's not just the product, but it's as an artist, the process to me is the passion. I enjoy the heck out of this, and I want to do it from the moment I wake up in the morning to the moment I go to sleep, and I'm just going to keep on doing that. And they didn't ask me to work on their project, and so I don't have an outlet for it. So this is my outlet for, I mean, for the rest of my life. This is what I do, have done, and going to continue doing, just because. And if other people like it, it's convenient, but I'm going to keep doing it anyways. That's like, as an artist, it'd be great if other people like what I'm doing, but I'm not going to stop. It's
Wonderful. Congratulations, Brian. Thank you so much. Thank you so much.
Well, we're going to break for lunch right now. I want to remind everybody that Dr. Robert Zubrin is upstairs on the 3rd floor. If you want to mingle with him, if you've purchased one of his books and you want to get it signed, you can take that upstairs to the 3rd floor. Also, a reminder, at 1 o'clock in room 334, we're doing the Mars VR. So check that out as well. And then we're going to meet back here at 1:30 for the afternoon session.
Probably not.
Hey, James, come to the front real quick.
Got it for you there. That one. Yeah, hold on one second. Let me just go back to your drive.
Oh, that's.
Save modified. Hey, Bill, how's it going? Yeah, likewise. I'm living the dream. He's gonna go. Essentially, it's really easy. We're just when the presenters come up to the laptop, they load their slides. Not hanging out upstairs because he doesn't want. Yes. Yes. What we can do is you can give your talk again sometime over Google Meet, and we can put that video out on YouTube. No, nope. That system in the back. We unplugged it and plugged it back in, and it worked. Luke thing. Like you're all set here.
Yeah, there's an enemy. Okay, we're cooking with gas. Okay, great, I'm done. Thanks. Oh, no, so he's not.
lost your partner in crime?
All right, I'm going to ask you, Peter. I'm going to ask Al.
Well, it's still an awesome opportunity. Yeah, it's just the way I overcomplicated everything with the audio. Get it better next year. Now we're gonna get to Mars. Improvement on everything. Oh, Sabine. Yeah, hey Daniel, how's it going? Good, good. Yeah, I remember we talked about AI about a year ago, right? Learned a lot since then. Yeah. Ask me after.
Oh, yes.
Right, we're back after lunch. I see quite a few faces. I think some people might still be finishing up their Pagliacci's pizza downstairs, but I see a few more starting to trickle in. Welcome, guys. Come and grab a seat. So get ready for our next speaker. Dr. Stephen Benner is a distinguished biochemist at the Foundation for Applied Molecular Evolution and is renowned for his work in synthetic biology, dynamic combinatorial chemistry, and a paleomolecular biology. Say that 5 times fast. He was the first to synthesize a gene for an enzyme and develop artificial genetic systems that have enhanced clinical testing for HIV and hepatitis. His paleomolecular biology work has allowed the study of ancestral proteins from extinct species. Benner also earned his BS and MS in molecular biophysics and biochemistry from Yale University and his PhD in chemistry from Harvard. He's also received prestigious awards, including the Dreyfus Award and the Sloan Foundation Fellowship. Everybody welcome Dr. Stephen Benner.
Introduction. Everybody in this room knows this, but since 1976, NASA, the NASA community, shall I be more precise, has not sent a mission to seek extant life on Mars. And John Rummel and Catherine Conley about 7 years ago wrote a piece to explain this. And I've just excerpted one of the quick lines from it. Is basically the Mars community is not convinced that a mission to attempt redetection of extant Mars life is a high priority. Now that redetection is a tease. It's because, of course, the Viking 1976 experiments certainly have data that people have said might have been detected, but we'll talk to that about later. Now, so you can ask the question, what things do NASA committees give high priorities to? So, of course, they fly drones on Mars, and the purpose of that is to prove that we can fly on Mars. Or they will, go pile rocks up on Mars, and you heard some discussion of this last night. And of course, that's basically a statement that we're getting ready to go look for ancient life. Right? It's almost as if they're piling up rocks, as if NASA does not think we know how to detect life now, but maybe when the rocks get returned, we will be smarter and be able to actually come up with a good experiment. But that's going to welcome you to the world of Aristotle. Okay, you have to ask yourself, what logic gives flying drones on Mars a higher priority than detecting extant life on Mars? Well, the short answer to that question is that the logic means that you don't think you're going to find extant life on Mars. There's no reason to go looking for life if you don't think you're going to find it. To be a motivated explorer, explorers have to believe that they'll find something. So here's Columbus, who thought he was going to find India. Now, he didn't, but that's what motivated him. Henry Hudson thought he could find the Northwest Passage. There is a Northwest Passage, but not with the technology that Hudson had at his level. But let me introduce you to Norm Horowitz, a modern explorer. He's professor of Caltech biology, a member of the National Academy of Sciences, and he's the first to show the one gene, one enzyme hypothesis in biology. He also built a model for the evolution of metabolic paths, but he also built the Viking experiment that saw the Martian soil fixing carbon dioxide. There was also a little bit of carbon monoxide. Both of them had radioactive carbon. And so what they saw was the Martian soil is able to take carbon dioxide, carbon monoxide out of the Martian air. Well, they put their own air in roughly the same simulation of the Martian air, but with radio-labeled carbon. They solved the formation of organic carbon in that soil. And it's exactly what photosynthesis organisms do on Earth. And this was intended to be the positive for life detection in the soil of Mars. So they saw life. So if you go to Wikipedia and look at Norm's biography, they will say, hey, Horowitz's experiments provided the first indication that there is no current life on Mars. Now you might say, wait a minute, that's kind of odd. They just got the result that was indicative of photosynthesis on Mars, and Wikipedia says, how the hell is it possible that therefore that organic carbon fixation indicated that there is no current life? Very good question. So the first lesson for the students, I know there's some in the room, is that when you want to know what a paper said, you don't read a review of the paper, you don't read what someone else said about the paper, you don't read an abstract of the paper, you certainly don't read the Wikipedia page on the paper. What do? You read the paper. Yes, thank you. And so there's a paper. This is by Norm Horowitz. It's in Scientific American, which of course is supposed to be accessible to the layperson. Now, keep in mind that every time I try to read a Scientific American paper, unless it's exactly in my field, I don't get past about the third paragraph before I don't understand a word. But there's a paper from 1977 by Norm, The Search for Life on Mars, and he described what Viking did in several steps. So the first thing he pointed out was they took pictures, which is what they did first. But then the second thing he notes is that they analyze the soil for any organic constituents. And to do that, they use the so-called Viking gas chromatograph mass spectrometer, which is a GCMS for short. Now, what the Viking GCMS spec did, as many of you know, is that it heated the sample to 500 degrees centigrade. They scooped a little soil in, they heated it to 500 degrees centigrade. That was supposed to volatilize any of the organics that were in that soil. They blew those organics into a stream of hydrogen and dumped them into a mass spectrometer, where they looked for ions coming from organic materials. Now, in his paper, Norm Horowitz describes that experiment, and he gives the result that is the only organic compounds detected by the GCMS were traces of cleaning solvents known to have been present in the apparatus. Okay, fair enough. What should you ask? Well, what cleaning solvents? Good question. Norm doesn't say. All right, lesson 2 for the students. So science begins with a distrust of experts. That's a line actually from Richard Feynman. Yes, Norm is a member of the National Academy of Sciences, and I am not. But you nevertheless cannot trust Norm. Nothing personal, it's just the rule, okay? So the point is, lesson 3 for the students is that when you get yourself into this situation, there's a chain of literature. So you'll read Norm's paper, and it will lead to the statement that there were cleaning solvents in this sample from Mars. You'll ask, what cleaning solvents are there? Well, they doesn't say, so you had to go to the paper that he might have cited. I mean, Norm had some reason to say this, right? And so that reason must be based on some data he got from somewhere. He didn't just make it up. So, but he did not tell us where he got the data. You have to go look for the data on your own. For all the people in this audience, that is a very, very productive thing to do, to follow it all the way back. So you got to find the guy who built the GC-mass spec, and there he is, Klaus Biemann, professor, MIT, member of the National Academy of Sciences. I am not, by the way. And he is the person, if you go to his Wikipedia page, says he partnered with a NASA Viking program to Mars, which failed to detect organic matter on its surface in 1976. Now you say, wait a minute, I thought they had detected cleaning solvents. Okay, well, more, you have to drill now the next paper back. So when you want to know what the paper said, you don't need to read a review of the paper. You don't read what someone else said about the paper. You don't read about the abstract of the paper. You certainly don't read the Wikipedia page of the paper. You go read the paper. And there it is. So that's the paper that Biemann published, where he actually says what he saw. Now, you'll notice he saw inorganic carbon dioxide. That's not an important point because, of course, the atmosphere of Mars is carbon dioxide. He saw a little bit of water vapor. That's not an important point. We expect to see that. The organics, none detected. See table 3 for detection. But then he has 2 organics in Roman numeral 3, which he labels terrestrial contaminants. And one of them is a fluoroether. Now, to be more precise, that's Freon E. That's what they almost certainly came from Earth. But the other one is methyl chloride. So now the question you're supposed to ask is, was methyl chloride a cleaning solvent? Right. Well, methyl chloride is not a cleaning solvent. Methyl chloride is a gas. Okay. What he's done is confused, so Norm certainly has confused dichloromethane with monochloromethane. That is, he's confused methyl 1 chlorine with methyl 2 chlorines. And by the way, methyl with 2 chlorines is a perfectly good liquid, which is used as a cleaning solvent, but they've confused the two in this particular subject. So that's a problem. So wait a minute, back to the subject. Norm might be excused, by the way. He's a biologist. He's a member of the National Academy of Science Biology section, so he need not know what methyl chloride and methyl dichloride are. But furthermore, Beeman's paper lumped these two things into a single heading in the table called terrestrial contaminants. So now the reason why they know that the freon is a terrestrial contaminant is because they ran the mass spec on the way out to Mars and they saw freon in it. So now the question you can ask is, hey, did they see methyl chloride in it? And the answer is he implies it in the science paper, but you don't trust them, right? You got to go back and actually read the paper where they actually did it. Lesson 4, when they tell you that they've observed something, you're supposed to ask to see the friggin' data. And it's fortunately, oh, by the way, the data will not be found in general in the science paper. Science is a fashion journal. It's for modeling clothes and various other things that are science related. But fortunately, Klaus published a full paper in what we euphemistically call a lesser journal. Maybe you've heard of this. And this is Journal of Geophysical Research. And he actually says that they didn't see methyl chloride on the way back, on the way out to Mars. So what he does say is that methyl chloride could conceivably, therefore, be indigenous to Mars. Okay, however, if it were, one would expect that the other related compounds like ethyl chloride or methyl bromide, well, methyl chloride, then you make it ethyl chloride, and methyl chloride, and then you make it methyl bromide, would also be formed, but none were seen. We tend to believe that all the methyl chloride is from terrestrial sources. Okay, so here you are. The observation of methyl chloride is recognizing that it could be Martian, but nevertheless having a tendency to believe that it is not Martian led to a table in Science where methyl chloride listed with freon as a terrestrial contaminant, which then confuses Norm Horowitz, not understanding the difference between a cleaning solvent and not a gas, which then leads to the Rommel-Connolly community decision to give a search for life at extant Mars a low priority. A number of steps are in between the last two. Okay, but it's valuable to follow this thread all the way back. So methyl chloride on Mars is an anomaly. It's not supposed to be there. If it's there, you can't explain it away. So as you all know, we teach this to 7th grade science students that when scientists encounter an anomaly, they reevaluate the assumptions behind their expectations, right? Not. Okay, you haven't got that far yet. Exactly. So scientists, in fact, don't do that. They find a way to rationalize away the anomalies as a way of confirming their propensities to believe. So here's what Klaus did. He said, if methyl chloride were on Mars, one would expect that other related compounds like ethyl chloride or methyl bromide would also be formed, but none were detected. This is technobabble. It's got words, it's got sentences, it's got a subject, verb, object, but there is no reason to expect that a process that would form methyl chloride would form methyl bromide or ethyl chloride on the side. Now, fortunately, we now know actually what happened, okay? We actually know, my only contribution to this field was a 2000 paper noting that the GC mass spec instrument could not detect the dominant meteoritic organic molecules, even if it were sitting on a pile of them. Okay, you can go read that paper. Then Phoenix, a mission to Mars, landed. Many of you, if you know about it, it discovered perchlorate on the surface of Mars. And the Viking gas chromatographic instrument heated the soil to 500 degrees before looking for organics to try to volatilize them. And when you heat organics with perchlorate, you get fireworks. That's what happens. Not at room temperature. I can mix perchlorate and organics all that I want in this room and nothing happens. But if I heat it to 500 degrees, I get fireworks and a small amount of methyl chloride. And that was actually shown in 2009 by Chris McKay. And by the way, rover after rover after rover has discovered organic molecules on the surface of Mars. There's no question that there's organics all over the place on the surface of Mars. But we understand why the GC mass spec did not observe them, and the answer is that it did not observe them because it set them on fire. How are we doing? Let that be a lesson. So in the face of these facts, did the community change its mind? Well, In 2021, the community worried that someone might incorrectly claim to have found a biosignature, set the Twitter sphere ablaze. And so a committee of experts was assembled to write out a community consensus for what biosignatures were to be allowed to be published and which ones were not, okay? To protect the public from false claims that we had detected life. And this was headed by Vicki Meadows, who, by the way, sits in an office about a quarter of a mile that way. She's a professor of astronomy here at the University of Washington, and Heather Graham was her cohort. And so you ask the question, how did they view the Mars GC mass spec result in 2021? This is 20 years after we published the paper showing that the GC mass spec could not have detected the dominant organics even though they were there. And of course, more than 10 years after Chris McKay and various other people explained the chlorate relationship. So the report says the search for organics using the Viking gas chromatography mass spec further support a non-biological interpretation of the results. So they are going all the way back to Norm Horowitz's interpretation of the results and ignoring everything that has occurred in the half century since to say, not the least of which is the rover identification of organics, to say that soil contained no organics, it was self-sterilizing. So you can ask the question, how is it possible in 2022, over a decade after the GC mass spec data were shown to be misinterpreted, and with a well-established interpretation of those data, that the Viking NASA community can get the Viking data so wrong? Well, there's a couple reasons. I just did a 2.5-hour interviews with Brian Dobbs, who is a documentary filmmaker, who has put out this wonderful thing called Blue Planet Red, which you can get off of Vimeo. But he told me that astrobiologists that he interviews think that Viking showed that the Martian soil was sterile, but they actually don't know the experiments that the Viking experiment did. So who's got the time, right? I mean, so the only point is, but this is a discipline we try to teach to our students as well as to ourselves, that we're actually supposed to know what the data are behind our conclusions. Sometimes we do. So the Meadow-Graham report saw Viking showing a need for community gatekeepers to control publication. In fact, what it shows is a need for the community to read the papers. That would have been. So that's kind of cool. But there's another real reason why this has not, the state of affairs has persisted. And that is because no one bothered to build a pro-life alternative. Because once they thought there were no organics on the surface of Mars, through a misinterpretation of the GC mass spec result, they were not inclined to go try to put together a model for how life could work there, because there are no organics, and no organics means no life, right? So we put one out on our favorite site. This is our blog, www.primordialscoop.org. Get it? Yes. And so the model is for a bacterial autotroph respiring with stored oxygen for overnight metabolism, which has the convenient acronym BARSOOM. Now, I don't know how many people are old enough to know what that reference is, but never mind. This is for those of you who have never read John Carter, Princess of Mars, and Edgar Rice Burroughs thing. He's the same guy who wrote King Kong, which is a property of his that earned him more money. Also noted that Martian life called Mars Barsoom. But you can go back onto Primordial Scoop and you can see Jan Spacek and Benner arguing about this. The question is, what would the lifestyle of a microbe be that could live under Mars soil conditions and give the Viking results? And the answer is a couple of things. It's bacterial. That means it's a small bug. It's an autotroph. That means it's fixing organic carbon from the atmosphere. It's respiring. What that means is that every now and then, once it's fixed the organic chemistry molecules, it will eventually burn them with oxygen, especially at night, because they need to live in the night as well as in the daytime. And it's storing the oxygen to do that respiration. And the reason for that is that on Earth, right, you have a plant, it does photosynthesis, makes organics, and it wants to burn the organics at night, but it can always get oxygen out of the air because it's thrown the oxygen out into the air, but there's a lot of it to come back. On Mars, there is really no oxygen. So what they needed to do if you're going to live on the Martian soil near the Viking site is you have to actually store the oxygen that you make during the day so that you can use it for respiration at night. Now, by the way, the first result, autotroph, is Horowitz's results. That's the fixing of carbon. The oxidizing reduced carbon food is actually the second result, Gil Levin's and Patricia Stratt's result. And there's a gas change reaction, which shows the use of stored oxygen. So the oxygen storage is the principal difference between Martian and Terran photosynthetic autotrophs. Right? A plant on Earth can discard the O2 that it makes by photosynthesis during the day because it can always recover that from the atmosphere at night. A Martian cannot. So this is really the difference between jet fuel and rocket fuel. Right? So jet fuel, you assume that you get the oxidizer from the air as you're flying along. Rocket fuel, you don't. Right? You have to bring the oxygen with you, and that's what, in fact, Barsoom is doing. So Barsoom actually gives all the Viking results. The first result is the Horowitz result on the left. I've already discussed it. You put radioactive carbon dioxide into the atmosphere, it makes organics. And Norm could never explain that result. I'll get to that in a second. The second is that they sprinkled radio-labeled food on the soil, and they saw the evolution of carbon dioxide. That's what happens if I sprinkle radio-labeled food on you. You exhale carbon dioxide. And the non-biological oxidizers do not exist that produce that result at that rate, at that temperature. And the third result is the so-called gas exchange experiment, which I just mentioned. They put water on the surface. They saw the evolution of O2. And of course, according to the Barsoom model, that is evidence for stored oxygen. They, and frankly, well, in my view, misinterpreted it by saying that this was evidence for such a strong oxidant in the Martian soil that the soil was self-sterilizing and therefore led to the absence of organics, which of course they're not absent. So the misinterpretation of the GC mass spec data poisoned the entire rest of the discussion of all of those experiments. Adding water caused Barsoom's stored oxygen to be released. But to explain the absence of organics, the team misinterpreted it as evidence of not of oxygen, which is not, of course, a strong enough oxygen kinetically to burn food. You have to have enzymes to do it. That's why you're sitting here in an oxygen atmosphere not catching on fire. But they also had to explain the absence of organics, the incorrect interpretation of the data showing an absence of organics. The team misinterpreted the appearance of oxygen, that a stronger abiological oxygen was in the soil, and that was toasting everything, including the food that Gil Levin was presenting to it. And that corrupts interpretation of the food experiment. All right, so you have Chuck Klein. He headed the Viking biological team. We must be wary of biological interpretations of the label release experiment in the face of information indicating that all of the samples tested yield O2 that in the gas exchange experiments. Upon introduction of water, evidence for strongly oxidizing chemicals in these samples, but that conclusion requires that you believe that there are no organics there. That's why you need the strong oxygen. So if the soil strongly oxidizes all organics, you can all of a sudden see a paradox with Norm's experiment. Because Norm is putting radioactive carbon dioxide and he's seeing the absorption of organics onto the surface of Mars. But if the Mars is strongly oxidant and doesn't tolerate organics, how the hell does Norm see the fixation of organics on the surface of Mars? Norm is aware of these. He says it, he mentions it. So he says the production of radioactive carbon dioxide from Gil Levin's food is understandable in the light of the release of oxygen, suggesting that the surface material of Mars contains peroxides. A couple of problems. Doesn't suggest that the surface contains peroxides, it just suggests that the surface contains O2. That's what Barsoom is storing for the evening. In any case, standard peroxides don't oxidize Levin's food. Okay, but then he goes on further, the fixation of carbon in the Horowitz experiment was surprising in that such a strongly oxidizing environment should toast a small amount of organic material that is fixed in my experiment. He does not, I don't know how to explain it. He says it's not easy to point to a non-biological explanation for this anomaly, but he's going to brush it aside by saying, well, we have investigations underway, and when we get those investigations done, we're sure we're going to have some way of explaining that result. Okay, so no solution, by the way, has yet to admire. Now, we're worried about other things in Barsoom. We're worried a little bit about how it would survive in Martian ultraviolet light. There's a rather harsh environment. As a photosynthetic autotroph, it has to have access to photons from the sun. But again, you can go back to Primordial Scoop. Jan has put together a paper talking about that radiation environment. And actually, you heard yesterday from Pete Worden about this organism. This is a guy who's going to sit inside of a mineral shell, which is going to filter out the harsh UV light, but still be able to do metabolism inside of the cell. And obviously, the question next comes is, can you eat Barsoom? Well, I mean, why not, right? You don't have to breathe if you eat Barsoom, right? It's jet fuel, so it's not jet fuel, it's rocket fuel. So we're bringing the oxygen as well as now, it may be a little crunchy, it may be a little hard to digest, and of course, you are assuming that it has the same fundamental underlying molecular biology as you have so that it's tasty to you, so it can provide needed nutrition to you. And that may or may not be true. We have to go look. But that's the final point. How do we look for Barsoom? Well, we are hoping to find molecules that are needed to enable Darwinian evolution, not unknown molecules that are necessary and unique products of Darwinian evolution. So DNA information is a central part of biology. Biology is at some level information. And so synthetic biologists, people like myself, we've made alternative forms of DNA. We've made DNA with actually I see Jens, he's doing the sequencing of 8-letter DNA, so it's good to see you. He's my collaborator at the University of Washington. And from our efforts to make alternative DNA, we can make systems that do evolution just like the DNA that you and I have, but there are certain rules. So we cannot remove the repeating charge in the backbone of DNA. This is a so-called polyelectrolyte theory of the gene. Right? For all life in water, the informational needs of Darwinian evolution require a biopolymer that has a repeating charge, positive or negative, yours happens to be negative, built from a small vocabulary of size and shape regular units. So that's cool because if that's the case, it's very easy to find polyelectrolytes in water and it's very easy to concentrate them from water if you just put them in an electric field. And so I have a schematic diagram here where you're putting polyelectrolytes, and that's a little bit better by the animation. So here you are seeing water flowing from Mars through a device. There is an anode on the left-hand side. That's the red bar with positive signs on it. There's a cathode on the other side, the black bar with negative electrons. And so first approximation, all the particulate matter just flow vertically through. But then you put a field on, and now you have the DNA, green DNA, and it's going through semiporous membranes. So the first membrane is large enough to has holes in it, large enough to let the DNA pass through, but not particles. The second membrane has pores that are smaller. They hold back the DNA, which is now these green double helices, and allow the DNA to be concentrated in this way. And of course, if you encounter on Mars a weird life form, which has positively charged DNA, instead of negatively charged DNA, it gets concentrated in the channel to the right. Meanwhile, the salts are going to get passed through farther into the outside channels because the membranes have holes in them that are large enough to let the salts pass, but not large enough to let the genetic biopolymer pass. There's also another plan, which you can go to Primordial Scoop to read, which has to do with planetary lawn darts, which is our penetrators, but you have to go to Primordial Scoop to actually have a look at that. So Jan and his team are now building this agnostic life finder, ALF, agnostic life finder, get it? With NIAC, and the community, frankly, is coming around. There was this paper published in Astrobiology in 2020 rather, which got a whole bunch of us together to decide where to go look for this water on Mars, in caves and other locations where it might be found. Amy Williams put a Mars extant life plank into the latest decadal survey. You heard some about it earlier in this conference. And John Rummel, by the way, is participating in this activity as well. Okay, so what lessons have you learned? Read the damn paper. Science begins with a distrust of the experts. Follow the literature back until you get the answer. Don't stop before you get to the primary data and demand to see the data. But there's a fifth lesson I want to mention is that we still have a need for private interest, activity, and funding, and that's, of course, what the Mars Society represents. Chris Temby, who's sitting up here in the front row, is heading up the Agnostic Life Finding Association, ALF. Alpha Mars is their webpage. It's a 501c3 nonprofit private astrobiology organization. It's administered by students. It's international. A lot of people subscribe if you go to the webpage. And it's the only entity solely dedicated to looking for extant life on Mars. So you can participate by going to this website or by talking to Chris, who's sitting in the front now. With that, let me stop, answer any questions.
I just want to say briefly, the Mars Society, one of the great strengths is that we're independent. We're a grassroots organization. So we can say to NASA, you guys should be doing more to look for life. And so we're 110% behind what Stephen Benner and his team are doing. Just want to say that.
What's the expected size and mass of ALF? And have there been any discussions with NASA or other space agencies of putting it possibly on a future Mars probe?
Yeah, so there's a small ALF, which is a stationary ALF. You just put the electric field in a stationary sample of water. There's a medium-sized ALFs, which of course will have a flow. And of course, what we would love to do is go with SpaceX to, they're going to be mining a lot of water out of the near surface of Mars so that they can use that to create propellant for human missions to Mars so that the guys can get back, right? So there are various sizes. So you can have it something that's this big, or we can have something that's now as occupies a lab table. Yeah, and we're in constant discussions, but keep in mind, we still need more discussions of how we're going to get this device to Mars. And if anybody has any suggestions, we'll talk about it. We're obviously not going to be with private donations funding the launch. And so we're talking to a lot of the bigger organizations trying to get this to go. And eventually we might even get NASA to take it.
You were saying that we should no longer be looking for things that are the result of the process of life. We should be looking for things that are required for life.
Yep.
So if we're looking for excellent life and we know that there's the stuff possible, we don't know that if we know that there's stuff that is required for life to exist, we still don't really know if it's actually there.
Yeah, well, that's right. Well, here's your problem. So if you ever watch Star Trek, you'll notice that all the aliens look like Hollywood actors with prostheses. And that's, of course, because they are. But you have to start worrying about coming across microbial life where morphology is not a very distinctive thing, right? The bacteria don't have Vulcan ears. And also you have to start worrying about what would be universal. So you have 20 amino acids. You eat lysine, you eat arginine, you eat valine. There's no reason why Martians should have the same amino acids in their proteins. If they've had a natural history independent of the natural history of life on Earth, they might very well not. So you can't go looking for those things. But here's what the synthetic biologist does. We do know that information is a key part of evolutionary biology, and you have to have a molecule that stores it. We can made in my laboratory maybe 150 different variants of DNA. Some of them work and some of them don't. And so what we find among all the ones that work, they have a repeating backbone charge, positive or negative, and that's makes them work. And there's a reason for that, which has to do with the need to have this molecule have physical properties that are stable as they evolve in structure. So if you swap out ATGC for GCTA in your thing, you have to have the molecule still dissolve in water, still be function. And the repeating charge actually is what enables that. Without the repeating charge, you don't have a system that does that. So that means that we can go even to Vulcan or to Kronos and speak to our favorite Klingon and expect that even if they don't have DNA that looks exactly like yours or mine, they will have DNA that has this repeating charge. And so that's a universal, that's the claim. So that is, if there is life, there will be these DNA-like molecules with a universal charge, and we can concentrate them in an electric field. And therefore, we know that they are there if life is there. How you doing?
Thank you.
So our next talk is the update on the Mars Technology Institute. Sorry. I'm sure a lot of folks have been waiting for this update. I'm trying to get Robert on the call. We're going to hopefully have some opening remarks from him. But what I can do right now is just show you guys and talk a little bit about I can do a little bit while we're waiting for him to join, is just talk about kind of where we've been this year with it all. which is, we announced this last September on the Ashton's podcast, Red Planet Live, with Alan Boyle. And we talked about it at the conference last year. And then we did a crowdfunding campaign from Thanksgiving until February, and that raised 150,000 or 150,000 for the project. Started a biotech project we just talked about a little bit, and an AI project. And here's Robert.
Yes. Hello. So, once again, I have to apologize to people because I very much want to join you. If you do want to talk to me, I'm on the 3rd floor of this building, but I have refrained from coming to the sessions because I have an asymptomatic case of COVID. So if you're willing to risk it, come on up. But if not, I'll talk to you this way. So we're here to talk about the Mars Technology Institute. And to recap, if you read my books, especially my new book, The New World on Mars, I outline invention as one of the main economic supports for Mars settlement. That is, a human Mars settlement, a city-state on Mars, will be a group of technologically adept people in a frontier environment that forces them to innovate. And so they can, well, a successful Mars colony will need to be highly innovative, and it will have the chance to be highly innovative because of those facts. And it will make inventions that will meet its own needs, but also be licensable on Earth. And those inventions, as it were, IP, as exports from Mars, will be one of the main economic supports of a Mars city-state. So people sometimes ask me, well, if you think that a Mars inventors colony could actually be profitable, why not create it here on Earth first? Now, there's some counter arguments you can make to that proposition. Certainly, an inventor's colony on Earth would not be as strongly motivated as one on Mars. On the other hand, it'd be a lot cheaper to build, that's for sure. But the decisive factor between those two things, however, is that we are not currently in position to create an inventor's colony on Mars. So why not create one on Earth? And that was the idea that gave birth to the Mars Technology Institute, that we would create an institute that would be dedicated to creating the technologies needed to settle Mars, okay, and make money by spinning off those technologies for use on Earth. So we were not focused on the area of flight technology. We were focused on the technologies needed to live well on Mars once you are there. Now, there's a number of areas that one could name here. There's energy technologies, advanced nuclear and fusion, but the entry point into getting involved with those is high, and so we chose to defer that. There's another important area, which is food technology, which I'll get to in a minute, and a third, which is artificial intelligence. I'll talk briefly about artificial intelligence, and then James is going to pick that subject up, and then I'll return to the subject of food technology. One of the key problems facing a Mars settlement, and once again, this is not an essential thing for a Mars expedition, okay, but for a actual Mars city-state, is that a Mars city-state will face an extreme labor shortage in both numbers of people and diversity of skills. And because you're going to have a colony initially of thousands of people, perhaps tens of thousands of people, perhaps 50,000 people, it still is extremely small compared to the population of the Earth or any one country on the Earth. And would you really have within that population all the skills you need for a civilization? Not an expedition. Now you can do with 4 people, but a civilization is something else entirely. So therefore, the Martians, as early America, which also suffered a severe labor shortage, early Americans became gadgeteers pushing labor-saving technology. And it was one of the main reasons for the success of America, especially in the northern colonies. With also greatly increasing American living standards, creating labor-saving machinery, which is labor productivity multiplying machinery. Well, Mars is going to be this way even more so. Okay, so it's going to need to do conventional labor-saving machinery and automation and robotics, but the most powerful form of labor-saving machinery that it can possibly be is a form of artificial intelligence that doesn't compete with people, but enables people. A form of artificial intelligence, an app, if you will, that would allow anyone to do anything. So now you have 50,000 people, all of whom have all the skills of the Earth. Now, that would be an ideal, but if we could have most people enabled to do most things, that would be a big step in that direction. And James is going to talk about the technological initiative that we have that is dedicated to pursuing that. And it should be obvious that if you had any such technology, it would have enormous utility on Earth. It would be enormously enabling, expanding human abilities, raising living standards all over the world, and making a huge amount of money in the process. It would literally be a killer app. So that's what James is going to discuss. I, right now, however, are going to switch gear to another key technology problem that Mars colonies will face, which is the issue of food. Okay. Now, this may not seem like a fundamental issue because you can say, well, we know how to grow food. We can build greenhouses on Mars and grow food. And that is true, you could. And if you look at self-contained greenhouses, for instance, of the type that are being developed by Interstellar Labs, they represent a reasonable solution to the problem of growing food for a Mars base of 10 people, 30 people, maybe 50 people. But if you're talking about supporting a city of, say, 50,000 people, putting aside entirely something like a million-person metropolis that Elon Musk discusses, you find that this runs into very real problems. Okay, because you see, conventional agriculture, whether done in fields or in greenhouses, relying on photosynthesis, is extremely inefficient from an energy point of view. A Iowa cornfield, which is the most productive form of conventional agriculture done on Earth at scale, could support about 20 people per hectare. With what it produces. 30 if you have people just eating corn, but if you have a fraction of the corn going to feeding animals or replacing a fraction of that corn with fruits and vegetables, whatever, say it's 20 people per hectare. So that means for 20,000 people, you need 1,000 hectares, okay, which is 50,000 acres. Okay, and are you really going to put that under greenhouses? Or are you going to build tunnels lit by artificial light to try to do that? The power for that would be incredible. And the reason why this problem exists is because, you see, photosynthesis at the level of the chloroplast is about 4% efficient in terms of turning energy into food energy. And at the level of the wheat field, cornfield, excuse me, is about 0.2% efficient. And if you use some of that wheat to corn rather to create animal protein, it's 0.02% efficient. Now, we've been able to tolerate that on Earth because we got lots of land and it's lit by natural sunlight, which gives you, megawatts per hectare of power, you're fine. But on Mars, you don't have that. So what's the answer? Now, is synthetic food. Now, there are microbes that can turn simple chemicals that can be made by physical chemical means, such as methane, which, for instance, we would make in the Mars Direct Plan as propellant, or methanol, which can be made by a related process, into protein, which is a perfectly edible animal protein. These microbes are extremely efficient, and even if you then took the protein they make at more than 50% efficiency and then fed it, say, to fish, which might be about 50% efficiency in turning raw protein into fish meat, which would be aesthetically acceptable form of food, you're talking about a process which is order of 20% efficient, which is to say 100 to 1,000 times more efficient than conventional agriculture. Now, so I thought a bit about this, and I went to see Steve Benner, who we've heard from at this conference, leading biotechnologist, the inventor of synthetic biology, and discussed the concept with him. And he and his people took my initial idea, which was using bacteria to turn methane into animal protein. And they had some criticisms of it, and they altered it and said, okay, here's a better idea. Let's use yeasts and turn methanol into animal protein. And that would be superior quality protein to what you could get with the process I had originally outlined. And it looked pretty good. So I had them do some further analysis. And it turned out that the idea actually is good, so much so that there's a couple of companies in China that are working on doing exactly that. And the problem with that is that if we want to get investment to do it our way, that precludes, it makes it hard to get an investor unless you have something new and unique. And I asked Benner, do you think we could come up with a better approach to what they're doing to either produce higher quality food, more tasty food, more nutritious food, or have the reactor be more productive in terms of yields, or any number of other points of superiority that you might name, and or develop combinations of this with, say, aquaculture. And he said, certainly, but it would take a significant amount of work, perhaps 6 months worth of work, for his company, for example, to work into this problem and get into the real issues there and find out better solutions than the ones that are currently being explored. And the Mars Technology Institute simply didn't have the amount of funds to fund a paid R&D effort of that character in order to get the basis for formulating a business plan to seek investments and so forth. So we're going to try something else. We're offering a prize. Okay. We are going to start a competition. It's an open competition for anyone, anywhere in the world, to develop a better process for producing food from simple chemicals like methane or methanol. It's not restricted to them, although we do mention that those are the ones that we know can be easily produced on Mars and which can be converted into protein. So you're welcome to start with them or start with an alternative, provided that it can be readily produced on Mars, and do a microbial process, either as a standalone or in combination with, say, for example, aquaculture or other forms of food production, livestock, to produce an attractive form of food for use on Mars. And we're going to be announcing this contest, and there will be awards, cash prizes for first prize, second prize, etc., through fifth, and so on. And the people are encouraged to do experimental work to validate their claims. The winners will be chosen before our next international conference, which will probably take place here in Seattle as well. We will, if the process is attractive, we will offer to patent it at our expense and give the inventor a piece of equity in the company that is produced by commercializing that patent. So that is how we are going to attempt to develop synthetic food. And if this is successful, you should realize, if we can actually produce animal protein at 100 to 1,000 times the efficiency that it is currently done on Earth by growing corn and feeding it to cows, we will do something enormous to advance the human condition worldwide. Because while the cost of food, for instance, is not a major part of my budget, I'm a successful engineer, and for most people in the United States, it is no longer a driver on your household budget. It's not actually the cost of food, it's your many other expenses. To most of the world, it remains a major part of their budget, and in the poorest parts of the world, it is the majority of their budget. And if we can reduce that, we will greatly improve the lot of the people of Earth, especially the poorest people of Earth. And this will completely disprove the contention, by the way, of those who claim that these space advocates don't care about the needs of the people of Earth. On the contrary, we will show that by taking on the challenge of space in its most important ways, in terms of creating the technologies needed to settle Mars, we will address the most fundamental problem that have faced people around the world for the entire existence of the human race, from prehistoric times down to the present. So this is what we're going to do, and we would encourage everyone listening to this to wait for our formal announcement of this contest and to participate in this. Thanks. So now I'll hand it over to James to talk about our other key initiative of the Mars Technology Institute.
Yes, thank you, Robert. So yeah, today represents us kind of announcing these contests, trying to get the community more involved in Mars Technology Institute. I'm going to talk about our AI project, which we've codenamed Athena after the goddess of wisdom. Now, by this strange coincidence, my older daughter, who's 19, is also named Athena, but it's a total coincidence. But we chose the name Athena because she's the goddess of wisdom, not the goddess of knowledge. What's the difference between knowledge and wisdom? You know, we want, you know, you can go on ChatGPT and get a ton of knowledge right now, right? But is it wisdom, right? We want to have a system that is trained in the space domain. So it's almost like a consultant for you. So for example, if you were going to develop a project like this company Varda that just recently manufactured pharmaceuticals in Earth orbit, you know, they spent millions of dollars on R&D to try to get to building their spacecraft that manufactured what is it, Conavir in orbit for the first time. They successfully did that. They've now raised another 90 million for their company. If they had our system, we think they could have cut their research budget maybe in half. We want to have a system which essentially allows anybody to help develop the in-space economy. And so we started this out as the idea it would be something that could guide someone through learning a topic, but then go as deep as possible, and also be able to bring in expert knowledge as well, expert consultants beyond the AI itself. And so we've been developing this for about 9 months now this year. One of the big things we've also been learning how to do is how to talk to investors about a project like this. You know, you might not be surprised to hear that it's kind of hard to raise funds, even if you have a good idea. But if you don't have a revenue model that's going to return money back to the investor by year 3, usually big institutional investors don't want to talk to you. And so we've learned a lot in the course of developing Athena and this project, this idea, that will also help us as we help other companies get formed out of MTI. So we're kind of using Athena as a test pilot for the investment aspect, as well as developing the technology itself. Now, I don't have a ton of time to show you demos of Athena, but we have organized this afternoon around MTI. And you'll notice on the schedule that there are now 3 tracks we're going to start for biotech, AI, and robotics. Those are 3 of the 4 MTI silos that we're going after. And so for each of the track talks we have someone from the Mars Society that's going to introduce the topic. We've just introduced biotech. Next in the AI track, my good colleague Charles Finkelstein. Charles, would you stand up for a second? Charles and I worked together at Microsoft. I recruited him onto the Athena project, and he's been working hard with our developer Andy Barr on an actual technology demo using what's called a RAG, or Retrieval Augmented Generative System, that would essentially give a system like ChatGPT more specific knowledge about space, more specific domain knowledge that you can't get on Google. You know, things like what would be in a research paper behind a paywall that's not available on Google. We're going to have information like that in our system. We're going to have basically all of Robert's books, for example, all of the 400 research papers that he wrote. And we're reaching out to a lot of other scientists to also get their material to contribute into this system, so that you could essentially have an expert consultant helping you with your project, with what you're trying to do related to space. So Charles will be going a little deeper on the Athena project. in the next half hour. We also have on the schedule open discussion slots. So we're also hoping today that you, our community, can start helping us with new ideas of what we should be working on for the Mars Technology Institute. One of the things we're going to be asking for is if you guys have projects that align to what we're talking about, tell us about them. I'm also going to ask Michael Lane to stand up really quickly. Michael Lane is part of our business development team on the Mars Technology Institute. He'll be roaming around at these open discussions. And so if you want to connect with us about the project you have, or if you're just interested in learning more, talk to myself, talk to Michael Lane. We also have an intake form that we've set up. I'll throw that QR code up really quick. Go ahead, Robert.
I'm not saying anything.
Okay, sorry. There's a little audio there. So there's the QR code for the intake form. And basically, yeah, we want to start getting the community more engaged with what we're doing at the Mars Technology Institute. We've got the biotech project to create food for Mars and also to help new processes be created on Earth for food. We've got the AI project to try to build this space domain knowledge system, which we hope will expand to other domains in the future. But we're starting with space because that's our subject matter expertise. And then robotics, energy, we want to hear projects like that as well. We have a robotics track. We have Kent Nebergall, who's on the Mars Society Steering Committee, presenting on the EVA Link system. And then we have a talented young woman, Samantha Dominguez, is going to talk about robotics and some of the ideas that we think for MTI that we could do for robotics. And then we'll have that open discussion. But like I said, if you're interested in participating in the Mars Technology Institute, please reach out to us. We also do have abilities for people to donate to the Mars Technology Institute. We did our crowdfunding campaign where we raised $150,000 earlier this year. Part of the rewards for that were if you gave us more than $5,000, then we would give you a ticket to the first Series A for one of the MTI companies. You'd be able to invest first. It won't be one of the first investors and have a pro rata offering, which would allow you to get more stock than you bought in with at that time because in lieu of the donation you gave us prior. That's for accredited investors. If you want to just help us out on a smaller scale, we have lots of patches and t-shirts and other rewards as well. So we have a website, marstechnology.institute. Keep an eye on that. We'll be updating that with more news as time goes on. But we want to say, thanks very much to our community for helping us get started on this. This is the first of, we hope, a long effort to create and spawn off companies that will help us settle Mars and will help us create technologies, breakthroughs, and innovations that will also benefit people here on Earth as well. So that's basically the path we're on, and we're really excited about it. So with that, I'll take any questions you guys have.
Hey, I'm Alan Boyle. I think at one time there was talk about actually having a physical headquarters for the MTI. Is there any update on that, or do you see this really as being a virtual institute?
I think that we would love to have a presence here in Seattle. I'm from Seattle, and we've had some discussions with the community here. I've talked to some of the different mayors of Bellevue, Redmond, Kent. We actually have a really great conversation happening with Bellevue College right now, where we may come in and help them with a few things and possibly form a partnership where we can get research space or research partnerships with their school, their faculty, get their students involved. But we definitely also see this as a global project where we want to have virtual teams around the world helping us. I could see a situation where we have 5 to 7 research teams working around the world in concert in the near future on MTI projects. But it would be great to have a physical facility for a lot of reasons. And for a lot of reasons, Seattle, as you've written in GeekWire, it would be a great place for us to come.
James, I'm wondering if you could talk about possible interactions between the Mars Technology Institute and some of the other things that the Mars Society is doing or working towards right now, including MDRS, FMARS, and the Journal of Space Analog Research?
Yeah, great question. We definitely see the assets of the Mars Society as things that could be used for the Mars technology stations in the Arctic and in Utah. We could use those to test hardware or to test experiments, have MDRS crews working in the Green Hab, doing some of the experimentation for the biotech project, for example. We also see synergy with our community. Our community at the Mars Society, all these excellent technical talks we have every year at the conference, there's potential PIs and research projects there that can come in and be part of MTI. And also our worldwide chapters. A lot of our chapters have very talented individuals working in universities and companies and governments that could also be part of the MTI. And so we are hoping to leverage the Mars Society community with this project. We always think that the MTI will be joined at the hip with the Mars Society. It will eventually, the MTI, the Mars Technology Institute, will eventually be a separate nonprofit from the Mars Society, but we'll always have them joined at the hip where they're helping each other out.
James, tomorrow I'm doing a presentation on the path towards peace is through space exploration. And I would encourage the Mars Society and the Mars Technology Institute to lead the way in encouraging all nations to participate in a global program to demilitarize the global economy and work on space exploration. Because I think by having the combined space programs of all spacefaring nations and pushing technology down towards the equator so that it would lessen the pressures of migration, that the Mars Society and the Mars Technology Institute could be a force for peace in the world, because we are on the very edge of a nuclear war. And all of you are aware of this, and all of you are quite worried about it. The only way that I can think of to avert that is to combine the space programs and direct the energy of the planet outward. And I think the Mars Technology Institute, the timing couldn't be better, could lead the way in integrating these programs so you have a commonality of interest and hopefully save mankind from an absolute disaster.
Love that vision of us having the ability to do that, and I think that's a great thing for us to strive for. So thank you. Okay, I think we're past 2:30 now. So again, if you're interested in biotech, stay here. We're going to have a biotech open discussion. If you're interested in the AI project, go follow Charles over to room 250, where he's going to give his presentation on the Athena project and a little demo on the technology we've built so far. And if you're interested in robotics, head upstairs to 332, and Kent Nebergall will have the EVA link presentation, and following that, we'll be talking more about the MTI robotics area and how you can get involved with that. Thank you very much. So now that we have this room for the next half hour to talk about biotech, Robert's on the call. I think, yeah, Dr. Benner's right here as well. I think we can we have an open mic here. I'd love to hear the community, what you guys think of our idea for the Mars Food Project. What other ideas you guys may have.
Nothing this time.
And let's just have a little discussion here, shall we? So go ahead and somebody can come up to the mic here and get started.
Guess how your synthetic biology.
Hey guys.
Hey there. Thanks for the presentation on MTI. I was eager to hear about it. Specifically in the biotech track, maybe I missed it, but it sounded like you described physicochemical synthesis of food, which I wouldn't really characterize as biotech. So what other biology-oriented things are you guys planning on doing?
Robert, did you catch that question?
The question is, could, for instance, the microbes be altered by biotech to produce a superior product?
I'm sorry, I actually couldn't hear that very well. It's kind of noisy in here.
Okay, that is, could the microbes be altered by biotech to produce a superior product?
Sure. Okay. So microbially sourced nutrition. I see. Yeah, like
Yes.
sodium, for example, or other stuff like that. Okay. I think that when I had heard the rumblings of MTI in the past, when I was envisioning also a physical space, I heard something about you guys planning a closed analog facility or something with food production systems and all that. And I guess, you know, plans change as funding changes, but I was imagining more along the lines of the what kind of crops are we going to grow? What kind of protein production are we going to put in place in closed loop systems?
Well, what we're talking about here, okay, first of all, as James said, we are looking to create a physical facility. But our initial projects here at this point are spinning off businesses based on certain key technologies, of which the first two are Athena and, well, we don't have a good catchy name yet for Mars Foods, so I'll just call it Mars Foods. Even though there's a Mars candy company already. Okay. Which my father saved during World War II, but that's a story for another time. Perhaps at the banquet. In any case, the idea here is we're talking about creating technologies that radically expand what human beings can do, because this is what is going to be needed to settle Mars or space in general. And these technologies, these settlement technologies, if you will not only enable the settlement of Mars, they will vastly improve life on Earth. So, yes, so this is a technology development initiative, and which is designed to become self-funding and more than self-funding, because we aim these companies created by commercializing these innovations to be extremely profitable, and not only be able to fund more research, but ultimately create, as it were, an empire of a variety of companies spanning all the different areas that are critical for the creating new societies on new worlds. These companies will have the financial heft to fund the human settlement of Mars.
Okay, yeah, thanks for that context. And it's also a great transition to the second question I had, which is you mentioned that you were doing prizes for some of the submissions in these categories. And I'm curious to know, are these prizes sized and intended to fund the entire product development cycle or not? I was like, is this an SBIR kind of thing?
No. Okay, the prizes. Okay, you see, if I could just fund the development cycle, I'd fund the development cycle. The purpose of doing things with prizes is to, by offering basically eternal glory to the winners, is to incite an amount of activity that is greatly in excess of what you could pay for it yourself. I mean, look, every year we have the University Rover Challenge contest, in which 30 teams bring rovers to the desert, and they probably at least are spending, $10,000. So that's $300,000 worth of R&D work creating Mars rovers for testing in the desert, and we spend less than 5% of that ourselves on the prizes. The X Prize that Peter Diamandis sponsored, which offered a $10 million prize, the winners spent $50 million to win it. The prize that Charles Lindbergh won, crossing the Atlantic, which I think was $50,000, if I remember correctly. But it inspired millions of dollars worth of work advancing aviation. So no, we are not going to offer a prize that pays for 6 months of R&D. We're offering a prize that there'll be a cash prize, there'll be a trophy, there will be an international public announcement, and there will be a piece of the action in terms of the equity of the company that is built, because we will spend the money to patent that technology. Okay, those will be the rewards. Now, what we're hoping for example, is scientists who have university laboratories at their disposal, or even high schools have laboratories with glassware and thermocouples and incubators and all kinds of things that or amateur scientists who have a certain amount of facilities of their own will apply themselves to this thing to try to win this prize. And yes, they will win an international prize. It will win great renown. That will be of use to them in all their future endeavors, whether we're talking about young people who are trying to get into college, or we're talking about people who are trying to make a career for themselves. We're offering, eternal glory for doing a truly great deed, and a deed more consequential, for instance, by far than many of these other prizes that I've mentioned. That's what we're offering.
All right. Thanks for your answers.
Patrick. Come on up to the microphone. Anyone who wants to talk, just come on up to the microphone.
Today. So Robert, we may have some experience you might find useful, because we've been running the space health contest at the NSS, as you may know, for a few years. And most recently, we got good promotion, we had good participation, but the students make mistakes, okay? We were very free form about it, and they said, design an ag module for us. However you go about it, if you want to bring cattle into space, you can do that. If you want to synthesize food, you can do that. Use bioreactors, whatever it is. Okay, but the problem we saw was that they knew very little about nutrition and what features the synthesized food should have. So they pretty much ignored carbohydrates, and they pretty much ignored other things. We know if you look at Robert Lustig's book, Metabolical, there's a whole compendium of things that are good and bad for you. So just a heads up. I'm Dennis.
Hi.
It's nice to meet you.
Okay. I have to.
Did you hear anything I said?
Want to mute there, Robert?
Yes, I did. I just a visitor arrived here who I'm meeting with at 3. But please go on.
Okay, so maybe I should repeat something I said, because we've been running a space health contest at the NSS for the last few years. We upped it considerably, got promotion going. Then last year, we had about 225 participants and maybe representing about 500 students. Are you talking to somebody else? He's talking to somebody else.
I can kind of answer your question, William. I mean,
Oh, okay, sure.
Yeah, I think that we're trying to structure this contest and any other community calls that we do to be very specific about what we want to get back. I think that's kind of what I'm hearing you say about how you organized your contests. You gave the students a lot of flexibility and leeway, which is probably really great for their creativity, but not great for getting back a standardized set of results.
That's true. We did that the first 2 years, and we got 2 participants. Well, we made it very specific, and you have to be low carb and seed oil free and all this stuff. And we got postgrads, and they were good. But the students, the younger students, like the 8 to 15-year, 18-year-olds, didn't get it. So they were high carb, 55, 60% of the calories from the carbs, and that kills astronauts as well as anybody else in the long run. So I'm glad to hear you say that.
Hey, hello again.
Hi there.
Robert, you referred to how the Chinese were doing something similar to what you were thinking of doing, and the issue was, well, can we do it better? Could you provide a few more details or pointers to what they're doing so that I can get a better idea of what the plan is?
Well, the plan is, okay, what the plan was, was to use a kind of yeast to metabolize methanol to create a form of edible protein, essentially equivalent to Vegemite, and which is quite edible, especially if you're Australian.
Vegemite. So, yeah.
Yes. But so, and, you know, Benner and his people did the chemistry and said, this looks like it's going to work. And so then they did some literature search and said, yeah, it does work. And in fact, it's being worked on by some Chinese companies. So that if we wanted to get a foothold in this field, we need to do something better than that. And we don't know what that is yet. And that's why we're opening up this contest, because we're going to offer a prize for somebody who comes up with something that takes a significant advance on that approach. It's fundamentally a sound approach, but I think it can be greatly improved on. And we're going to be offering prizes for those who contribute such ideas. And this is going to be an international contest. People from any nation can participate, and the winners are going to get international renown. And if we're successful in building a spin-off company based on their ideas, they'll get a piece of the action.
Can companies participate?
Yeah, I just, someone who's right here in the room with me just asked me, can companies participate? And the answer to that is yes. Companies, schools, individuals, okay, can all, infantry battalions, anyone who wants to participate in this contest can participate.
I had a very similar question, and I think you already answered it, perhaps. I was curious how much the MTI has reached out to companies that already participate in this kind of research. I can think of two from my past life in oil and gas who are looking at transforming carbon dioxide and methane into animal products. There's a Caverdi and String Bio, but you've kind of already answered this question to some degree. I guess.
Well,
Yeah.
basically, here's the thing. We intend to become their competitor. So we did some literature to look at what some people were doing. And there were various reasons why Benner and his team converged on methanol as the feedstock and yeast as the microbe. And that is superior, for instance, to methods of using methane as the feedstock, even though methane would be easier to make on Mars than methanol. Methanol is not too hard to make, but it's already partially oxidized, and you don't have, with these processes that use methane, and there are people doing that, they actually have to mix methane with oxygen at high pressure in order to create the medium, and this creates certain issues. Because you're creating an explosive mixture in your reactor, but and there are other issues as well in terms of the quality of the product. But the point is, it's been my experience, for example, I led an R&D company, Pioneer Astronautics, for 27 years. And what you always find when you actually get your hands dirty with any particular problem is that you find better ideas than those you had when you first went into it. We need to get some action right now of a lot of people getting their hands dirty, and whether it's on this particular methanol and yeast idea or something different, or a way to do it from methane, or a way to do it from something else, or hydrogen and CO2. We want to have a lot of people getting their hands dirty, and we want to see what the best ideas that the community comes up with. And then what we can do that many of these people wouldn't be able to do is find investors and create a company around this idea. To do the patenting, to do the business plan, to do the rest, and once again give them a piece of the action of this, so they get, well, first of all, as I said, eternal glory, but not just that, the satisfaction themselves of having done something truly material in advancing the human race, both in space and on Earth, and in all the ways that we've described. So that's what we're going to do. And then and what they're also going to do is provide one of the two major financial props that is going to get the Mars Technology Institute off the ground, by the other being the Athena program that James Burke is spearheading right now with Charles Finkelstein and some other people on their team.
I think one area the MTI should focus in regards to its biotech and also robotics programs is trying to establish some sort of connection with universities located in extreme weather conditions, like in the Arctic and whatnot. For instance, I spent a lot of time with the University of Alaska Fairbanks, where it reaches -40 and sometimes lower. But overall, in trying to establish that level of food production, as mentioned with the contest, and it would also help with robotics because areas like the Alaskan interior and northern Canada experience temperatures during the winter that are quite similar to ours. The way to do that would be to establish connections with universities in those extreme environments, like in the high Arctic, and to eventually establish headquarters there in one of the cities or high population density areas in the Arctic, to be right in that those level of conditions and to be able to test those innovations on the ground, so to speak.
I mean, as you may know, we do have a research station in Canada called the Flash. We do have partnerships with the tribal government up there, and we are reaching out to the university, tribal university, as well as connections we have actually we have connections at Fairbanks that you just mentioned as well. I think that's a great idea, and I think it's definitely something. Robert, did you have any comments on that? You're on mute. You're on mute, Robert.
Yeah, okay. No, I agree with what you just said. And working with universities in general, and in particular, those that have some acquaintance with extreme environments would be very valuable. And I actually was talking with someone from Fairbanks last week, as I recall. And he brought up the issue that here's Alaska, which is not independent in food. If there ever should be a cutoff of transportation between Alaska and the rest of the world, people up there would starve. So if for instance, I mean, if we were to create this synthetic food technology, Alaska would be able to produce its own food quite easily. And because basically, for instance, the process that I just outlined is a fuel to food technology, is basically what you're talking about. People found, the ethanol program of turning food into fuel objectionable for a number of reasons. This does the reverse. And since we know how to make fuel, or in Alaska, they can just drill for it. But we know how to make fuel on Mars, such as methane, methanol, or other fuels that could be made by the Fischer-Tropsch process. If you can turn that stuff into food, you're way, way ahead. Because once again, you're getting past the inherent inefficiency of photosynthesis, which compared to most chemical engineering processes is actually quite low.
Thank you
very much for that.
Hi, I had a suggestion for maybe some future contest. This just comes from a background of in 2005 and 2009 receiving some grants related to bioregenerative life support systems, and also being a member of Gene Labs, some of Gene Labs analysis working groups. I'm not seeing a lot of data out there on what's going on in the microbiomes and aquaponics and hydroponics systems. And if that was going to be a product, I'd like to see some more data about what's going on with the bacteria, what's going on in these systems, so that we could build some kind of expert system to help diagnose health issues. And again, if you're building a control system for a bioregenerative life support system, omics in the toilet is going to be one of the most powerful tools for diagnosing health of the astronauts in the whole system. So, just a suggestion, anything you guys can do to get that, and scientists.
I think the approach we're taking of starting with the synthesis of the food from the fuel could easily build a process beyond that to then feed that new food to fish and have the humans on Mars eat the fish, for example. We actually talked about that, but you're right. Like aquaponics and that closed loop bioregenerative life support is definitely a holy grail of the Mars community. Whatever we could do as part of MTI to help advance that, I think we will. Robert, did you comment?
Yeah, look, no, and in fact, that's a viable entry into the contest, because if you had an efficient way to use an aquaponic system to upgrade the Vegemite into tuna, or salmon, you know, that's of some interest. I mean, one problem you see with aquaponics on Mars is that the basic biomass that feeds the aquaponics on Earth, it all comes from photosynthesis. On Mars, once again, if you're trying to do that, if you want to use natural light, you got to create greenhouses to create illuminated land, or otherwise you're using artificial light, which becomes incredibly power costly. I mean, if you think about 1 hectare of land on Earth, okay, a hectare is 100 meters by 100 meters, so that's 10,000 square meters. And you take the fact that sunlight is 1 kilowatt per square meter, okay, that's 10,000 kilowatts. That's 10 megawatts of power is actually illuminating 1 hectare of land. I mean, that's incredible, right? That is the amount of 10 megawatts is the amount of power to power a town of 10,000 people. Okay, that's how much sunlight illuminates 1 hectare. Okay, so to provide that with electricity to illuminate the farmland of the state of Rhode Island, we would need, with light bulbs, we would need more electricity than the United States produces. So that's not an option. But actually, to produce the amount of food needed for 10,000 people, well, it's about 100 watts per person is the amount of metabolic food that you eat. And anyway, one could go down this, but the point is, aquaculture combined with a chemical synthesis process is a viable concept that could be considered in the contest.
Thank you.
Any other questions or comments? I mean, if you guys just want to give us advice, we'll take it.
Hello, Robert. I thought I'd say hello. Right. I have a worry, I guess it would be. For example, what if MTI is successful in one or more avenues of pursuit of excellence, whether it's bio, AI, or whatever? When it becomes known that you are successful in any field of your endeavors, what's going to happen? You're going to get big institutions or governments want what you have. So what do you have in place to protect yourselves? Because they're going to want to walk all over you and take everything you've got, because governments and institutions are getting desperate these days. So do you have, I guess everything is going to be patentable?
We'll patent what we can, but sure, you know, look, but this is the challenge that any successful company faces, and you need to face it, you need to deal with it. And it's a problem I'm looking forward to having.
Good.
I would also say that the model we have is that the MTI itself will remain a nonprofit, will keep equity in startups, and it will remain independent. We could start a company out of MTI like Athena or Mars Food, and some corporation could buy into it and become a majority or minority owner. But the MTI is not affected by that.
Great. So do you have like a board of directors and a charter to say, this is our goal, this is how we're going to go there, and we will keep this ethos from now until whenever? Do you have that already in place?
We have a deck that we used for the crowdfunding campaign that lays out the model here, and I'm be happy to share that with you.
Okay, great.
We're in the process of incorporating these things, but currently that's
Good. I just wanted to see if there was any protections involved because I didn't want, because someone's going to steal your good ideas. I just wondered if you just had any way of protecting yourselves.
I think we'll fully leverage the IP laws of the United States.
Good luck with that.
Hello, Robert. Hi, James. Quick question. When you're doing the competitions, are you looking for teams that are at a certain level? For example, like maybe you have a team of 5 and they have a really good idea, but no one has the capability to put it into play. Is the advantage of working with the MTI Mars Technology Institute is that if they like your idea, would they pair you with people to help further it, or should you come in with like an idea and with people already with the expertise to go further? Like, am I making sense? That's my question.
There's multiple ways we're going to work with the community. So for the competition we announced today for the Mars Food Biotech Project, we're going to be very prescriptive of what we're hoping to get help on. And that's open to anybody at a university who's independent, who's at a company. Help us do that if follow the prescription that we're going to put out as part of this contest. Now,
Right.
and we definitely want to work with everyone. I mean, we're not limiting ourselves at this point.
Right, but we will have both the general prizes and we're going to have prizes like a special prize for schools. Because we view this as a tremendous STEM initiative as well. Okay, in other words, getting large numbers of young people involved with biotech as they, for instance, attempt to upgrade the microbes to produce a better product. And we believe that we can get some corporate sponsorship for this because the value of this incitement of young people to become scientists through participation in this contest is tremendous.
Thank you so much.
So it's 3 o'clock now. We're going to shift into the next presenter. So thank you very much. This was really a great experience for me and Robert. Thank you.
Okay, right. James, I have to sign out now. But for anyone who wants to speak to me, I'm up on the 3rd floor. Okay, bye.
Bye-bye. Okay, and our next speaker is Chris Temby. Your slides are on here in Dropbox somewhere. This one. Yeah. Okay. Yes.
All right, let's see. Can you guys hear me? Yeah, sounds good. Okay, nice to be here. Really, honestly, a great honor. Very excited. So today I'm going to be talking about the Agnostic Life Finder, which we call ALF, a little bit of a backronym to the 1980s sitcom. I'm really happy that Dr. Stephen Benner was able to give a talk about an hour and a half ago, so that there's a little bit of context already out there, so I don't have to go into a bunch of nitty-gritty about some of the science that we're working on at the Agnostic Life Finding Association. So that being said, I want to mention, I want to thank the Agnostic Life Finding Association and also the Foundation for Applied Molecular Evolution, Alpha and FAME, for having me here. And also a specific thank you to the NASA Innovative Advanced Concepts Program, so NIAC, for funding the development of the Agnostic Life Finder. And they always say, deliver your message early and often. So the Agnostic Life Finding Association wants you. We are a nonprofit looking for volunteers, scientists, engineers, marketing, all sorts of things. We have a small team, but we're really looking to expand. So if any of the things that Stephen Benner and I have said, piques your interest, definitely get in contact. Okay, so the first question we have that I want to bring up is, why do we think that life on Mars is likely if we're going to be looking for life on Mars? Also, I want to note that there's a few formatting issues, like, for example, why all my bullets are ones. I worked on a Mac and then exported to Microsoft, and they hate each other, so just bear with me. Okay, anyway, so why do we think that life on Mars is likely? This is the most amount of text I have on a slide, so again, bear with me for a second. This is a quick synopsis of some of the history of the search for life on Mars, essentially. So in 1976, we sent life detection experiments with Viking, which are still the only of its kind. And these results were misinterpreted, as I said before. But essentially, the consensus was established that life was not detected. But in the 50 years since Viking, right, we've learned an incredible amount about life on Earth, the sort of limits it can withstand, and also about Mars. And how there was potential for a much more Earth-like environment on Mars in the past. So in 2019, see, there's another formatting issue with that box, upsetting me, but that's okay. In 2019, the Carlsbad Conference essentially concluded that there was a realistic possibility that Mars hosts indigenous microbial life, and they listed the subsurface as an important place to search if we were to search. And so that being said, the fact is true that the surface and the near subsurface on Mars is the only extraterrestrial astrobiological target which will be impacted by human presence in the coming decades. And there was a white paper by Carol Stoker, who is at NASA Ames, titled "We Should Search for Extant Life on Mars in This Decade." And that was co-signed by over 80 astrobiologists. And essentially this paper called on the community to seek extant life on Mars as soon as possible. And we definitely agree at Alpha with this sentiment. A couple other things I want to mention about, why we think that life on Mars is likely. This photo keeps showing up everywhere we all look, I'm sure. Chiava Falls, another example of how the conversation about life on Mars is, maybe 20 years ago it was argued that there wasn't life, and that was the consensus. But now, the paradigm is starting to shift. Even recently, there was a workshop which I was a part of, which was essentially discussing the important steps before human missions to Mars. It was called the Science and Planetary Protection in Advance of Human Missions. It was a workshop organized by NASA. And the biggest takeaway with the people there was that we need an extant life search before humans arrive, which is great for the Agnostic Life Finding Association. NASA has recently started to pay attention to the issue of having an unexplored Martian biosphere. And now they're working to make up time and organize an extant life search before humans arrive. And again, that's great for us, and we would really love to spearhead this endeavor. I asked a question earlier to Tiffany Morgan about a Mars-like version of CLIPS. So hopefully there's a way to take what we learn from the commercial lunar payload services and be able to do the same thing at Mars with efficiency. Okay, last thing I want to talk about with life on Mars before I get into some of the stuff that we're working on is this is a paper that was published by those people listed above. A couple of them are actually a part of the Alpha Mars project, essentially talking about low organics and life detection limits. And so what I've highlighted from this abstract here is that with the state-of-the-art laboratory equipment, extant and ancient microorganisms can barely be detected, and that with the instruments that are on or will be sent to Mars, it shows extremely difficult or impossible detection of those sorts of things that we're looking at. So clearly, if we're going to do an extant life search, we need improved resolution and also alternate search methods. And for point 3, I would probably say we need to do it urgently. Okay, so now what is ALF? ALF is an add-on to large-scale water mining operations on Mars to screen for introduced and alien life. It's not a mission by itself, and I also want to note that it is a concentration device. It's not actually an analytical device. But as Dr. Stephen Benner was talking about previously, essentially, we're looking for these polyelectrolytes in the stream of water, and we are isolating and concentrating those polyelectrolytes. And again, I want to thank the NIA program, NASA Innovative Advanced Concepts, for phase 1 funding to develop a field testable prototype of ALF. So that's great. Okay, and ALPHA is also currently under development by students under the guidance of Jan Spacek at the Foundation for Applied Molecular Evolution in Florida. And the goal is to develop a field testable prototype. And you know, since we're at the Mars Society, I want to give a shout out because you know they support us, and that's been a fruitful connection there, and I think it will prove to be so even more so in the future. You know, there's potential to do some field testing with the Agnostic Life Finder at the FMars location, but yeah, I just wanted to thank the Mars Society for their support of us. Okay, so if we have the Agnostic Life Finder, can we detect life on Mars agnostically? So we use, the basis of the Agnostic Life Finder is basically two theories. One is the lasagna ice theory. Essentially, it's fairly clear that there's subsurface ice on Mars, much like on Earth. Well, on Earth we have surface ice as well, but there are glaciers with this ice that hold geologic records of many things, geologic history, but also microscopic life forms. And via aeolian transport, which basically just means wind transport, there are global Martian dust storms, which encompass the entirety of the planet and deposit contents from around the planet into these glaciers. So therefore, the entirety of the planetary surface is exposed. The subsurface ice is exposed to the entirety of the planetary surface over geologic timescales because of global Martian dust storms and aeolian transport. So this global cycling reduces the likelihood of sampling the wrong location, making it an agnostic search technique. So that's the where and the how of agnostic searching. So for the what, well, kind of as Dr. Stephen Benner was talking about earlier, instead of looking for biosignatures that might be produced by life, ALPHA is searching for biomolecules that are necessary for life. And that gets into the polyelectrolyte theory of the gene. Again, lots of similarities with Dr. Benner's talk and I. But if the polyelectrolyte theory of the gene holds true, then all life must contain informational biopolymers, which are used for heredity. You and I have DNA. These are linear molecules with repeating positive or negative charge, and they carry genetic information encoded in the sequence of their building blocks. So again, we have DNA, A, G, C, T, with the repeating phosphodiester backbone. And if we're looking for these sorts of polyelectrolytes in the Martian subsurface ice, we don't care whether it's A, G, C, or T, X, Y, Z, and O, right? What's important is that we're looking for this repeating charge on the backbone. We have a repeating negative charge shown in the animation at Dr. Benner's talk. If there's a positive charge for the polyelectrolyte on Mars, we would also be able to isolate, concentrate, and downstream analyze that as well. And then, let's see, I'm not sure if I read this last line, so I'll read it. Polyelectrolytes with a repeating charge, as I just mentioned, and non-repeating sequence of building blocks are the only theoretically universal and unambiguous biosignature that ALF seeks. And there's lots more science and justification for these arguments and the polyelectrolyte theory of the gene, but I don't necessarily have all the time in the world to get into it, and it becomes a convoluted conversation. But these sources, I'll go back one second. On the bottom left, that's a photo I took while I was working and living on a boat in Thailand, reading Dr. Benner's book, Life, the Universe, and the Scientific Method. And that's on the left there is the justification for the polyelectrolyte theory of the gene. And then again, the Agnostic Life Finder, that paper is findable online. Okay, so now that we know what ALF is, what is the mission? So our mission is to integrate a fully autonomous ALF unit to offer to any and all entities planning to mine and melt water on Mars. This will monitor forward biological contamination and allow for the scientific investigation of the largest astrobiological target ever collected on Mars. That's a bold claim, so I'll back it up just slightly. There's plenty of science to be gained by looking at rock cores from Jezero Crater, even 20 or 40 of them. But if we are to be mining up to hundreds of tons of Martian subsurface ice. That's quite a large search space that we should be taking advantage of. And so we're targeting 2028 for this goal to have a fully autonomous ALF unit. And you know, the objective would be, for example, to start with Honeybee Robotics' Redwater Rodwell system. But regardless of who or what is going to be mining ice or water on Mars, if they want to look for life, then we plan to offer the Agnostic Life Finder to help them with that. And what's clear is that ISRU, or in situ resource utilization, will be necessary for large-scale Martian infrastructure. And even regardless of large-scale Martian infrastructure, it seems pretty clear that the scientific community wants to be looking for many things, let's just say that, in the subsurface ice. Okay, another example that I want to point out is by looking at SpaceX's plan to establish a permanent private presence on Mars. I mean, this is just straight from their website. This is their plan to get people on Mars. Step 5 is the important one, and it's talking about using Starship, refueling Starship with local resources of H2O. And again, our objective is to basically put our instrument on that stream. So after the mining is done, but before the industrial manufacturing and processing is done, why don't we search some of that water for signs of life? And you know, it could be 5%, 10%, 1%, 0.1% of the water they mine. But again, it's that amount of water would be a very large search space compared to what we have had access to in the past. Okay. So finally, what's the justification for alpha? And before I do that, there's a quick asterisk. I'm going to tell you about why I'm the one telling you about it. So I'm Chris. I went to UCSB, graduated with the degree in physics, studying with a minor in astronomy and planetary sciences. I'm an explorer, hiking the rim of the Long Valley caldera. I also am a pilot, explore high and low. And what do I do? Well, I am the president of the Agnostic Life Finding Association. There's another formatting error, hurts my eyes, that's okay. I work with Gabby Rizzo and Courtney Pasternak. They're great. And I also worked at the Foundation for Applied Molecular Evolution, developing the earliest prototype of the Agnostic Life Finder and also some of its early research models. And yeah, there I am in the lab as well. Okay, so now what is the justification for alpha? Okay, so Alpha is a 501c3 nonprofit research organization doing astrobiology research in Alachua, Florida. And we are administering an international group of scientists who believe we should be looking for extant life on Mars. And the mission statement is to determine to a high degree of certainty whether or not Mars hosts an active biosphere before humans arrive. Okay, and what's important to note is that Alpha is the only entity dedicated to looking for extant life on Mars. And, you know, again, while the paradigm in the community, especially, you know, through NASA, has actually started to shift even within the last year, pretty much 365 days ago, if someone were to tell me that actual NASA headquarters said that we should be doing a search for extant life on Mars, I probably wouldn't believe you, but you know, here we are. So I'm happy that the paradigm is changing, right? Obviously, so we don't have to kind of swim upstream. But that being said, you know, we are dedicated to looking for extant life on Mars, and we really want to spearhead this endeavor. Of course, you know, with the support of the community and of course the support of NASA. Okay, so let me also note that it's not required to have the support of NASA, since you know we are a private organization. It's possible to. Anyways. Okay, so the Alpha Mars project, or Alpha, will utilize international collaboration. So if you look at the Alpha Mars team, we have scientists from all over the world: USA, Canada, Spain, Argentina, and the list continues to grow. And also, we will utilize a growing private space industry where capital investment continues to rise, reduce launch costs where the cost per kilogram has reduced significantly thanks to the reusability of SpaceX's rockets, you know, and other players out there in the future, and We will also utilize widespread public interest in extraterrestrial life. There's plenty of movies to suggest that the public is interested in looking for life out there. And also funding from public and private sources. So crowdfunding campaigns, and hopefully we get lucky with some venture capital or philanthropists. And then of course, government funding, NSF, NASA, ESA. And so we will utilize these things in order to fund astrobiology research and provide life detection instruments that want to fly them. So I've already kind of talked about the second one, which is the life detection instruments. So this is focused more on ALF, but we have ideas for projects of a wide range of a wide scope of objectives to develop life detection instrumentation. And so that's for that conversation for a different day. So let's talk instead about number one, which is funding astrobiology research. So currently in 2024 with NASA funding, I already mentioned the NASA Innovative Advanced Concept Program, NIAC. We have phase 1 funding to develop a field testable prototype of ALF. And of course, we will seek further NASA funding for this project. And in parallel, through our target date of 2028, we're running a fundraising and a marketing campaign to fund further ALF development and testing. And as a nonprofit, we ask that you please consider donating, getting involved. And there should be more on that slide underneath, which I don't know why it's not there, but if there's our website, www.alphamars.org. But even if you don't feel like donating is your best way to help our cause, like I've said before, we're more than happy to have scientists, engineers, volunteers, and if you'd rather just stay involved, stay up to date but not be involved, you can also join our emailing list. If you just check out our website, there's a way to get on the email list. We send one email maybe every 3 or 4 months, so it's not like we're spamming you. Okay, so in a world where we have we have lunar landers landing upside down. That's JAXA's SLIM lunar lander. And we have lunar landers landing upside down and lunar landers limping to the finish line. It's clear that space is hard, especially for private organizations. But what's clear is that we're going to Mars, and we should be going. But Alpha agrees with this paper from Stoker et al., saying that we should search for extant life on Mars in this decade. With the Space Race 2.0 is on, right? I mean, NASA Administrator Bill Nelson has said this, and there's many actors, China, NASA, and SpaceX, to name the most prominent 3 that have plans to get humans to Mars. It's clear that we're going. So with the money being invested in the geopolitical goal clearly stated, we are going. So I'll see you there, and I'd love to take some questions. It's on. No questions? Oh, one question. Woohoo!
I was wondering what's the analysis part, because you mentioned it's only a consultation device. What's planned there?
Sure, yeah. So the question was what sort of analysis would be done with these polyelectrolytes. The jury's definitely still out. Good options are some sort of min-ion sequencer. I mean, there's probably going to be a multitude of different analysis techniques. But yeah, I mean, sequencing and also some sort of mass spec in order to determine essentially the complexity of these biomolecules that we would be concentrating. Does that make sense? Okay, next.
Hello, my name is Lawrence Warnock. Wanted to ask you about sterilization. So
Sure.
Obviously you're looking for kind of the products of life, but you don't want to introduce life. What's your protocols for that? My second question is, when you were in Thailand, were you on a liveaboard? And I recommend Indonesia. Head down there.
Okay, so the first question was about planetary protection and sterilization. Yeah, we will definitely be adhering to all COSPAR requirements. Yeah, I mean, we don't plan on if the objective is to search for extant life before before humans contaminate a Martian biosphere, it would be counterintuitive to contaminate it ourselves. So yeah, we're definitely taking that into consideration, and all all requirements that exist we will be following. And the other question was about Thailand. Yes, I was working on a liveaboard boat off the west coast in the Simoleon and Surin Islands, and I've been to Komodo, and the diving in Indonesia is amazing as well.
Interesting talk. I liked the thinking behind it. For implementing the sample capture and processing, have you looked at different sizes and scales of doing that? Like small ponds versus large processing volumes that are being fed to some industrial process. What scale have you tested it on so far? Or have you tested it on existing DNA that we do know about?
Yeah, so currently it's a tabletop, maybe about the size of the computer. That's currently the scale of the prototype we're using. And again, since we're in the process of developing the field testable prototype, we haven't gone out to test on pond A versus pond B. We have at the Foundation for Applied Molecular Evolution, they have plenty of DNA, single strand, double strand stuff that is just in the lab. So we have a flow through system that we just basically dump in our DNA, if you will, and then we can separate it from that. But yeah, I mean, ideally we could make it autonomous, scale it up, and then it could be quite large. But it doesn't necessarily have to be. I mean, it just depends on a lot of things. But yeah, I mean, it can be small, it can be big. Yeah.
I was curious, do you have any idea of like the ratio of like the total amount of what we're looking for compared to like how much you're thinking that the alpha will be able to capture?
Sure. Yeah. So the question was essentially, how, if I understand the question correctly, it's how much do we need to look to get the minimum amount required, right? So the beauty is that, as I said, it's a concentration device. So even if the concentration is quite small to begin with, if we are able to filter through enough, oh, it's pretty far back here. If we're able to filter through enough of the water, then it doesn't matter what the density of the microorganisms in that ice are, right? Or what the density of the polyelectrolytes are in that sample. If it requires, one ton of water, which is quite a bit, but after enough time of this flow through and concentration, then yeah, we should be able to recover even the smallest amount of density. All right, looks like we have a follow up here. No worries.
So you're saying that you'd be like running it through and then running it through again, or?
No, so if there's, for example, one cell in 100 liters of water, and right, so one unit of thing we want to find in a large amount of water we have to filter. If we filter 100 liters, then we are able to concentrate that one. And if we keep doing the next 100 liters, eventually we'll have concentrated from a very dilute original volume to a more concentrated final volume. But we wouldn't run that 100 liters the same time over and over again. It would be new water. Does that make sense?
Yeah, thank you.
Yeah. Any other questions? Yeah, definitely come find me. I'd love to talk to you guys about all sorts of things. Thanks.
Okay, do we have our Interstellar Labs people here for the next presentation? We're just going to take a quick 5-minute break, try to figure out where our next presenter is. Is Jay Garg here? Okay. All right, yeah, we'll just take a 5-minute break. Hopefully we'll have something again for you soon. All right, everyone. We haven't been able to find our representatives from Interstellar Labs, so we're going to be taking a break here just for this next half hour until 3:30. or until 4 o'clock, and Jay Garg will be presenting here. If you guys wanted to check out, they're doing a VR demonstration up on the 3rd floor if anyone's interested in that. Thank you. All right, everyone, we're ready to get started in here again. We'll be having Jay Garg speak to us on harnessing the power of biostimulants. So, Jay.
Hello. Good evening, everyone. Thank you for being here. Thank you for being here. So glad to see everyone. Today we are going to talk about harnessing the power of biostimulants. I'm the director and co-founder of Easy Harvesting. We at Easy Harvesting work towards developing the future of biostimulants, which is a new category of plant food, which does not provide nutrients to the plant, but helps absorb nutrients. So recently in March of this year, me and my co-founder, we filed patent for a new multi-component plant growth enhancement nutrient system. In simple words, it's a three-part solution composed of micronutrients, macronutrients, along with biostimulants. Biostimulants is the key component here because from our results and testing in the experiments, we found that with biostimulants, we are able to expedite the growth of plants using less fertilizers and water. So I think if something can work on Earth, can potentially work on Mars, Moon, and even further. So with that mindset, let's look into what we are going to discover today. First, we need to understand that mankind has to achieve a few milestones before we could even understand or even make this a reality of growing plants on Mars. So we need to look into the timeline for growing plants on Mars. What are the milestones and what timeline it looks like? Next, what are the challenges that you will see when you try to do farming on Mars? And how does biostimulant plays a role in overcoming those challenges? Along the lines, we'll also look at a very interesting study in which the researchers tried to grow plants on lunar soil and they were successful to grow, but there were some challenges. And then theoretically, how could biostimulant overcome those challenges when trying to grow similar plants on lunar soil or even Martian soil? We haven't found the samples yet, but by 2033, we are expecting to get there. Finally, we would also want to look into what are the unit economics of growing plants in Mars. And finally, what are the pharmaceutical applications of plants on Mars? So the timeline for growing plants on Mars, as I said, require some mankind milestones to be achieved, starting with the establishment of Lunar Gateway, which is going to be the main base camp on Moon from where the astronauts and other researchers are going to do experiments and also try to go beyond Moon to Mars and further. That is expected to be done around 2028. Following that, SpaceX is planning to have an unmanned cargo mission to Mars by the year 2030, followed by exploring the first Mars base alpha location finalization by 2032. Around the same time, we are also expecting the Martian soil to be received by NASA from the Perseverance rover, which which landed in 2021. It is around this time that the startup ecosystem would accelerate. We would see a lot of companies realizing the potential of making this dream into a reality of growing plants actually on Mars. And that's when the commercial race of growing plants would begin. By 2034, we are expecting the arrival of unmanned Starship by SpaceX to land and make the first base construction. And by 2038, the first crew mission to Mars, right? By 2038. And then by 2040, we will have the first human residency at the Mars base Alpha. They're expected to stay there full time. Yes, full time, and then explore the possibilities of colonizing Mars. So we're talking roughly a timeline about 20 to 25 Earth years But believe me, this is just 10.5 Martian years. So the future is very close and exciting. Of course, there are going to be challenges, right? And the best way to overcome challenges is to understand them as good as we can. So I've highlighted broadly into 3 categories as soil. By definition, soil is something that needs to have organic matter. And Martian soil does not have organic matter. That's one of the biggest problem with Martian soil. It has about 95% of highly mineral substances, which are really good for the growth of plants. But one of the substance, which is the calcium perchlorate, is the most dangerous to process by plants. It's easily consumed by plants, but it makes the plants toxic, which is not good for humans. But it's also been found that just by using water to wash this off from the soil is possible. But again, the question is, where do you get water from? We'll explore in this presentation how we can solve this problem with biostimulants. The next challenge is gravity difference. The plant species that are grown on Earth have a different gravitational adaptation compared to what it would be on Mars. There's about 38% less gravity on Mars, which would make it very difficult for these plant species to have a stronger root anchoring, which is going to be a challenge because with weaker root system, you would have stunted growth in plants. And what about the sunlight? Mars is actually a very cold place. The amount of sunlight you receive on Mars is about 60% of what you get on Earth. And not just that, due to the longer nights and the dust storms, the amount of sunlight you receive could even be hidden for days or even weeks. So that's a big challenge as well. Without sunlight, how do you make sure that your plants are growing properly, right? It's a problem in Seattle itself. What about Mars? What's the solution to this? Or let's say, what's the potential solution to this? I say it's biostimulants. And you ask, how? So let me tell you. The image that you see here on the screen of the untreated and treated plants is actually comparing the biomass which is produced by the plants in the controlled environment with treated being the one that have biostimulants added to them and the untreated are grown regularly without any biostimulants. The nutrients added to both the samples or both the control groups are equal. The only difference is addition of biostimulants. Now, what actually biostimulant is? It's a very sophisticated combination of shoot hormones, root hormones, and vitamins, which enables the plants to develop its transportation system, whether it's water, nutrient uptake, or even volatile organic components, which makes it robust against abiotic stress. How does shoot hormone works here? Shoot hormone actually stimulates the cell division in the shoot meristem. The shoot meristem is analogous, or just meristem is analogous to human stem cells. When you have an expedited growth of meristems, what you're doing is activating the expedited growth of stems, roots, leaves, fruits, anything that's part of the shoot. Now with this, you're not only just increasing the growth rate, but you're also delaying the aging of the leaf. What does that mean? In layman terms, it's called as the perishable lifespan of the plants. That means a lettuce head, when you harvest, grown regularly, would go bad in about 4 to 5 days. But if you're using biostimulants along with this, the perishable lifespan of this lettuce head will go beyond weeks, which is amazing, which is required because now you're making your plants more robust to the abiotic stress. How does root hormones come into the picture? Similar to the shoot hormones, the root hormones help in the lateral development of roots. Roots are important for the increase in the uptake of water and nutrients. And this is heavily influenced by the gravitation. So in the case where the gravitation is 38% less on Mars, this plays a very important role for the plant development. Finally, biostimulant provides a platform for all the other nutrients to perform a synergic effect of vital nutrients like zinc, magnesium, and copper. These nutrients or these ingredients have an enzymatic function and stress response mechanism, which enables the plants to fight from the abiotic stress in harsh conditions. Let's actually look at this quick video that me and my team actually made. So,
Not have the sound.
yeah. So in this, we are actually trying to explain in a very simple and animated way how the biostimulant works. This, what you're seeing, is a regular earth condition of plants growing in soil with organic components. Our biostimulants have root hormones and shoot hormones represented by red and yellow. When you apply these biostimulants to the regular environment, the hormones start distributing to the respective areas. This is just nature. Now, how does root hormone works? It enables the growth of meristem cells at the root, leading to cell division, elongation that you're seeing here. And then finally, the shoot hormones present around the root creates the differentiation for the root cells. The same thing happens at the shoot as well. Here we are focusing on the apical meristem cells, which is being targeted by the biostimulants. The same story is for the shoot hormones as well. In the shoot hormones and in the root hormones, the meristem cells are divided into two, leaving one meristem cells as it is and making the other as the respective different cell, a stem cell, leaf cell, or a fruit cell. Benefits of using a biostimulant becomes that you have your plants growing faster, healthier, with thicker stems, more yield per plant. As you can see here, biostimulants are not similar to pesticides. Biostimulants enable the plant to grow, produce their own volatile organic components, which is a natural mechanism built inside the plants to fight against abiotic stress. So what you see here is completely different from what a pesticide would actually behave like. So you have healthier, more produce, higher yield, better nutrition, stronger roots, increase pest and disease resistance, and a sustainable solution. Try to focus here more on the apical meristem cells present at the root. The biostimulant targets the apical meristem cells and initiates the cell division process. This is the first step which always happens when the plant needs to grow. The root has xylem and phloem. The plants have xylem and phloem going all across their systems to enable the transportation of nutrient and water. And these meristem cells are the key components to that development. Similarly, in the shoot hormone, you have stems, leaves, fruits, and flowers. The shoot apical stem is also being targeted by the biostimulants, enabling the cell division in the shoot, leading to cell differentiation, leading to cell elongation, and then cell differentiation. So Let's try to understand what are the roles of biostimulant in overcoming all of these challenges when we understand how the biostimulant works. As we have been hearing now, that it increases the resistance of abiotic stress. It reduces the impact of environmental stress, where you have conditions like lower gravity, you have less sunlight, and you have toxic environment. It enhances the nutrient availability as well. With biostimulants, you're not just making more nutrients available, but you're making the plants build more robust and stronger with the transportation system so that they can naturally absorb more nutrients given to them. Boosting photosynthetic and growth under lower light. The mechanism that is under the hood, which enables the photosynthesis, is being built more robust by using biostimulants. It supports growth during extensive dark period because the plant can now sustain the energy levels during the Martian long nights. It also helps mitigate from the reduced gravity because of the stronger structure that the plants are able to build and the improved water and nutrient transportation system. It's very interesting to know that people have already started looking into growing plants in laboratories using the lunar soil. The lunar soil that we collected from Apollo mission 11, 12, and 17 has been used by researchers, and this study done in May 2022 tells us that when you try to grow plants, specifically the Artemis, which is the plant which is the Arabide Arabidopsis, which is a very popular species because of the presence of the entire gene sequence, it's really important to understand the stress under which these plants go because of using lunar soil. But the real question is that how was this study being done? What kind of nutrients did they use? What kind of setup did they have? They used an MS media, which is a very popular tissue culture plant growth media used very commonly. They did not use any hormones, they did not use any vitamins, neither any biostimulants, which gives us a very interesting opportunity to explore. So let's see in theory what happens if the similar tests are being performed with biostimulants. So in theory, as we saw the role of biostimulants, it improves the nutrient availability. What was the challenge during this study? Because of the lack of organic matter present in the lunar soil, it was very difficult for the plants to thrive. The plants did survive the 20-day trial period, but they did not thrive beyond that. And one of the biggest reasons is because of the absence of organic matter. Now, the biostimulants can be of different kinds, and the specific ones, the being humic acid or the fulvic acid, can improve the nutrient availability in the soil by chelating the micronutrients and enhancing their uptake by the plants. Enhanced stress tolerance. It's another factor that biostimulant offers. So the challenge was that the lunar regolith exhibits significant stress responses due to the harsh physical and chemical properties of the soil. Now, biostimulants of a different kind called the seaweed or the seaweed extracts or amino acids or other beneficial microorganisms can enhance the plant's tolerance to abiotic stress like salinity, metal toxicity, and also oxidative stress, which is a very common characteristics of any extraterrestrial soil. These substances can activate stress responsive genes, and it has been found that seaweed tend to have about 49 stress activating genes present in them. Promoting the root growth. This is one of the fundamental benefits of using biostimulants. It promotes the root growth because it's using root hormones. So the challenge was that the study found that the plants in lunar regolith had stunted root growth, which leads to stunted growth of the plant overall. By using the root hormones like auxins or cytokinins contained in the biostimulants, we can stimulate the root growth, leading to a more extensive root system. Extensive root system equals to better transportation of nutrients and water. Enhancing microbial activity, which is one of the most crucial part of any ecosystem where you want to grow plants. So in lunar regolith, it's sterile. It does not have any microbial uh, communities present in it. With biostimulants, biostimulants can collaborate with other beneficial microbial entities as well, and then create an ecosystem which helps in establishing a microbial community that assists in nutrient cycles, organic matter breakdown, and the overall soil health, which means that you're not just helping the plants to grow, but you're actually leaving behind an ecosystem which helps to grow the next plant in a much easier and safer environment. Mitigating toxicity. As mentioned before, the presence of toxic elements like calcium percolates and nanophase ions in lunar regolith or even in Mars poses a significant risk because these toxic metals are being absorbed by plants, leading to the plants being difficult for humans to consume. Now, certain biostimulants can help plants tolerate or even detoxify the harmful substances. For example, microbes that degrade percolates or plants that can help process these heavy metals. For example, algae can be used with biostimulants to clean up these percolates and even produce oxygen, which is really exciting. Finally, the water retention. The regulates hydrophobic properties made it very difficult to maintain the adequate moisture level. With biostimulants, you not only improve the plant's health, but you also improve the soil structure in which the plants grow. Because the biostimulants help insulating the micronutrients, helps in breaking the organic components, and also helps build the microbial community inside the soil, which is essential for the plants to thrive. So this was the role of biostimulants and also the lunar study which was done to grow plants. But when you're talking about going to Mars, the unit economics is very important to grow every plant because every pound counts. So it's very important to understand that along with the micro and macronutrients that you're utilizing, why do you want to add a third substance as biostimulant for the growth of plants? So I've tried to break it down in a very simple flow diagram. It's very obvious to know that the cost of farming on Mars is going to be very high. But it's not just the money, it's also the payload that you can take with you on Mars. It's really important to understand that the efficiency of biostimulants in resource utilization is the key here. We are not just relying on applying a lot of fertilizers on the plants. We are relying on applying the minimum amount of fertilizers required to grow the plants as nutritious and as effectively as possible. And this is what biostimulant helps you to achieve. Reduces the fertilizer utilization and also maximizes the yield with less input. To give a simple analogy, how this works is that, for example, you need 10 pounds of fertilizers NPK to grow 50 pounds of your produce. Now, with the use of biostimulant, you can use the same 10 pounds of fertilizers to grow 80 pounds of produce. But if you think of it the other way, if you only need 50 pounds of produce, you would need less than 10 pounds of fertilizers to grow the same produce, saving quite a bit of payload here. Similarly, when you talk about having a sustainable farming environment, it's not just what you can grow, but also about how you can recycle it. So biostimulants can work along with algae productions, which is one of the key study areas in the Martian space colony to support the production of oxygen and also creating a sustainable ecosystem. And there has been quite intensive study around this area to see that how algae and biostimulants can work together to enable the fast proliferation of algae in the area. Finally, this is very interesting, that all the medicines that we use here on Earth have expiration date. Imagine something as simple as Tylenol. You can put it on the shelf for 2 years, but if somebody orders a Tylenol in Mars, just the delivery is going to take you 2 years. So by the time it reaches you, it's already expired. So it's really important to understand that we need to first focus on growing these pharmaceutically beneficial plants on Mars, and that is something which could play a very key factor in the promotion of biostimulants and similar components to enable the existence of human colonies on Mars. For example, the recent study have also made the researchers have designed a lettuce or engineered a lettuce to produce acetaminophen, the active ingredient in Tylenol that can produce a continuous and fresh supply to this common pain relief and fever reduction. So with this, I thank you all for listening to me and open for collaboration, because what I believe is that, and quoting, the future belongs to those who believe in the beauty of their dreams. Thank you.
While he's bringing up another mic, we do have a few minutes for a few questions here. I'll actually start us off. I had one. You mentioned near the end the shelf life limitations of some pharmaceuticals, and this is why it would be important to be able to grow them there. I was wondering if you've thought about the shelf life limitations of the biostimulants themselves, and if you have an answer to that problem.
Excellent question. So biostimulants can be of multiple types. They can be organic and inorganic. So we would start something with inorganic, which has quite a long shelf life.
Thank you.
Look at the U.S. military took a look at the expiration dates for medicines and found that the expiration dates for most things were quite a bit longer as far as the effectiveness of them versus the expiration dates. Something to look at. A question from your presentation. You had on there that plants would probably grow shorter. With the reduced gravity, isn't there a good possibility that they'd actually be taller?
The question is that, is it a possibility that with gravity the plants could go taller?
Right.
Question. So in theory, the size of the plant depends on the activities that go with different cell division, elongation, and differentiation. Now, if gravity affects the growth of roots or hampers the growth of roots, then this process of cell division, elongation, and differentiation would not happen. So I don't see a case where you have the bad effect from gravity on the roots and then plants growing taller as well. Provided there are other type of plants, like there are many type of plants, but one specific, the air plants, which are supposed to be going along with the nuclear reactor, which is being planned to release by the SpaceX, don't really need any media to grow. They can grow anywhere. So for them, maybe the gravity would not play a big role in terms of their growth. In that case, there could be a possibility.
Thank you for your presentation. This was awesome.
So are these biostimulants being used at scale currently? And have you seen any challenges from, regulations like the FDA or that could be started to get worked out, in the meantime?
Exciting question. So the question is about regulations around biostimulants being used on Earth. Okay. So every state has their own compliance around biostimulants. Talking specifically about the Washington State Department of Agriculture, we have a clearance from them. And just in terms of biostimulants, it was in the year 2019, 2020, when the regulations around this biostimulant category was being started to come out and in the light. So the states are actually working towards it.